So in this, our first lesson, before we talk about the how we're going to build our CG rig, we're going to start by talking about why we're building it the way we are going to eventually build it. So it all starts with the classic principles of animation. And this will be just a simple overview of just a few of the principles, the ones directly relating to rigging and deformation. But for a more detailed explanation of these principles, there are several books and resources out there. One of them being The Illusion of Life by Frank Thomas and Ollie Johnston, another being Richard Williams' book, The Animator's Survival Kit. Once again, this is a brief overview of just a few of the principles, the ones directly relating to explaining how and why we're going to build the rig the way we're going to build. So one of the first principles is squash and stretch, and this is typically shown as a bouncing ball. You start with a perfect sphere, which is the default volume, and in animation, it elongates to show speed and momentum through space. And then when it contacts the ground, then it will squash and flatten to sort of show the change in energy. So that's one of the basic principles, and that's a principle that we'll use to denote volume control in our rig. So we'll need to put in controls so that we can scale and expand certain portions of the character. And this next image illustrates it a lot more clearly. Here we have a very simple character where his midsection is basically a sphere, and we can see in this bouncing motion here how the squash and stretch will help to show the sense of motion as well as impact for the character. So once again, these are controls that we'll need to think about when we're building our rig. So another principle is follow through. And here, an example of a simple tie moving from left to right. We can see the tie sort of flowing, sort of showing that sense of motion. And it's very fluid, and once again, another thing that we're going to have to add into our rig. And this will be, like many of them, will not only be a rigging control, but a combination of rigging and deformations. So in this lesson, we'll set up the foundation. And in the next lesson, the second part of this series on deformations or skinning, we're actually going to continue with some of the rigging. We're going to add rigging that's directly applied to deformations that will allow us to get these nice bends and arcs to help us denote follow through with our character's motions. So here's another example of follow through, and we call this breaking joints. And in a character which has a sense of anatomy where you want to show the joints of the arm in a sense of a rigid understructure and anatomy going on there, you often need to break the joints, meaning to bend them in successive order, and sometimes bending them in ways that they can't normally bend. But that's a part of the flexibility that needs to be built into rigs. So here's another example of breaking of joints. And here we can see the elbow is bent at its normal angle, but in a very quick move, as it moves upward, you'll need to reverse the elbow. So once again, this is a control that will add both through the rig itself as well as the deformations, allowing us to, regardless of what the joints are doing underneath, often the animator will need to have the flexibility to literally pull the geometry off the joints to get the line of action that they need. So another example of breaking joints, here in the opposite direction, where the arm moves down quickly. So another principle of animation is line of action. We can see with these two drawings of the same character, just through the line of action, through his body, we get a very clear indication of that character and what their pose tells us, not only in terms of posture, but also in terms of attitude, what's going on inside this character's mind. And this is clearly something that we can control with the rigging and deformations, giving the animator control over this line of action. So next we move into overlapping action or counter action. And this is another tool that will be used for volume control. And then in this simple character, a very large character, as he walks and moves up and down, you will have the different masses moving in different directions and at different speeds to show a counteraction or lag or mass. And once again, very clear control that we can add in the skinning portion and deformations on this character. And this is once again shown in the squash and stretch of a character's face. You know, in the first drawing here, he's startled. He reacts by sort of compressing and drawing inward and then expands outward. Typically in animation, if you want to move from a very a standard or stock pose, this being sort of the default proportions of the character, if you want to move from that to a more extreme pose, you typically need to give yourself a place to go. And what that usually means is you'll get a more dramatic effect rather than transitioning directly from this pose to the more extreme pose if you compress it. And with this squashing, will just further accentuate the stretched or expanded pose. And so that draws on both the squash and stretch of the bouncing ball as well as follow through, the overlapping action showing the sense of mass, of having different masses in that face moving at different times. This is another example of squash and stretch as well as overlap. A character just quickly looking from left to right. So once again, we're getting squash and stretch, volume compression and expansion, as well as overlapping action to show a sense of weight and fleshiness and volume. And this type of thing, specifically with the face, we'll get into in detail with the third part of this series when we get into facial rigging. We'll build in quite a few controls so that the animator can squash and stretch regions or volumes of the character, as well as have localized controls over the character's volumes. Once again, another more straightforward example of squash and stretch. We start with the default pose of the character, and then rather than transitioning directly to this stretched or accentuated pose, we'll squash the face to give it a place to go so that this final pose is more heightened. So here's another example of a squash and stretch on a full character's body, and this gives us a sense of anticipation. As the character starts at their default pose, he compresses inward, and that gives us a sense of anticipation. We know that something's going to happen. It's sort of like stretching a rubber band. You know that it will release the energy and spring in the opposite direction. So here, once again, we have overlapping action where the character springs forward and one mass moves before the rest of the body, and then the body will eventually catch up. So here, this is a combination of rigging, where we'll need to be able to extend, squash, and stretch various regions of the character. So here we go from a default pose to not only the face being expanded, but the neck and the arms as well. So lastly, we have what we're seeing here is a very quick move where we have pretty much all the principles applied here. We have squash and stretch, where the volumes are changing their shapes, their volumes based on the speed of the movement. We have overlapping action. We have breaking of joints. Pretty much everything is going on in this one. And once again, a combination of rigging and deformation controls, but quite a bit of this will be controlled through the rigging, where we'll be able to scale finger joints. Despite the angle of the arm joints, we'll give the animator controls to sort of contour the line of action on the arm. We'll be able to stretch the limbs so that they can achieve this overshoot. So all of this we'll be able to achieve in our rig, and this is our goal of encompassing as many of these principles of animation, the ones specifically relating to rigging and deformations, and to this rig that we're about to embark in building. But before we start, I'd like to thank a talented artist and animator and friend, Joe Sandstrom, for providing these drawings for this tutorial. So, without further ado, we'll end this lesson and then begin building the rig now that we've discussed why we're building it. Now we'll talk about how we're going to build it. So now we're going to talk about one of the primary tools used for both rigging, skinning, as well as for animation, the joints, or sometimes called bones. For animation, this is the tool that they'll use to manipulate and pose their character. And this is done either through direct manipulation of the joint or by indirectly manipulating it through controls, which either drive it through a parenting scheme or with constraints. So typically you'll see animators rotating joints, although it shouldn't be confined to just that. You can effectively use all the transformations when rigging a character. But typically you'll see a rotation used. For rigging and deformations and skinning, it's through the transformations on this joint. And these transformations drive the position of the vertices or CVs of the character model based on the weight that's inherited from each of the joints in the hierarchy or rig. So what basically is a joint? I guess basically you can boil a joint down to a hierarchy of pivot points, either a single pivot point or a hierarchy of pivot points. So here, let's open up our hypergraph. Let's frame this. We can see we have two joint nodes. Each is basically a pivot point. If we unparent them, we can see that we have two separate objects. And how Maya determines how this joint affects the CVs or vertices of a model is through the transformations applied to this pivot point. This is quite similar actually to a simple parented hierarchy. Here I have another example to show what I mean by that. So here we have two 3-node hierarchies. One are joints, which are parented into a hierarchy, and the other are 3 polygonal cubes. Let's open our hypergraph once again. So here we can see the similarity in these. 3 joint nodes and 3 polygonal cubes. Display their local rotation axes. Just go ahead and fix this one here. So we can see, although they're oriented differently, they're basically 3 pivot points. So let's select and manipulate these and see what we get, and to demonstrate how similar they are. So here we can rotate them and scale them. So I'm going to do a similar action with the parented cubes. Rotate and scale. So that way you can see how similar these two structures actually are. And one thing I've shown here is this local coordinate system, which is called a local rotation axis. This is something that you want to keep an eye on when building rigs. If this were a spine, for instance, an animator would expect to select these two joints, and when rotating them, to have them rotate in a predictable manner. I'm going to switch to component mode and actually flip this local rotation axis arbitrarily. Return to object mode, let's select it, let's rotate it on Y, and here you can see we're getting a totally unpredictable rotation. So by making sure that your local rotation axes are all aligned properly to give you the rotation that an animator will be expecting, that's one thing that will help ease the animation process as well as control the deformations and motion of your character's hierarchy. Another interesting thing with joints is rotation order. I'll switch back to our single joint here. Every object, every DAG object in Maya which can be transformed has a rotation order. Let's open up our attribute editor. And here we can see in rotate order, it's set to X, Y, Z. What this means is this is the order from top down that the rotations are evaluated on this character. So let's display our local rotation axis. And we can demonstrate the importance of the local rotation axis by putting this joint into a situation that's called gimbal lock. What gimbal lock is basically is when a 90-degree rotation is applied on a joint, depending upon the rotation order, you can lose a degree of freedom by aligning two of the three axes with one another. And that can happen, for instance, this joint is in an XYZ rotation order. So if we were to skip the X rotation and go directly to Y and rotate it 90 degrees, we can see that we still have our Y rotation, but our X and our Z rotations are aligned with each other. And if we return to the original position of the joint, we have 3 degrees of freedom. There's X, there's Y, and there's the Z rotation. But by bypassing the first rotation in the rotation order and putting a 90-degree rotation on Y, then we can see that we've aligned the Y and the X rotation. So they're both pointing down the length of the joint. Gimbal lock is something that you'll need to be aware of, particularly in areas such as the hip, but more so in the shoulders, where a character with the ball joint configuration can easily put an arm into a gimbal lock situation. And although with Euler rotations, gimbal lock is not at all 100% avoidable, there are ways to alleviate it. For instance, if Y and Z are the dominant rotations for the character's arm, let's say this is an arm, we can go in and change the rotation order from XYZ to YZX so that it will evaluate those two rotations first, and then the less dominant rotation down the axis of the joint last. Let's go in and repeat the process by rotating it 90 degrees on Y. So we still have our X-axis as well as our Z. So there we've shown the importance of the rotation order, as well as a demonstration of what gimbal lock is and how you can help to alleviate that process. So another thing I want to talk about with a joint, the last thing actually, is segment scale compensation. Switch back to our multiple joint here. Let's hide our polygons and handles. So what segment scale compensation does, let's rotate this off axis. I'm going to select the first joint and scale it. So we can see that the second joint, the child of the first joint, retains its original scale, which is 1. So if we were to select that joint and open the attribute editor, we can see that if we scroll down to the joint, we have segment scale compensation enabled. If I were to disable that, it doesn't know how to compensate for the off-axis scale, and so we get skewed joints. Typically, you want to keep this enabled on a joint chain. I mean, there are instances where you can use it to your advantage in rigging, but it's something to be aware of. So those are the major components and joints within Maya. So now let's move on to the next section on the fundamental tools of rigging. So in this lesson, I'm going to go over a brief description of the various kinematics available to us in Maya. What I mean by kinematics is basically motion. Kinematics means motion, but more specifically, joint motion. Joints being one of the primary ways of affecting or deforming the surface or skin of a character. So let's start going over these. So we're going to start with FK, or forward kinematics. How this works, these are joints which are basically rotated. All the transforms are available to you, but primarily an animator will use rotation on a forward kinematics chain. This is called forward kinematics because if this is an arm, for instance, in order to position the wrist at a specific space in the scene, an animator would typically start at the base of the hierarchy, rotate the base, and then move forward through the hierarchy to position the end of the wrist. So in that way we call this forward kinematics. You start at the base and move forward through the hierarchy. Another important idea with forward kinematics, let's select both of the joints. Let's rotate them forward in Z so that the two joints, or this arm, will curl forward. And here we see we get an unpredictable result. So with both of the joints selected, we're going to display our local rotation axes. Display, component display, local rotation axes. So here we can see the Y, Z, X coordinate frame of each of these joints. And what this does is it tells Maya how these joints rotate. So here we can see that this is a positive Z rotation. And we can see this Z pointing in an opposite direction. We can guess that rotating forward is a negative Z rotation. So that's why we get the unpredictable results. As a character TD, one thing you're going to want to watch with all of your joints is you want to make sure that your local rotation axes are aligned so that an animator will get predictable results when they're rotating the joints. So to change this, we can switch to component mode and then select the question mark icon, which gives us access to the local rotation axis component. With that selected, we can drag over our local rotation axis and then rotate it 180 degrees along the x-axis so that it matches the orientation of the base joint. Rotate minus R, which is relative, 180 degrees in X, 0 in Y, 0 in Z. Switch back to object mode. Select both of our joints, activate our rotate tool, and rotate forward, and there we have a much more predictable result. So the next example is IK, or inverse kinematics. So this works obviously in a way that's opposite of forward kinematics. Rather than starting at the base, we no longer have access to the individual rotations of these joints. Instead, this IK, we can think of it in this way, where we have an IK handle, which is at the tip of the joint chain. We position the IK handle in space, and at the end of this joint chain, there's an object called an effector, which we can think of as being point constrained to this IK handle. So wherever we move the IK handle, the effector will follow. And then Maya figures out in reverse that in order to position the end joint and the effector in the same position as the IK handle, in reverse it figures out what rotations need to be placed on the joints. Hence we call this inverse kinematics, since it figures out, it solves in reverse or inverse. This is very useful if you want to lock down an object. You can position the IK handle and set a keyframe and then move the base, and the end will remain in place. So we can see that this can be good for both arms and legs, as well as many other things. So here we have a new solver, or kinematic solver in Maya 7 called the Spring Inverse Kinematic Solver, or Spring IK. So here we have identical joints, sort of a simple spring configuration. And here we have a standard IK handle. So when we translate that down, we can see that we're affecting the rotation, or the IK is solving at the first bend and the second, but not in the middle. So we're getting an uneven distribution of the deformations on the spring. Whereas with the new spring IK solver, it evenly distributes the compression throughout this chain. Once again, this is something new in Maya 7. It can be useful for all types of things: antenna, mechanical devices, the legs of an insect, but very useful, very useful. Okay, and the last example here, and these are very quick, simple examples, because we're going to go over a lot of these in much more detail in the examples to follow when we're building our character. This is spline IK, or spline inverse kinematics. So I'm going to select the end effector here, or the IK handle. We can see that we get an error or a warning saying that basically we can't really move this in the 3D view. That's not how the spline IK works. Instead, switch to component mode. There is a spline, or a curve, running through all of the joints. And the deformations on the spline determines how these joints are positioned in the scene relative to each other. It's as if the splines are locked onto, or the joints are locked onto the spline, and by changing the shape of the spline, we can change the shape of this chain, because they're constrained or almost path animated along this spline. We can see that a spline IK can be useful for a spine of a character, a tail, once again an antenna, many other things. So as I said, we're going to go over most of these in much greater detail as we go through building our character. Primarily, we're going to be using the forward kinematics, the inverse kinematics, and the spline IK, along with many others, but those are the main kinematic solutions we're going to use with our character. And although I showed the spring IK, we're not going to use that on our character, not in this example. So there we have a basic, very quick and general overview of the kinematic solutions available to you in Maya when building a character. So in this lesson, we're going to talk about a very fundamental concept in rigging and 3D in general. We're going to talk about hierarchy. And what I mean by hierarchy is the ability to create a parent-child relationship between two DAG nodes in a Maya scene, or multiple DAG nodes in a Maya scene. Although very fundamental, you're able to achieve some pretty stable and basic results by simply parenting or hierarchy. Through this parent-child relationship, you can pass the deformations, translation, rotate, or scale of the parent down to the child. This also is true for things like texturing. If you have a parent-child relationship and you apply a shader to the parent, it's also inherited and applied to the child. So this is true for not only transformations, which we're particularly concerned with rigging, but also things like shaders. So I just used a term, a DAG node. What a DAG node is, in Maya, it means a directed acyclic graph node. And what that means, rather obtuse term, is these nodes have a sense of hierarchy, of parent-child relationship within the scene. For instance, object B can be a child of object A, but you can't create a cyclic parent-child relationship. For example, object A can be the child of object B, but at the same time, object B cannot be a child of object A. That would create a cycle where each is both the parent and the child of the other. Another thing you can't do with the DAG node, in terms of the acyclic aspect, is object B, for for instance this object, cannot be the child of both objects at the same time. This object can be a child of this object, which can then be a child of this object. So in that sense, it will inherit all the transformations down the hierarchy. I'll give you a quick example of this with the classic Sun, Earth, Moon hierarchy example. So we have three spheres here. Let's open up the hypergraph. And we can see that they are completely in a flat hierarchy where one is not related to the other at all in a parent-child relationship. So in that sense, I could select any of them and transform them without affecting any of the other nodes. That's because, once again, they're in a flat hierarchy. There is no parent-child relationship between them. So we're going to create a simple solar animation here, where the sun will rotate, the Earth will revolve around the sun, and the moon in turn will revolve around the Earth, which is in turn revolving around the sun. We can do that simply through hierarchy with parenting. Once again, this is a very fundamental concept, but wanted to understand if it has never been explained to you thoroughly. So we're going to start by setting up the Earth-Sun relationship. So what we'd like to happen is when the sun rotates, we'd also like the Earth to inherit those rotations and also rotate around the sun, keeping its relative offset from its parent. So we can do that parenting multiple ways. In the hypergraph, for instance, you can middle mouse click on the child node, drag and drop it onto its parent node. So now it is a child, the Earth node is a child of the sun. Let's undo that. You can also select the child, shift select the parent, and select Edit Parent. Once again, we have the same parent-child relationship. Let's look at what we have at this point. Any transformations, rotate, translate, scale, to the parent are inherited by the child. We can rotate, and we can even scale it. You can see they're both scaling together. Additionally, the Earth, the child of the sun, also has its own transformation channels available to it also. So here, we're going to rotate the sun 360 degrees over 100 frames. So that's on the y-axis. So I'm going to set a key at frame 1, scroll to frame 100, and input 360 to rotate it once completely, and set another key. So here we can see that the Earth revolves with the sun. Although there is no animation on the Earth, it inherits the rotations or transformations from its parent. But we're leaving the moon behind. Once again, we can create another parent-child relationship by making the moon a child of the Earth. So wherever the Earth moves, whatever transformations occur on the Earth will also propagate down or be inherited to the child. So that's the motion we get revolving around the sun. We're also going to rotate the Earth. Here we're going to set rotate values a default of 0 at frame 1, and at 100, let's say we'll rotate it negative 720 degrees, or twice in the opposite direction that it's rotating around the sun. So there we can see the Earth is not only inheriting the positive rotation values of the sun, but it's also rotating about its own axis negative 720 degrees, or twice. And the moon, being a child of the Earth, follows along with it. So now I'm going to display the local rotation axis of the moon so we can see this more clearly. And rotate it about its own axis. And this time we'll rotate it in Z, let's say positive 3600 degrees, or 10 times over 100 frames. Let's display all these local rotation axes. So with this hierarchy stack, the sun rotates 360 degrees. The Earth inherits that rotation, but also has its own 720-degree negative rotation. And the moon inherits the rotations of the sun and the Earth, but once again has its own rotation about its own axis. Let's see what we get here. In these transformation inheritance, it's not constrained to just rotation. We could also translate the moon out. For instance, translate it on the x-axis. We'll go 50. A little too close to the Earth. Take it to -2. Then back to -3 at the end of the 100 frame cycle. So we can see here that we can also translate the moon. Actually, let's take it a lot closer just to make it more clear. Let's get a near Earth-Moon collision there. So you can see the moon translating as well as rotating about the Earth axis. That's a simple Earth-Moon sun example with parenting. So we're going to move on to another example where we'll take on an analogy of a root node, branch nodes, and then leaf nodes. Using a, rather than a parent-child analogy, it's still a parent-child hierarchy relationship, but often you'll also hear the root, branch, leaf terminology used in parenting hierarchies as well. Open up our hypergraph and frame these, and once again we can see all these nodes are in a flat hierarchy. They're not related to each other at all. I can grab any of them and transform them without affecting any other. What I'm going to do here is I'm going to create a relationship between both branches and the root. I'm going to select both branches, shift select the root, and parent the branches to the root. So now we have a relationship where we can transform the root, and the two branches will inherit all the transformations. So next I'm going to create a relationship between these two leaf nodes and this branch node. So now our two leaves, leaf A and leaf B, are children of branch A, and then we'll make leaf C a child of branch B. So we have our root as the base or root of the hierarchy. We have two branches where one branch has two leaf nodes as the child and the second branch has one. So all of the nodes will inherit the transformations of the root node. And the two leaves will inherit the transformations of their parent, branch A, and likewise for leaf 2, they'll inherit the transformations of branch B. Once again, this is another simple example of a parent-child relationship using root, branch, leaf terminology. Once again, fairly simple, fairly straightforward, but very important fundamental concepts that I didn't want to skip over. I just wanted to explain them before we move ahead with the rigging demos that are to follow later. So now we're going to get a brief overview of the 5 main constraints used in Maya. Those being the point constraint, aim constraint, orient, scale, and a relatively new constraint, the parent constraint. A few other constraints exist in Maya, but these are 5 of the most used constraints. So those I'll cover in this section here. What all constraints do is they work on the pivot point of an object. They use the transforms defined by the pivot point of one object and manipulate or drive another object's pivot point accordingly. Let's start with the point constraint. What that does is it will drive one point or pivot positionally of one object by another, basically snapping the pivot point positionally to a driving object. So let's demonstrate that quickly. And all constraints in Maya work with the same selection process. You select the driver first, the object that will control the other object, and then you shift select the object that will be driven second. So with these two objects selected, the driver and the driven, I'm going to select constrain point. So open up our hypergraph. We can see that our driven object now has a point constraint node added to it. And every constraint node will have offset attributes, where you can offset, in this case, the position in X, Y, or Z. There's a node state drop-down menu, which gives you access to whether the constraint is working or whether you have it blocked and a few other state values. And then there's the weight value of the constraint. Right now it's at a weight of 1 or 100%. So to demonstrate this point constraint, we can select the driver and translate it around in space. If I select the driven, we can see that it's right on top of the driver node. Positionally, there's no difference between them. But if I rotate this, then we can clearly see our driven node. Once again, with the point constraint, we're only getting positional information. We're not getting any orientation information from this constraint. Okay, let's reset this. Let's delete our point constraint. Let's move on to the next, which is an aim constraint. What an aim constraint does is it will point the driven object toward the driver object. So in this case, I'm going to point or aim this driven object to the center or pivot point of the second driver object. So once again, we start by selecting the driver, shift selecting the driven object, and I'm going to select constrain aim. Here I'm going to open up the option box. There are quite a few useful options with an aim constraint. So here we're going to use the default value. What it's telling us here with the aim vector, it gives us 3 values for X, Y, and Z relating to the coordinate system, the local coordinate frame of the object. And then we have a weight value of 1, meaning that the aim vector is 100% in X, so X will be the controlled aiming vector. And then 0 in Y and Z. And you typically only want one aim vector, although it is possible to have multiple. The up vector defines just that. There will be the aim vector and then a vector that's called the up vector. In this case, there's a world up type which corresponds to the up vector. In this case, we're using vector. We could also use scene up, which is defined by the Y up of the scene. We'll leave it at the default for now. And then the constraint axis, which defaults to all. So we're going to click Apply. Nothing has happened. But if we open up our hypergraph, we can see that we have a new aim constraint node beneath our driven. Once again, we have the weight of that node, offsets, and then the node state drop-down menu. So now if we select our driver object and translate it around, we can see that our driven object, the x-axis always points toward the pivot point of the driver object. So I'm going to delete this aim constraint node and go over one more useful option, although there are others, but I'm going to create a locator and translate it out in Z. So now I'm going to select the driver object, shift select the driven object, and I'm going to change the world up type from vector to object up. And that activates this text entry field where we can specify the world up object. In this case, we're going to use locator 1. And I'm going to leave this with the up vector of y so we can clearly see what happens when we use this world up object. Going to hit apply. We can see that now our y points toward this locator. So once again, we can translate our driver object around. But we can also select the world up object, the locator, and then use that to affect the twist or the up vector of this constrained or driven object. Okay, so let's delete that node. Once again, this is a very brief overview. We'll use a lot of these constraints as well as the options throughout the tutorials. The next is an orient constraint. And in a way it's similar to an aim constraint in that an aim constraint drives the rotate values of the constrained object. What an orient constraint does is it's like a point constraint but a direct connection with the rotate values or the orientation of this pivot point of the driven object to the driver object. Once again, select the driver object, shift select the driven object, select constrain, orient. What happens, and another clue here is you can tell if an object is being driven by another object is if you select it, the driven object, the object that has connections to the object that's selected, will highlight, in this case the default purple or magenta color. This does not have any connection to the driven object, so if we select it, we don't get the highlighting. But here we have the orient constraint. So with that selected, once again we're saying that it's a direct connection between the orientation of the pivot points. If we translate this, it has no effect on this because we're only driving the orientation of the driven object. The next constraint, which isn't used, I tend not to use it that often, is the scale constraint. Once again, the scale of the pivot is directly connected to the scale of the pivot of the driven object. We select the driver object, shift select the driven object, select constrain scale. Once again, our translate transforms have no effect, nor do our rotate transforms, but only our scale transforms. So on all axes, the transforms on the pivot of the scale of one object drives the other. And the last constraint we're going to go over in this brief overview is called the parent constraint, which is a relatively new constraint in Maya. And what this allows us to do is to constrain either or both the position and the rotation or orientation of the driven object but by multiple objects. Let's give an example here to more clearly demonstrate it. I'm going to select the driver A, shift select the second driver object, and then shift select last the driven. Select constrain parent. Let's open up the option box. And we'll leave it at the default values for now, where we have maintain offset enabled. And what that does is whatever the relative offset of the driven object is to the two driving objects, it will maintain this offset position. And then we have the constraint axes of both the translate and the rotate, all the channels selected. So I'm going to click apply. And here with the constraint node, we see that we have two weight attributes. One for driver A, weight 0, and one for driver B, weight 1, index 0 and 1. So I'm going to quickly set driver B to weight of 0. We can select it and we can see we have a connection, since once we select it, the driven object highlights. I'll translate this, no effect, and rotate it, no effect. And that's because the weight of the parent constraint for driver B is set to 0. But if I select the driver A object, which still has its weight set to 1, I'll translate it. It's as if it's an offset point constraint. And that's because we have the maintain offset selected. And I can also orient it. And this works differently than a point orient constraint in that it works as if we were switching between the parenting of these two objects, something that we go over in the hierarchy chapter. So once again, rather than getting the actual orientation where this would remain in place and simply rotate with the driver object, it behaves as if it's a child of this object. So now we're going to switch the weights. We're going to turn the weight to driver A to 0, and then turn the weight of driver B to 1 or 100%. Let's translate driver A. We can see the connection still exists, but its weight is 0. So once again, it has no effect on the driven object. But now it acts as if the driver B is the parent of the driven object. This parent constraint can be quite useful in areas where you need to toggle between the position or orientation in a hierarchical sense, a parent-child sense. And we'll use it later on with things such as toggling between a local and global rotation of an object. If you have a shoulder, for instance, that you want to follow the chest or to switch so that it follows the root of the character. And we'll use a parent constraint for things like that. Once again, it's a relatively new constraint in Maya and very useful. So those are the 5 primary constraints in Maya. Very brief overview. And they're pretty straightforward once you use them and experiment with working with them. And in rigging, it comes down to often using them in a creative way of finding out what motion you need or what inheritance you need, and how to creatively and effectively use constraints to arrive at that. So in this brief and basic lesson, we're going to go over expressions and utility nodes. Through a pretty simple example, we're going to show how they're created, as well as their similarities and differences. So the example we're going to use in both cases is we're going to use the rotate Z of joint 1 to drive the rotate Z of joint 3. But rather than having 100% of this rotation driving the rotate Z of our target joint, we're only going to use a percentage, let's say 25% of the rotate Z of our driving joint, and then pipe that into the rotate Z channel of our target joint here. So we're going to start by creating an expression, We're going to select our target joint and then open the expression editor by selecting Window, Animation Editors, Expression Editor. So here you can see we have an input field for expression name where we can actually name our expression, something I always recommend doing. Because once it's named, then you can click on your Select Filter tab or menu option, and then you can select filter by expression name. And what that will do is it will list all of your expressions by name in this dialog window here. Let's name our expression. Let's call this rotate follow underscore exp for expression. This way I can quickly look at it in the channel box and see that it's an expression. So here it lists the object that our expression will be created for, as well as the attributes that are animatable on this object. So in this case we're going to scroll down to rotate Z, and then here the selected object and attribute, it shows that joint 3 rotate Z channel is what will actually create our expression on. Let's expand this window a bit. So I'm going to select that and copy and paste that into the expression dialog window where you actually create the components of the expression. Another thing we want to notice here is the evaluation. Right now it's set to always, and what that means is whenever the timeline is updated, the expression will be evaluated. Here you can set it to on demand and after cloth, which is obviously cloth specific. But typically you want to keep it to always so that an expression is continually being evaluated throughout a scene. And here for the editor, we want to leave it at expression editor, which is the window that we're using now. So here we're going to define what our rotate Z will be driven by. So we'll start by putting an equal sign. Rotate Z of joint 3 is equal to, we're going to type in joint 1 dot rotate Z, and the dot is the designates a channel on the object. Joint 1 is the object and rotate Z is the channel. We're going to multiply the rotate Z by 0.25 and then end it with a semicolon. Hit create. We can see that the rotate Z channel has been colored purple, which shows that it's being driven by an expression. And then we have a couple of new inputs into our joint 3. One is the actual expression, and the other is time. And the reason why we have this time node is the expression is evaluated whenever the time node is updated. So whenever the timeline is updated, then our expression is evaluated, which we went over a little earlier by showing our evaluation is set to always. Let's rotate our driving joint, joint 1. We can see that we're only getting a percentage of the rotation. Let's set this to -100, which means that we'll multiply this by 0.25, so the rotate Z on our joint 3 is -25, or 1/4 of the rotate Z value on our driving joint. So there we have an expression, pretty straightforward. So we're going to duplicate this process using a utility node. So we're going to use the same joints, select this, and in the channel box I'm going to select our rotate Z channel, which is now controlled by the expression, right mouse click on that channel, and break connections. And what that does, any connections going into that channel are then broken, and we can see that we no longer have any inputs into our joint 3. So to create a utility node, we need to open up our script editors, clear it out, and we're going to create a multiply and divide node so that we can once again multiply the rotate Z of our joint 1 by 0.25. So to create a multiply divide node, we're going to type create node with a capital N, and we need to specify the type of node we're creating, in this case a multiply divide, a capital D here. We're going to give it a -n argument, which is name, and here we'll give it the same name, rotate follow, and give it an _MD suffix for multiply divide rather than exp for expression. Let's select that and hit enter. You can see that it's created a node for us, and that node is immediately selected. So with the node selected, let's open the attribute editor, and we can see that for this multiply divide node, the operation is set to multiply, which is the default and the one that we'll eventually use. But let's look at some of the other operators here. Here we have no operation, which basically is a complete pass-through, so that it won't do anything to the inputs. We can divide, or we can use the power operator, which is an exponent. In this case, we're going to leave it on the default, which is multiply. So we can close that. So now what we need to do with this multiply divide node is we need to connect the rotate z value into the input 1z, and then multiply it by the value of input 2z, which will be 0.25. So let's open up our connection editor, window, general editors, connection editor, and with our multiply divide node still selected, load that into the inputs. Let's expand our input channels, select our joint 1, load that into the outputs, and scroll down and expand our rotate channels. So once again, we're going to connect the rotate z to the input 1z, select our multiply divide node once again in the channel box and load it into the outputs. Scroll up to the top. Here's our multiply divide node. Let's expand our outputs, which is the result of whatever operations we're doing with our multiply divide node. Select our target joint, load that into the inputs of the connection editor, scroll down and expand our rotate channels. Then we're going to connect the output of this multiply divide node into the rotate z of our target joint. So when we select our joint 1 and rotate it, we get a 1-to-1 rotation correspondence, 33.906, 33.906. And here it's colored yellow, which is showing a different type of connection. So the reason we're getting a 1-to-1 correspondence is we need to set one more channel on our multiply divide node. So let's expand it in our channel box, and we need to multiply our input 1z by 0.25. So now when we select our joint 1 and rotate it, we're getting a quarter of the rotation of our joint 1. So let's set this to -100, and we'll have -0.25 in the rotate z of our target joint. Let's reset this. So you can see that in this case the expression and utility work, and they give you the identical results. One of the differences being is that with an expression it's evaluated on every frame. And in a case where you have a rig where there are a large number of expressions and complex expressions, each of them needs to be evaluated on every frame, whether they need to or not. For instance, if I have 1,000 joints with this same expression on it, and only one of them is rotating, all 1,000 of them will need to be evaluated each time the timeline changes when you scroll back and forth in time. And although that's a very simple example, on a complex character with a decent number of complex expressions, that can sometimes bog down your scene a bit. You'll see a performance hit. Not always, but sometimes. Whereas with the utility node, there's an object called a dirty bit. And what that means is a utility node will look to see upstream if whatever inputs are feeding into that utility node, if those inputs have been updated, then the dirty bit will be set to it needs to be evaluated, or on. And in that case, the utility node will look at the inputs and then process the value and then output that downstream. If, on the other hand, the inputs into the utility node have not been updated, then the dirty bit remains at 0 and it doesn't need to evaluate. So in a similarly complex character with a similar number of utility nodes, in this case, if we have 1,000 of these multiply divide nodes, if only one of them is being updated, then only that utility node will have its dirty bit set to 1, and so you'll only need to evaluate that one multiply divide node. So in that case, Maya can more intelligently evaluate the scene. Now we saw here, let's select our multiply divide node and open our connection editor once again. So we can see here with the multiply divide node, it behaves similarly to all utility nodes. They're sort of like black boxes. They'll take any type of input, perform an operation, and then output it, not knowing what the input is, although it has to be a suitable type. For instance, input 1 will accept a float value, whereas it won't accept a string value. It performs an operation, in this case multiply, and then outputs the result of that operation downstream to who knows what. It could be another utility node, or it could be an attribute in a shader. The utility node really doesn't care. It just does what it does, performing an operation on whatever data is fed to it. We can see this. We're going to create another utility node here, a condition node. So create node, conditions, give it a name. Let's call it just test underscore CND for condition. Select that, hit enter. And then load this into our connection editor. Let's expand these color of true and false. So we can see here that the condition node, the inputs specify color if true or false. But you'll see in later lessons, I actually use this rather than for inputs. I connect rotate values, float values, into these color of true and color of false values. These channels require a float value to be connected into them, and then it outputs a float value. It seems to have been originally written for shaders and for colors, but as long as it's a float value, it really doesn't care what inputs it gets as long as it's the proper type, and then it outputs a float value into, once again, another node or an object directly. So that's basically how a utility node works. It takes information in, performs a given operation, and then outputs it, not knowing what it's actually outputting to downstream. And a Maya scene, or a DG scene, or dependency graph scene, is essentially a collection of several, sometimes thousands of utility nodes, all connected together, and that compilation of utility nodes and their connections will actually specify or denote every single thing in your Maya scene, whether it's animation, whether it's modeling operations, operations on particles. They're all defined by dependency graph nodes, utility nodes, and their connections to one another in a Maya scene. So once again, it's a quick example of expressions and utility nodes. And in these examples to follow, I'm going to use utility nodes or dependency graph nodes for all of my mathematic operations and conditions. I could have well used expressions, but for the reasons given earlier, just for a more intelligent scene evaluation, I'm going to stick with using utility nodes. But once again, either is fine, expressions or utility nodes, and often you'll find yourself wanting or needing to combine both of them to get the results that you want on a character rig. In this lesson, we're going to talk about naming conventions. There are a few components that I believe are pretty good standards to have in any naming convention. One of them is that there should be some indication of the name of the character, creature, or object or prop name somewhere in the name, preferably in the beginning. This way, if you have 4 characters in a scene and they all have left arms, if you have the name of each character on each specific node, that way you don't have to rely on Maya's namespacing to differentiate those. You could just search for that particular limb or node with that character prefix on it and find it immediately without having to sort through several duplicate nodes. Another thing that I believe a naming convention should have is an indication of whether an object in the rig is on the center of a character or prop, the left or the right. You can break it down and be more granular than that and indicate front, back, top, or bottom depending on the design of your character or prop. Another thing is having a description of what that object is. That's pretty obvious. For instance, if it's, we'll stick with the arm example. If it is a left arm, of having to know which indicates, that it is an arm. And usually on this node, I tend to put a numerical indicator. For instance, an arm will have multiple joints. You can have arm 01, arm 02, or you could have shoulder, elbow, and in that case you don't need the numbering scheme. Another thing that a node should have is I think that there should be somewhere within that naming convention an indication of what type of node it is. For instance, whether it's a joint, a utility node, and if so, what type of utility node. That way you can just quickly look through your nodes and see what that node is just very quickly. And lastly, I think that, or almost lastly, I try to avoid having numbers on the ends of my node names. I like doing that because if there are duplicate nodes, you can quickly look those up and they'll point themselves out by having numbers on the ends of them. So if you name them without numbers, you'll be able to quickly see if there are any duplicate nodes by just seeing if there's a number on the end of them. And the last thing is, with all these different components, is having some sort of token which will separate each of these naming components. I tend to use an underscore. You can use dashes, colons, whatever it is, as long as it's consistent and something that you can use to tokenize a name using mel, so that way you can split it into distinct parts. So here we have an example of a simple two-joint chain with an IK handle and a pole vector locator. So here, let's open up our hypergraph. We can see that I have named the joints with the naming convention that I'm using for this character for these tutorials. I start with the character prefix, in this case just char01. It can be, this token can have any number of characters in it. You could spell out character, you can have ch, it really is up to you and your pipeline. But anyhow, here's the indication of the character name. Once again, since it is possible to have multiple iterations of this character, if there were to be a second or third, then I would just change this numbering to char02 and char03. Then I have an underscore, a token, and then I indicate that this is on the left side of the character. Once again, this could be uppercase, lowercase. I just choose to number all of my nodes with lowercase letters. It's fairly arbitrary as long as it's consistent. And this also allows me to quickly and easily, as long as it's consistent, to mirror joints from the left side to the right side. I tend to build all my left side joints first and then mirror it over. The next name, I just have it generically as lim01. The next one is lim02 and then lim03. Now, this would be more descriptive if this were an arm or a leg or a spine. And then we have the numbering. Once again, you can have any number of digits here. If you expect to have, more than 100 of a single type of node, then you may want to expand this out to 3 numerals, 001, so that way you can go up to 999. So depending upon the show that you're working on, the restraints of your pipeline, you may have 1 digit, 4, it depends upon the naming convention that is works best in your pipeline. Then lastly, I have IK, which describes this as an IK type joint. It could be JNT, it could spell out joint, once again, as long as it's consistent and descriptive. So here we can see I have a similar naming convention, char01 underscore L underscore lim01 underscore EFF for an effector. Here I have an underscore IKH for IK handle. And then lastly, I have lim polvec01 underscore LOC for locator. So once again, this contains many of the ideas that I think work well in a naming convention, having an indication of the character name, preferably early in the node naming, indicating which side, whether it's the center, left, or right on that character or prop, having a description of what that node is, in this case a pole vector for this particular limb, and then the number of that joint, in this case this is the first, and then we end with the type of node that it is, in this case locator, without any numbers on the end of that. So if we were to select this and duplicate it, we know instantly that we had a duplicate because it's added a number, in this case 1, to the end of that name. So we could just instantly look at it and know we had a duplicate, and then determine whether it needs to be renamed, because we prefer not to have duplicate node names, or if it's a mistake. So once again, pretty straightforward, but this simple naming convention, which I have used personally for quite a while, contains a lot of the elements that I think work for a naming convention, and it's pretty simple and straightforward. So that's basically what I'll be using throughout the tutorials. So to build a stretchy spline IK is actually quite simple. So here we have a typical spline IK. We have a hierarchy of joints, a curve or spline, which runs through the joints, and the deformation on this spline defines the rotation of each of these joints. And then we have the IK handle, which dictates the end position of this hierarchy of joints, or actually the end position of the spline, which in turn drives the joints. So in order to add squash and stretch to this, we actually need one piece of information, and that is the length of this spline. So we call this the arc length, and what that is it's the length, the U length and world space of this spline. So in this case, let's say this length is 10, just for example. So if the original length is 10, what we need to do is to determine, as this IK handle is transformed in space, it will actually stretch or reduce the size of the spline, which in turn changes the arc length of the spline. So what we need to do is we need to first record what the original arc length is, and then we need to scale each of these joints by whatever the end result of the new arc length of the deformed spline divided by the original arc length. So if we return to our previous example where I used an original arc length of 10, if we stretch the IK handle and deform the spline so that it now has an arc length of 20, twice its original length, we have an arc length value of 20 divided by 10, which is 2 over 1, so we'll scale each of our joints to 2. So here, our new arc length is twice the original length, and we're scaling our joints twice their original scale, a scale of 2, which will scale the joints so that their end matches the end of the IK handle. So that's how we set up a simple squash and stretch for a spline IK. Once again, pretty straightforward. So now let's go about actually building this. So in this lesson, we're going to build the base spline IK for this character. We're going to add several components to it later on, but in this lesson, we're just going to build the basic joints as well as the spline IK. The way we're going to do this is we're going to build, first I'm going to build a spline that I'll use as a visual guide for joint placement. That way I can work out the joint distribution and curvature using the spline by snapping the joints to the CVs of the spline. And then we'll go over all the options of the Spline IK tool and then build the Spline IK. So let's switch to a side view. I'm going to switch to template mode. And we're going to build a third degree curve so that we can edit the curvature of it and then rebuild it later on so that we can get an even distribution of CVs to snap our joints to. So we'll select Create, CV Curve tool, and option box. Make sure that the curve degree is set to cubic. And you can just loosely place 4 joints, or 4 CVs, excuse me. With the attribute editor, select Component Display and display the CVs of that spline. I'm going to switch to component mode and then do a little more editing for this spline. So here we're working out the curvature of the spine, and then we'll rebuild it in a moment so that we can get an even distribution of the CVs. Okay, so this is the curvature that we want. So select this and open the attribute editor. So you can see that we have a third degree curve with one span. What we're going to do is we're going to rebuild it so that we have basically 5 evenly distributed CVs that we can snap our joints to, because we'll eventually want 5 joints on the Spline IK. So with the spline selected, we'll switch to the modeling module and then select Edit Curves, Rebuild Curve in the option box. So we're going to leave our rebuild type on uniform, so we get a uniform distribution of CVs. We'll leave our parameter range to 0 to 1. And we're going to change our number of spans to 5, which equals the number of joints that we're eventually going to have. And we'll leave it as a degree of cubic, a third degree. Hit Rebuild. So there, ignoring the second and then the second to last CVs, you can see that we have evenly distributed CVs so that we can snap our 5 joints to. So we'll switch back to the animation module, select Skeleton, Joint Tool, and enabling the point snap. We'll just draw our 5 joints, once again skipping the second and second to last CVs. Okay, hit enter when you're done and disable your point snap. Let's open up our hypergraph. Okay, so we'll select all these joints and display their local rotation axes. Switch back to perspective mode. So with all the joints selected, we'll select Display, Component Display, Local Rotation Axes. Okay, so we're going to go in and start reorienting these. You want to make sure that we have a consistent orientation. In this case, our Y, we're going to rotate so that it points outward toward the side of the character, the left side of the character. But the first thing we're going to do is select the end joint and orient it so that it matches the orientation of its parent. We can do that by selecting the joint and selecting Skeleton, Orient Joint tool in the option box. Let's reset this. We want to change the orientation to none. And what that means is relative to its parent, it will have no orientation variance. So select that. So now you can see its orientation matches its parent. Let's quickly select and rename these before we go in and start orienting them. So select all the joints and then select Modify, Search and Replace Names. We're going to change joint, let's type that right, joint, in this case to cave 01, C, spine 0. We're going to add the suffix of underscore IK to each of these. Okay, let's rename this last joint. Okay, so with the joints renamed, now let's go in and start aligning all the local rotation axes. So we're going to switch to component mode and enable the question mark icon, which selects image planes, but more specifically for this task, local rotation axes. We'll go through and we'll select all of these, and we need to rotate this 90 degrees on the x-axis so that it will rotate the y-axis so that it points toward the left side of the character. So in the mail command line, we can type in rotate -r for relative, 90 on x, 0 on y, 0 on z. So you can see all of our y-axes are now pointing out toward the left side of our character. Now let's reorient our first joint local rotation axis by selecting it, and this time we're going to rotate it -90 degrees on x. So type rotate -r, -90 on x, 0 on y, and 0 on z. Okay, so now all of our local rotation axes are renamed. All of our joints are renamed and our local rotation axes are aligned. So now it's time to go in and create the spline IK. So let's select skeleton, spline IK handle tool, and option box. Let's talk about what some of these options are. So the first option is root on curve. What that means is it constrains the joints along the curve. So you will be able to activate a manipulator if you chose that option and slide this joint chain along the length of the spline. This next option, auto create root axis, it creates a parent transform node which can help orient the entire spline IK chain. We're going to use advanced twist control later on, so that's not an option we're going to use. The next option, auto create curve, or auto parent curve, I'm sorry, if the root joint is a child of a node, it will also parent that curve to the same node that's the parent of the root joint of this chain. The next option, snap curve to root. What this will do, if we were to draw our joint, let's say a curvature of, I'll just draw a joint real quick. So if we were to draw this joint and use it as a spline IK joint, what it would do, reactivate this spline IK option, with the snap curve to root, it would snap the curve to the root joint and then orient the joints to match the curvature of that spline. So the next option is auto create curve. What that will do is it will create a spline with a CV on each joint node. But if we were to select auto create curve and activate auto simplify curve, rather than creating a CV on each joint, it would create a CV where you would specify the number of spans of that CV. And it will be a 1 degree curve, so the number of spans equals degree 3 plus the number specified here. So for instance, if the number of spans were set to 1, it would be 3 plus 1, so we'd have 4 CVs along that curve. If it were 2, we'd have 5, and so on. The root twist mode allows for control of the twist of the root of this chain, the joint chain. But once again, we're going to use the advanced twist control, so that's not an option we're going to use. So instead, leaving this at default, we'll select the first joint and then select the second joint. Okay, you can delete this extra spline here. Open our hypergraph. So that spline IK tool has created 3 new nodes, one being the effector. What the effector is, it sort of acts as a goal or a target what it will do is it will always match its position, almost as if it's point constrained to the position of the spline IK. So wherever this end node is moved, the effector will match that position, and then inversely, or from the end of the chain backwards, figure out rotations it needs to apply to all these joints. Here's the IK handle, which is the end solution of the joint chain, and then the curve, which is actually how this spline IK is manipulated. We'll get into that a little later. Let's quickly rename these nodes. So rename the effector cave01 C spine 01 underscore EFF for effector. Rename the IK handle cave01 C spine 01 underscore IKH for IK handle. And rename the curve cave01 C spine 01 underscore CRV for curve. So we can select the first curve that we use to draw it and simply delete that. Okay, so let's select this spline and display the CVs on the curve. So display, NURBS components, CVs. Let's turn off all of our selection masks except for splines and switch to component mode. So the way a spline IK is actually manipulated is you do not manipulate it like a standard IK by selecting the IK handle. If you do that, you'll get a warning saying that this item can't be moved in a 3D view. Instead, with the spline IK, you affect the curvature of the chain of joints by manipulating the curvature of the spline that was created for the spline IK. So for instance, if I select the CV and translate it, we're changing the curvature of the spline, and all the joints are, in a sense, sort of constrained to a U position on that spline. And that's how you actually affect the curvature of the spline IK. So rather than manipulating the CVs directly, we're going to create a series of clusters. 3 to be precise. We're going to create a cluster on the first 2 set of joints that will comprise one cluster, a cluster for the center CV, and a cluster for the last 2 CVs. And here I meant a cluster on the first 2 CVs rather than joints, sorry. Okay, so let's select the first 2 CVs, select deform, create cluster, make sure it's set to relative. So we've created our first cluster. Select the third CV, hit G to create another cluster, reactivate the last used tool, and then select the last 2 CVs and hit G once again. Let's open up our hypergraph. You can see we have 3 new clusters, and these are what we'll use to allow the animator to manipulate the position and keyframe the spline IK. So let's quickly rename these. Let's select all 3. Open up Modify, Search and Replace Names. So we're going to change every instance of cluster to cave01 C spine 0, so we can leave that as is. Hit Apply. And with the cluster still selected, we're going to change every instance of handle to underscore CSR for cluster. Okay, so there we have created all the components for our spline IK spine. At this point, we're going to, in this lesson, but in subsequent lessons, we'll add secondary controllers, and then we'll add the squash and stretch to the joints of the spine by allowing them to scale to match the end position of the effector, or the IK handle rather. And then lastly, we're going to add the advanced twist control, which will allow us to distribute twist along the length of the joint chain. So although we have a fully functioning spline IK at this point, I'm going to replace the 3 clusters with 3 NURBS circles to control the spline IK deformations. What we'll get by doing this is we'll be able to place the pivot points of the start and end clusters directly at the pivot point of those joints, we'll also be able to match the orientation of those joints as well. Additionally, through group nodes, the transforms, the scale and translate for each of those controls will be 0. So once the spine is deformed, an animator will easily be able to reset it to its original position. And lastly, because the rotations will be all zeroed, we'll be able to set up the advanced twist control a lot more easily, something we'll do later on in this tutorial. So we'll start by creating the control objects. Create, NURBS primitive, circle, and option box. Now because the twist axis of the spine is X, I'm going to set X as the normal axis and leave all the other default options as they are. Hit create. I'm going to open up the hypergraph. We can see that we've created one NURB circle. So I'm going to hit the G key twice to create 2 more circles. So now we have our 3 control objects. Select them, quickly rename them. Okay, I'm going to add a suffix to them. In this case I'm using CTL for control, but once again you can use any suffix as long as it's consistent and works within your given pipeline. Now what I'm going to do is create a series of group nodes, which will be the parent of each of these controllers, and absorb all the transforms when we're repositioning them. So I can do that by hitting Control G or Apple G if you're using a Macintosh. Create empty group node. So those are 2 ways of doing that. For the center, I'm going to create a series of 2 group nodes. One which will be point constrained between the top and bottom control objects, and the second will be used as an offset. So I'm going to rename these. Okay, so I'm going to add a suffix to each of these using group. This I'm going to change to off for offset. Change this to spine 03. Okay, get rid of that one on the end. Now I'm going to parent the control objects to the appropriate group node. Now to position orient them, I'm going to select the group node, shift select the joint, and hit P to parent it. Next, I'm going to locate those group nodes in the spine hierarchy, select them, and set all of their translate and rotate transforms to 0. What this does, once again, is relative to its parent, it has 0 rotate and translate transforms. I'll unparent these. Now we can see that all of the transforms needed to position and orient these control objects are all placed on the group node, whereas the control objects themselves have clean transform values. At this point I'm going to display the local rotation axes on these control objects. And for these two, I'm going to set their X rotation to 0. So this way we can be assured that they have a consistent X, Y, and Z orientation. So now I'm going to constrain the group node of the center control object between the beginning and end control object. So select the 2 control objects, shift select the group of the center object and select constrain point to create a point constraint. Next, I'm going to select the offset group node and rotate it 90 degrees in Z. So now the orientation matches the relative orientation of the other control objects. So now I just need to position the offset node so that it lies right on top of this cluster. So to do that, with the offset node still selected, I'm going to select snap to points and snap that object onto the cluster. So now when we translate either of our two control objects, the position of the center object will be averaged between them. So now we're going to assign the clusters so that they are driven by these control objects. Rather than parenting the clusters to the control objects or constraining them, I'm going to simply replace the handles of the clusters with the control objects so that the control objects become the handles of the clusters. So to do this, you select the cluster and open the attribute editor. You click on the shape tab of that cluster and open up the weighted node box. Now here, for weighted node, this specifies the handle for that cluster. We just need to change the name to the name of the object that we're going to use to control the transformation of that cluster. So now if we select the cluster and transform it, it has no effect on the spine. But if we select the control object, which we've just specified as the weighted node or handle for that cluster, it drives the position and orientation of that cluster. Let's do it for the other two clusters now. Select the shape node, and then the last. At this point, you can actually select the clusters and delete them. One thing we want to make sure of is that the clusters are non-relative. You can see here the effect of having relative clusters. So simply select the control object and deselect relative. Now when we select our control objects, they move appropriately. So you can see we still have these cluster icons visible. Although this has no real effect on the deformations of the spine, it is somewhat of a visual nuisance. So once again, to have as clean a rig as possible, I'm going to hide the display of these objects. To do that, we're going to select the cluster shape, select the Object Display tab, and disable the visibility. Okay. So now we have control over the position of the controls, the clusters of this spline IK. We have no control over the twist along the entire length of this spine. So for that, we're going to use the Advanced Twist Control option on the spline IK. Now before we do so, let's make a visual note of the Y orientation of the joints of the actual spine and the Y orientation of the control objects. They're opposite or negative one another. So now we're going to set up the Advanced Twist Control. We're going to select the IK handle and open the Attribute Editor. Open the IK Solver Attributes tab, and then open the Advanced Twist Control tab underneath that. Now I'm going to enable the Advanced Twist Controls, and it will jumble all of our rotation axes on the joints. What we need to do at this point for world up type, we want to control the start and end of the spline IK using an object rotation, the control objects. So we'll select that object option. And the up axis, we noted earlier that the y-axis of the joints was negative or reverse the y-axis of the control objects. So we're going to select negative y for the up axis. Now we just need to specify the world up object, or the control object which we're using to control the twist. In this case, it's the beginning and end control object. So let's just input the names. There, we can see that the bottom axes are aligned, and we'll do it for the top. There. So now we can see when we select either one of these, when we rotate it on X, it distributes the rotation behind the little rotation axes of the controllers themselves. It distributes the rotation from the bottom almost all the way to the top, and vice versa, from the top almost all the way to the bottom. We have no control over the twist in the center. So now we have one last step. We have control over the position of the clusters, the orientation of the rotation distribution along the length of the spine. Now we need volume control. We need to be able to stretch and squash the spine. And that's relatively easy to do. Let's take a moment and I'll describe briefly the simple mathematics behind what we're doing here. Okay, so now let's add the squash and stretch to the spline IK. It's going to be fairly simple. We're going to use one multiply divide node, the arc length of the spline running through the length of the joints here, and then input values, and it should be fairly simple. So let's open up the script editor and start by creating the curve info node where we can get the arc length of this spline. We can do that by typing in arc length minus ch true, which is construction history, and then give it the name of the object we want to apply this command to. So once we execute this command, we see that a curve info node has been created. Open up the attribute editor, select the curve info node, and the main information we want from this is the arc length of that spline. Next, we're going to create a multiply divide node. Typing create node, multiply divide, specifying the type of node we're creating. I'm going to give it a -n flag where I can specify the name of the node, and then give it a naming convention appropriate to one we're using in our pipeline. And a -mdn, or multiply divide node suffix. I'll close this. Open up the connection area here, move it to the side. So there we have our multiply divide node. I'm going to load that into the inputs of the connection editor. Select the spline, select the curve info node, and load that curve info node into the outputs. I'm going to connect the arc length into the input X of the multiply divide node. Close that. So now when we select this node, we can see that the arc length has been connected into the input X. We're going to input that same number into the input 2X, and then open up the attribute editor and select the multiply divide node tab. Now we're going to change the operation type from multiply, the default, to divide. So what we're doing here is we're going to divide input 1 by input 2. So if this, for instance, were, let's say 9, let's round it out to 9, roughly twice this distance, it would be 2 over 1, or twice the length. And then we're going to take the result of this and input that into the scale X of each of the joints. Open up the connection editor once again. Load the multiply divide node. Another way to do this, if you don't have your multiply divide node selected, open up my hypergraph, select my spline, and click on my multiply divide node. Or I could select the multiply divide node explicitly in the script editor by typing select and then the name of the node. And so once again we can see why it's helpful to actually define the name of the nodes that you're creating. This way you can select them explicitly. So with that node selected, we're going to open the connection editor and load the multiply divide node into the output section and expand the outputs 1. Open up the script editor and clear everything out. I'm going to select the first joint, load that into the inputs of the connection editor, and then expand the scale channel. So I'm going to connect output X to scale X. You can see it's changed the color of the scale X, showing that there's a connection into that. And since both the input 1 and input 2 are identical, A divided by A is equal to 1, so we don't get any scaling value above or below 1. Now what I'm going to do is I could connect them manually, or you could also go through and copy and paste the commands from the output of the commands from the connection. We're going to go through and just connect them manually here. Select the multiply divide node. Expand the scale. Connect output X to scale X. And just move down the joints. If we were doing this with a mail script, we would capture the output of the first and then change the parameters to apply it in a loop to all the subsequent. Now you notice that I had initially connected the output of the multiply divide node into the scale X of the last joint, but I changed my mind and chose not to do that, and I'll show you in a moment why. So now you can see we have expansion and contraction. I'm going to open up the connection editor once again. Select the multiply divide node. And select the last joint and connect the scale value, the output X, into the scale value. So here we can see we get a much better control of the scaling in keeping with the beginning and end controls. One result is that if we move the center control, the end joint moves off the end controller. And this isn't something we typically want. So I compromise by selecting the last joint I'm going to break that connection. So now, although this is an artifact of Spline IK, especially the fewer joints you have, the more the end joint will offset from the end point. But by removing the scaling from that end joint, you can minimize it. We'll talk about this offset of the end joint once again later on when we talk about the ribbon or the stretchy FK spine as a way to alleviate that problem. So now we are effectively done with the stretchy spline IK with the advanced twist control. So now let's complete this rig by creating the spine and hip joints and then connecting them into the whole hierarchy here. Let's display our character. I'll keep it in template mode. I'm going to switch to a side view and draw the chest joints first. Select skeleton, joint tool, holding down V, point snap. I'm going to snap the first joint to the end joint of the Spline IK spine. Then I'll release point snap and then draw the two chest joints, ending more or less at the base of the neck. Hit enter. Let's rename these joints. Now the appropriate suffixes. Now let's check their local rotation axes. So the first thing we want to do is select the end joint and then select skeleton or hip joint. It's still set to none. I'm going to switch to, actually I'm going to hide the local rotation axes of the Spline IK spine. Switch to component mode, select the question mark to be able to select the local rotation axes component, and then shift select all of them. I'm going to rotate 90 degrees in Y so that X, so that the Y axis points out to the same side as the spine joint Y axis. So rotate -R 90 0 0 there. Hide those local rotation axes. So I would have two ways of parenting this into the hierarchy. I could simply parent it to the end controller, and then use the controller to move the chest into place. Or I could do the opposite of parenting the group node of the third controller to the first joint of the chest, and then using the chest to move the Spline IK. And that's the mode I'm going to go for here. Okay, so we're going to do go through a similar process with the pelvis joint. Reactivate our joint tool, switch back to object mode, point snap the first pelvis joint to the start of the Spline IK spine, deactivate the point snap, and then draw the end of the pelvis joint and hit enter. Display our local rotation axes. Hide our critter, and let's orient them. So we'll orient the last joint, switch to component mode, shift select both the local rotation axes. And in this case, I have two options. I'll show you both of them. The first, I'm going to rotate the y-axis so that they match the spine and the chest. So rotate -R It's negative 90, 0, 0. Do that again. Rotate minus R. Switch back to object mode. So I'm going to parent the beginning controller to this first joint. Select the joint, select the first chest joint, and I'm going to rotate them. We see they rotate in a similar fashion along the same axes. I'm going to want them to rotate opposite so that I get an easy contrapposal or compression of the chest and the pelvis. So I'm going to unparent, switch back to component mode, shift select the local rotation axes, and rotate them 180 degrees on X, rotating them to the opposite orientation. And hide the local rotation axes, and then rename these joints while I have them selected. Add the FK suffix. And reparent, and let's see what we got here. Select the first chest joint, switch back to object mode, select the pelvis. Now when I rotate, I get an easy compression or contrapposal. So at this point we have our spline IK completely constructed. Stretch, let me turn off the point snap. So we have stretch and twist control. So that's it for the stretchy spline IK, something many will already be familiar with, but I know earlier tutorials did not detail the advanced twist control. That's a feature that was added from some of the earlier tutorials. But it's a quick and easy way to get a distributed twist all the way up the length of the spline IK. And using the utility, the single utility node, I think it makes the compression, the squash and stretch, a lot more easy to set up rather than writing expressions which will contain information for each of the joints. And with the nodes, you get quicker evaluation. So the choice is yours, but this is the way I like doing it. So that ends this section, and we'll move on to the next. So before we move into building the ribbon spine, here I'm going to show an example of the differences between the spline IK spine and a ribbon spine. Both of these spines are comprised of 5 joints. This is a typical spline IK spine, where we have the ability to translate the top, the bottom, and the center of the spine. Then I've also set this up with the advanced twist control, so we can distribute the rotation down the length of our spine. And of course we have control in the center as well. So here's our ribbon spine. Have a similar thing. Control over the top. There's the bottom. Let's distribute rotation down the length. And we can translate the center as well. So now for the differences I wanted to point out in these two. So here we have 5 joints in our spline IK spine, which for a feature animated character is not all that unusual. We tend to build our spines in the studios that I've worked at with just a few joints in our spine, sometimes even less than this. So one thing I wanted to highlight is with this configuration, this looks fine. But unfortunately, with a low number of joints in a spline IK, sometimes when you translate your spine with the scaling expression or the node connection for the scaling, the end of the spline IK joint chain will move off the end of the actual spline. This isn't always a problem, but sometimes it can be something that will cause a problem or unwanted deformations in a rig. Slide this geometry here so we can see it a little better. So here on this, actually let's show that again. You can see this evidenced by the geometry actually translating up past the end controller. Whereas with the ribbon spine, it rotates, but there is no scaling involved in this type of rig, so we don't see any of the end joints moving past the end controller. Another difference is while we have the advanced twist control, so we can distribute rotation all the way from the top to the bottom and the bottom to the top, with the spline IK, although we can translate this middle controller, there's actually no rotation control whatsoever. Once you enable advanced twist control, that's all distributed from the top and bottom, and the center has no ability to affect the rotations in the middle of that spline IK spine. Whereas with the ribbon, not only can we translate our center about, we also have full rotational control over the center on any axis. And of course we still have the distribution of rotation from one end to the other. So they're both good rig constructions, and I show how to build both of these in these tutorials and lessons. But I just wanted to show the difference between the spline IK spine and the ribbon spine, and why in the end I'll choose to use the ribbon spine for our character. And I like the fact that no scaling is involved, so I don't have to worry about the end joint moving past the end controller or the actual spline. And also, animators like having the ability to have some rotational control in the center of the spine as well. In this lesson, we're going to build a ribbon spine for our character. It's an alternative to a stretchy spline IK, and they behave in quite similar manner. You can stretch or compress both of them, and you have translational control over the center as well as twists down the entire length of both spines. But there are a few differences and reasons why I prefer the ribbon spine over the stretchy spline IK spine. One reason being is not only do you have translational control over the center, but you also have full rotational control over the center of this spine rig configuration. Another advantage, or something that I like about the ribbon spine, is since there's no scaling on the joints in order to get the expansion and contraction on the spine rig, in some cases with a spline IK spine, when you're scaling along the X to scale the joints so that they match the end of the spline IK length, it'll actually stretch beyond the length of the spline that's driving the spline IK. So this is something that can be avoided entirely with this ribbon spine. Let's start by building this. Let's switch to template mode on this character. The first thing we're going to do is build the actual ribbon, which in this case will be a NURBS plane. We can do that by selecting Create, NURBS Primitives, Plane. Let's reset this. Now we want the flat face of our plane to face toward the front of our character, which is the Z-axis. So we're going to change our axis to Z. Leave our surface degree at 3 for a third degree surface. And then an important set of changes is we're going to change both the length and the V patches. Basically, we want to change both of these values to equal the number of joints that we're going to eventually attach to our ribbon. In this case, I'm going to build 5 joints. So I'll set both the length and the V patches to 5. If I were going to build a spine with 8 joints, for instance, I would have set them both to 8. Let's hit Create. Let's rename this NURBS plane to Cave 01 C ribbon 01, geo for geometry. Zoom in, we can hide our model now. Now let's display the CVs by selecting Display, NURBS Components, CVs, switching to wireframe mode. Let's select that, open the attribute editor. You can see we have one span in U, 5 spans in V, and they're both third degree surfaces. And we need the CVs, the third degree of the surface type, in the V direction, since that will define the profile of our spine, and we want to be able to deform that as much as possible. But for our U direction, we don't need to deform in that direction at all, so we can actually change the degree to 1. So we can do that by selecting the NURBS plane, switching to the modeling module, and then selecting Edit NURBS, Rebuild Surfaces, option box. Let's reset this again. So we're going to leave the rebuild type to uniform. The parameter range we're also going to leave at 0 to number of spans. The direction, rather than rebuilding both the U and V direction, we're only concerned with rebuilding the U direction. So we'll select the U option. For the number of spans in U, we're going to set this to 1, which is the current number of spans. And then degree U, we're going to change that to 1. Since we're only rebuilding the U, it ignores any options that we have set in the V parameters for the number of spans in the degree. So you can click on Rebuild. You can see that we have no extra CVs in the U direction, and we still have our third degree surface in V. We can open up our attribute editor to verify this. We still have our 1 in 5 span count, but a 1 degree surface in U and a third degree surface still in V. So we've created a rebuild surface input. So I'm going to delete history just to clean out this surface completely. The surface selected, edit, delete by type, history. So it deletes all the inputs. So now that we have our ribbon, we need to figure out a way to attach joints onto this surface so that it follows it regardless of how it's deformed. So we're going to use the follicle from the hair system for this. And this is typically used to attach a hair spline onto a deforming NURBS or polygonal surface. But in this case, we're going to delete all the hair components that we don't need and just keep the follicles, and then use that as a way of attaching our joints to the surface. So we'll select the NURBS plane, switch to the dynamics mode, and then select hair, create hair. Let's tear this off. Okay, so we're going to select create hair in the option box. Let's reset this. So I'm just going to change our output to NURBS curves. They're easy to deal with. Our U count we're going to set to 1, and our V count, which will define how many joints we're going to have attached to the surface, we're going to change to 5 in this case. Or you'll want to change that to however many joints you're going to want attached to your ribbon. Then we'll hit Create Hairs, open up our hypergraph, and see what we've created here. So we've created a hair system output curves, and then a group of follicles. The follicles are all that we're really interested in keeping here. So we're going to select the hair system as well as the output curves and delete them. So what we get with these follicles, let's select a few of the CVs on the NURBS surface. Let's transform these. So you can see our follicles stay attached to the surface. You can see the little red line here, which you'll probably be able to see better in your scene if you're working interactively. They also follow the normal of this surface. So follicle is actually a very handy tool for attaching something to a deforming NURBS or polygonal surface. At this point, let's start renaming our follicle nodes. Let's rename this group node to K01 C follicle underscore group. Let's select all of our follicles, and we're going to simplify the name here by deleting the 4 digits at the end and just changing this last token to follicle. So select modify, search and replace names. Let's reset this. So we're going to search for geo follicle and replace that simply with follicle. So not only are we going to remove the 4 digits, we're also going to change the numbering on the third token. So this will be changed to ribbon 02 follicle. Let's remove the last 4 digits. This will be ribbon 03 follicle, and so forth. Okay, rename the last one. Okay, so we have our 5 follicles. So now that we have a way of attaching an object to the surface, we're going to create 5 joint nodes by just selecting the joint tool, switch back to the animation module, skeleton joint. Rather than clicking 5 times, we're going to do that, but we're going to hit enter after each joint that we create. So we're going to click, hit enter, select Y to reactivate our last tool, click and enter, and then create all 5 of our joints this way. Okay, so with that done, let's open up our hypergraph, and by middle mouse dragging and dropping each of our joint nodes into a follicle, we'll parent each of them to a follicle node. Now to reposition these joints onto their parent, we'll select all of the joint nodes and then set their translate values to 0. So what that's saying is, relative to their parent, there's 0 translation offset, which pops them to the pivot point of their parent, in this case the follicle. So with the joints still selected, let's rename them. Modify, search and replace names. So we're going to search for joint and rename it to cave 01 C spine 0. We're going to add underscore JNT suffix, since we're actually going to use these joints to bind to our character. We're going to give them the JNT suffix. So all joints that I'm going to use to skin with this character, I'm going to name them underscore JNT. We'll also have 2 other types of joints. We'll have both FK and IK, but they'll just be used to drive JNT joints. So at this point we have many of the major components for our ribbon. We have the ribbon itself, we have the follicles, which are attached to the surface, and then a series of joints, which are children of those follicles. So now, with both translation and rotation, we can stick these joints onto our ribbon surface. Okay, so in the next section, we're going to build the controls to control both the squash and stretch, as well as the center deformations on this ribbon spine. So now that we've built the basic components of our ribbon spine, we need to build a system to drive the expansion and contraction of the spine, the top and bottom controllers, as well as the center controller. In order to do that, we're going to build a series of joints, one joint chain pointing downward, another pointing up, and they'll be aimed toward each other. And then we'll have a controller in the center that we can use to deform the middle of our spine. Let's switch to a front view and turn on our grid. So we're going to start by creating a set of joints pointing downward. I'm going to hold down X, which activates grid snap, and just click twice in the interface and hit enter. Let's open up our hypergraph and quickly rename these. Let's select them, modify, search and replace names. So we're going to call this spine top and give it an underscore FK suffix So we're not going to skin to these joints. Give that one a underscore end suffix. We activate our joint tool, holding down grid snap once again, create a pair of joints facing upwards, and rename these to spine bottom. So from spine top to spine BTTM, shorthand for bottom. Give them the FK and end suffixes. Then we're going to create one last single joint node. Rename that to Cave 01 C spine mid FK. So eventually we're going to use these joints to skin our ribbon. But first we need a way of changing their position as well as aiming each of these toward the other. So quickly I'm going to select the end joints and just for visual reasons change the translate X to 0.5. This isn't necessary, but just something I'm doing here to make it look pretty. So we're going to use a stack of locators, one to position each of these joints, another to aim toward another locator, and then for the center we're going to add another to offset that. And then we're also going to have up vector locators as well for each of the aim constraints. Let's open up our hypergraph. We're going to create 3 locators by selecting create locator, then hitting the G key twice to repeat the last tool selected. We're going to select the second and third locator, shift select the first and hit P or edit parent to parent the 2 locators to the first. Let's select them all and rename them. Okay, we're going to search for locator and change it to spine top. Okay, so we're going to give each of these a suffix that's descriptive to how they're going to be used. So for the first, we're going to give it an underscore POS suffix for a position change suffix. The second, we're going to change it to top 01 underscore aim suffix. We're going to use this as an aim constraint object. And the last one, top 01 up, since this will be an up vector object. Let's create another stack similar to this. Create locator. Hit the G key twice. Let's parent the second and third to the first, and then rename them. Change these to spine bottom, BTTM. Give them the same suffixes. This will be an underscore position, underscore aim, and underscore up. So we're going to create one more stack of locators, but in this case for the middle controller we're going to create a 4th locator which will be a child of the aim locator, and that will be used to offset that center joint. And so we'll give that an underscore OFF or offset suffix. So create joint and create locator, sorry. Hit the G key 3 times. Select the second and third locators, parent them to the first, just as with the other stacks here. Then select the 4th and parent it to what will eventually be the aim locator. Let's select them all and rename them to spine mid. Then give them the proper suffixes. So this will be mid underscore pause for position, mid 01 underscore aim. This 4th locator, mid 01 underscore off for offset, and the last mid 01 underscore up. So with each of the up vector locators, I'm going to select them and translate them a couple of units, 2 units out in X. And then to easily distinguish them, change their local scale to 0.5. Switch to a perspective view. You can hide the grid at this point. So for the top locator, we're going to hold down the V key for point snap, deactivate the grid snap, and just snap it up to the top joint. Then we're going to snap the second to the bottom. So the first thing we're going to do is we're going to point constrain the middle position locator to both the top and bottom position locators. What that will do is it will average its position between these two. So select the top and bottom pause locators, shift select the middle position locator last, and then select constrain, point. So now if we select one of these locators and translate it around, we can see that the middle locator will always average its position between them. So that's how we'll get our stretch and compression on our ribbon spine. So the next step will be to aim each of these aim locators to a corresponding pause locator. So we're going to start by aiming the spine bottom toward the spine top pause. So we'll select the spine top position locator first, which will be the object that will be aimed toward. Shift select the spine bottom aim locator, and then select constrain, aim, option box. Let's reset this quickly. I'll move this over here. So we can see that our aim vector is pointing up toward the object that it's going to aim toward. So we want our aim vector to be y rather than x. So we're going to change the weight on x to 0 and the weight on the aim vector of y to 1. Each of these channels represents x, y, and z. Likewise, we can see that our x is pointing out toward our up vector locator. So we're going to change our up vector to x and set the y weight to 0. Since we're going to use this locator to define the up vector, we're going to change the world up type from vector to object up. And once we make that change, we can see that our world up object text input field is now enabled, so we can specify the name of the object that we're going to use as an up vector. In this case, it's cave01 C spine bottom 01 up. Hit apply. And we're going to repeat the process with the top locator. The top aim locator will be aimed toward the spine bottom position locator. We need to select that in opposite order. The spine bottom pause locator first and the aim locator second. So we can see here that we could keep the settings as they are, changing the world up object to the top up locator. But instead I'm going to show that we can, and what that would do is if we leave it this way, it would flip so that the Y would point down toward the spine bottom position locator. But I'm going to show that we can actually maintain this orientation and still create an effective aim constraint by changing the aim vector to a -1 weight so that it points negative of how the Y is pointing now. Everything else we can leave the same except for the up vector object, which will change to spine top up. Then hit apply. We need to do this one more time, this time constraining the mid aim locator to the spine top. So here we can see our Y is pointing up, so we're going to change our aim vector back to a +1 in Y. Change our world up object to spine mid, and then hit add. Now if we select one of our top pause locator and translate it, you can see that they're all aiming toward each other. So we have compression and aim. At this point, I'm going to parent each of these joints to their corresponding locator to the aim locator, so the top FK joint to the spine top aim, the bottom joint to the bottom aim, and then the mid FK joint to the mid off or offset. And we're going to select each of these and set their translations to 0 to position them onto their parent. And then, because I created a ribbon with a length of 5 in V, right now we have a position of 2 and -2. If we unparent them, we can see this is set at 2. So we're going to add 0.5 to each of these. So we'll change this to 2.5 and this to -2.5 so that they'll be positioned at the end of the ribbons. Okay, so with that done, let's collapse this. Actually, let's template this. Display, object display template. We're going to smooth bind our ribbon geometry, our NURBS plane, to the top, bottom, and mid FK spine joints. So we'll select our ribbon geometry, and then shift select each of these joints, and then select skin, bind skin, smooth bind in the option box. Let's reset this. We want to select our bind to option to selected joints, the bind method, closest distance, our max influences. We can leave at 5 since we are specifying the exact joints that we'll bind to, the selected joints. You pretty much always want to disable maintain max influences. And then we'll set our drop off a little higher. We'll go 10. And hit bind skin. So now I'm going to switch to a side view. So now we can edit the profile of our ribbon by selecting our middle joint and translating it out, so you can see the curvature that we have with the profile. You know, nice even bell curve. Let's say, for instance, we want a more abrupt curve. We can get that by editing the smooth skin weights on the CVs associated with this NURBS plane. So I'm going to switch to component mode, select the CVs here, and then open our component editor by selecting Window, General Editors, Component Editor, and making sure that we have the Smooth Skins tab selected. So here we can see that 100% of the weight is assigned to the top FK joint. So we're going to change that so that 0.5 or 50% of the weight is now assigned to the spine mid joint. We're going to do the same with this pair of joints toward the bottom. Now you can see that you can edit these smooth skin weights and affect the profile curve that you'll get with your ribbon. You can edit it to how you see best fits the profile that you want here. Let's switch back to a perspective view. Now let's select our, turn on all the objects, select our spine top pause and translate it around. So you can see we have compression, we have them all aiming toward each other. We're lacking one thing here. We're lacking the ability to twist down the entire length of the ribbon. We can do that quite easily by point constraining the middle up vector locator to both the top and bottom up vector locators. So we'll select the top and bottom locators first, shift select the middle locator, and then select constrain point. So now when we select the spine top and rotate it, it's changing the position of the middle up vector locator, which then rotates the middle controller. And that's how we're going to get our twist down the length of the ribbon spine. We can see here that it's not quite even. We're not quite getting the even twist that we want here. So I'm going to switch to component mode. We're going to edit the smooth skin weights once again. So select the CVs, open up our component editor once again. Right now 100% of the weight is assigned to the middle FK joint. I'm going to assign 25% or 0.25 to our top joint, and do the same with this by assigning 0.25 to the bottom joint. And I'm also going to change the weight on the pair of CVs near the top here. Right now they're weighted 100% to the top spine joint. I'm going to give them a weight of, let's say, 0.2 to the middle joint. Use my arrow key to walk down the CV selection, and then change this and give it 0.2 weight to give it a more smooth fall off here so that we get a more even twist. Switch back to object mode, set our rotations back to 0. So at this point we have squash and stretch, twist down the length of the ribbon, and we can also select our joint in the center. You can translate it just as we can with the stretchy spline IK, but we also have full rotational control on all axes. That's one big advantage of the ribbon spine. Another advantage is when we squash and stretch it, our joints being attached to a U location on the nerve surface won't ever move beyond the beginning and end point of our rig, as they will with a stretchy spline IK. Okay, so with that we have all of our components for the ribbon spine. So now I'm going to create the sternum and clavicle for this character. One issue that we're going to have to deal with, this character has very broad shoulders. So I'm going to try something to help reduce or minimize the wide sweep and huge mass we can get if we have a single clavicle joint in that area. Okay, but let's start with the sternum joint. Switch to a side view here. Select the joint tool. I'm going to hold down point snap or V and snap the first joint, release it, and draw the second joint so that it ends roughly at the base of the neck. I'm going to select both joints and display their local rotation axes. Select the end joint and orient it so that it matches the parent, making sure that none orientation is selected. You have the caveman model. I'm going to switch to component mode and make sure that my local rotation axes component selection is toggled on. I'm going to shift select both local rotation axes of the sternum joint and rotate it 90 degrees in X so that the Y orientation matches that of the chest joints. Switch back to object mode and rename the sternum. First joint I'm going to give a suffix of FK. I'm actually going to skin to the end joint. So I'll give that a suffix of J and T. Okay, turn off our local rotation axes display. So at this point I could parent the sternum joint to the second chest joint, in which case when I select the chest joint I'll get a typical behavior where the child inherits all the transformations of the parent. But given the large chest of this character, what I'm going to do is set up a joint that will help dampen the rotation of the parent, averaging it in a sense. So to do that, I'm going to first start by creating a duplicate of the chest joint. Well, first I'm going to start by unparenting sternum. Then I'm going to duplicate the chest joint. Delete the end joint of the duplicate and rename this by giving it a suffix of AVG for average. I'm going to parent the sternum to this new average joint, then parent the average joint to the chest. So once again, we still have the same parent-child relationship. Close this. So what I'm going to do is I want to take a portion of the rotation of this joint. For instance, I'm going to rotate it to 40 degrees in Y. And in the average joint, I want to dampen that rotation. In this case, I'm taking negative 0.5 of the Y rotation. So once I set this up with the multiply divide node, it'll become much more clear what I'm trying to do here. Okay, I'm going to open up my script editor and type in create node with capital N, multiply divide with capital D, minus N flag, and then give this node a name. MDN is my suffix choice for multiply divide node. So what I'm doing here is I'm creating a multiply divide node and then giving it a name. Select that, hit enter, and we can see we've created that node. I'm going to select display general editor or window general editors connection editor and click load into inputs, and I've loaded in my multiply divide node into the inputs channel. I'm going to select my chest joint and load that into the output side of the connection editor. So at this point what I'm going to do is I'm going to connect the rotations, the output of the rotations of the chest 2 joint into the inputs 1 of our multiply divide node. So whatever rotations occur on the chest joint, I'll feed those values into the first input of the multiply divide node. I'm going to select the multiply divide node once again in the channel box, load that into the outputs, scroll up toward the top. I'm going to step up and select our average joint and load that into the input section of the connection editor. So now whatever outputs occur on the multiply divide node, I'm going to direct that into the rotation channel of the averaging joint. So now we can see we have a connection to the rotate channels. So I'm going to select the multiply divide node and open up the attribute editor. We can see that the operation is set to multiply, which is the default. And this so happens to be the operation that we're going to use in this example. But I'll open up this drop-down menu to show you that we have two other options available to us. Divide, which will divide input 1 by the value that we place into the input 2's, and then there's power, which is an exponent. We'll leave it on multiply. So to adjust this, I'm going to select the chest 2 joint, rotate it 40 degrees in Y. So we can see what's happening here is the averaging joint seems to be getting double the rotation of its parent, which makes sense when you think about it. It's getting 40 degrees rotation from the parent by the fact that it's a child of the chest 2 joint. It's also getting 40 degrees rotation because I'm taking the rotation value of the chest 2 joint and putting it into the multiply divide node, and the output of that is going into the average joint. So at this point I'm going to open up the multiply divide node in the channel box, select all the input 2 channels, and type in -0.5. What this does is it takes the rotation value of the chest joint, multiplies it by 0.05, in effect reversing it by half the rotation, and then taking that end value and inputting it into the chest average joint. The effect is that this dampens the rotation of its parent, which will help us control the volume of that massive chest. So now that we have our sternum constructed, I'm going to create the left and right clavicles. I'm going to use a 1-degree curve, drawing it from the base of the sternum to the mid base of the deltoids, or shoulders, as a visual guide. Create curve tool, option box, still set on linear. Holding down point snap, I'm going to snap the first CV to the end of the sternum, and then point snap the last CV to the base of the deltoid, or shoulder joint. Switch to template mode. Open up the attribute editor, open up the component display tab, and click on display CVs, which will toggle on the CVs for this selected spline. So before I draw my joint using the spline as a guide, Maya sometimes, when we mirror across the weights, smooth skin weights across from the left or right or vice versa, if both target joints, if their origin lies directly on the center of the character, the center line of the character, sometimes Maya doesn't mirror those weights properly. So what I'm going to do is switch to component mode, select the NCV and step up 1, and shift it out just slightly from the center to help alleviate this problem. And that should do it. So now I'm going to activate the joint tool and point snap to the beginning and end of the spline to create our clavicle joint. Hit enter. Select the joints. Once again, display their local rotation axes. Select the end joint and orient it to match its parent. So now visually I'm going to change the orientation of this clavicle so that it matches the orientation of the palm. So currently the clavicle is set up to rotate almost straight out. What I'd like it to do is to rotate at an angle matching the angle of the palm. So to do that, I'm going to switch to component mode, select both the local rotation axes, and manually rotate this so that it matches the rotation roughly of the palm. You could do it far more precisely using an aim constraint and an up vector object, which we'll do later on when building the arms. But in this case, doing it a visual alignment should suffice. Switch back to object mode and rotate it to test it. Okay. Oh, excuse me, I accidentally turned off my help line. There we go. So one thing I want to check is when I rotate forward, I want to have a positive rotate Y. Okay, I'm going to name this clavicle joint. Name the end. I'm going to mirror this over to the right side. Mirror joint. I'm going to mirror, searching for _L_, replace it with R, and mirror it across the YZ plane, which cuts down the center of the character. So now we have our right clavicle. So earlier I spoke about the width of the shoulders, and the visual problem I'll have that if I were to rotate the shoulders out by this amount, it will create a huge volume. So one thing I'm going to try to do is to distribute the clavicle rotations over multiple joints. Let's give that a try here. I'm going to select that guide spline and rebuild it so that it has 4 CVs along its length. Switch to modeling mode, edit curves, rebuild curve option box, and change this to 0 to number of spans, leave the number of spans to 4, and change the degree to linear, which is the degree that the curve is at now. Hit rebuild. We've created 3 joints in the center of this spline, and I'm going to use those to point snap additional joint nodes to. So to create those additional joint nodes, I'm going to select the clavicle joint and simply duplicate it. Okay, so I've duplicated it once. I'm going to delete that and hit Control D to duplicate it 2 more times. So I'm going to rename these joints, renaming this Clav 2 JNT, Clav 3 JNT, get rid of that extra underscore, and then Clav 4. I'm going to select each of these and simply point snap them onto the corresponding CV of the rebuilt curve. Holding down V and point snapping. I'm going to parent them all together. I'm going to take that Clav 5 end joint and parent it to 4. And just parent them all the way up the chain. Select each of them, make sure that their rotates are 0, that nothing odd happened. Hide the local rotation axes. So now I've multi-selected all of the left clavicle joint and the single right clavicle joint. Do a simple rotation. So for instance, if I were to rotate this out 30 degrees, select the right clavicle and switch to a side view, just manually rotate it so that it roughly matches the forward sweep of the left clavicle. We can see that while this will distribute those rotations over multiple joints, bringing the shoulder as far forward as the right clavicle, but end more, visually reducing the mass of that shoulder versus the huge mass that we'll have over on the right side. The good thing about having the distributed clavicle, as we have on the left, is if I wanted this appearance, I could simply set these to 0 and rotate only the first joint. But flexibility is the name of the game in feature animation, so it's better to have the flexibility to distribute or not than to not have that option at all. So I'm going to delete the right clavicle, select the left side clavicle, and mirror that joint over to the right side. Switching to animation mode, skeleton, mirror joint tool. Options are still the same here. There it's mirrored. I'm going to parent our 2 clavicle chains to the end of the sternum joint. Okay, there. We've completed our sternum and clavicle, and next we'll move on to the scapula. So in this lesson we're going to tackle building the autoclavicle for this character. What that means is if we swing our arms forward or back or up, the clavicles will also rotate in the same directions. Now, since we have both an FK and IK arm in this character, we're going to essentially need to build a way to drive the auto clavicle regardless of it being in FK or IK mode. And then we're going to use a condition node to switch between which rotation values to drive the auto clavicle joint with. So first we're going to start by building the IK clavicle follow joint. Let's open up our hypergraph. The first thing we're going to do is we're going to duplicate the first joint of the multi-clavicle. So select that joint, hit edit, duplicate. We can delete all but the first joint. Let's zoom in and rename this to clav follow 01 IK. Then let's duplicate that joint, rename it to clav follow 02 IK, and then reposition the second clavicle follow joint to the end of the IK arm by holding down V for point snap and just snapping it to the end of the arm. Now we can parent this second joint to the first. Now what we're going to do is we're going to create an IK handle for this new joint here. So let's select all of these clavicle, scapula, and arm joints and temporarily hide them. Then activate our IK handle tool by selecting skeleton, IK handle tool, and option box. We want to make sure we have it set to a rotate plane solver. That way we can avoid any flipping if we rotate our character. Let's zoom in here, select the first IK follow joint, and select the end. Let's rename our new IK handle to cave01 L clav follow 01 IKH. Open our hypergraph, rename our effector cave01 L clav follow 01 EFF. So now we need to create a pole vector constraint for this object. So I'm going to create a locator here and then rename it cave01 L clav follow PV for pole vector 01 locator. So first I'm going to point and orient constrain it to our first clav follow IK joint. Constrain point, constrain orient, and delete these. So it's matching the orientation of the arm, and if we select our IK handle, we can see that our pole, it seems to be oriented in the same direction. Let's translate it back here. So right now, of course, we have no rotations on our clav follow joint. So we're going to select the locators, shift select the IK handle, and then select constrain pole vector. And you'll notice in your scene that there's a slight shift, and if we select our clav follow joint, we have rotate values on all of the axes. Let's undo that. So we're going to figure out a way to create a pole vector constraint that won't introduce any of this subtle shifting. So we're going to create another joint, or another locator, I'm sorry, parent that to the clav follow joint. Let's rename this up. So we have these two locators right on top of each other. Once again, we're going to point and orient constrain the pole vector locator to the first clav follow IK joint. So select that joint, shift select the locator, then select constrain point, and then constrain orient. We can delete these two constraint nodes. So the up locator, let's select it and then translate it down in Y, then unparent it. So now what we're going to do is we're going to aim constrain our locator to the clavicle using this up locator as an up vector. Let's select our IK handle, shift select our pole vector locator, and then select constrain, aim. Let's reset this. So we want to aim our y-axis, so we'll leave that, and our up vector will be, we want to aim our x-axis, and our up vector will be y, so we'll leave it at default values. We're going to change the world up type to an object up, and then specify the name of the up object. In this case, it's simply up, the name of the locator. Then we'll hit add. We can delete this aim constraint node. Now let's translate this locator back in Z. So now when we create our pole vector constraint, locator selected, shift select the IK handle, and then constrain pole vector. If we select our clav follow joint, there are no rotations. So that's one way of creating, using an aim constraint with an up vector, way of creating a pole vector constraint that won't introduce any minute shifting in your IK handle. Okay, so with that done, we can delete this up locator. Just unhide all of our joints here, rebuild our hypergraph. So now I'm going to point constrain our clav follow IK handle to our arm IK handle. So I'm going to select the arm IK handle, shift select the clav follow IK handle, then select constrain point. Okay, so now when I select the IK handle and translate it, our clav follow IK handle will follow it because the IK handle is point constrained to the arm. So now we're going to create the auto clavicle joint by once again selecting the first joint of the multi-joint clavicle and then selecting edit, duplicate. Let's open up our hypergraph and frame that. Once again, we can delete all but the first joint. We're going to rename this from clav01 joint to autoclav01 FK. So now we have all the components that we need for our FK and IK autoclavicle. What we're going to do is we're going to use the rotations from our FK arm joint, but we're going to need to invert them. If we look at those rotation values, those local rotation axes, we can see that the Y and Z are opposite those of the autoclavicle, as well as the clav follow IK. So we're going to need to negate these by multiplying them by -1, and we're going to use the multiply divide node to do that. So in our script editor, we're going to type create node multiply divide -n for name. We're going to call it cave01 L clav follow FK underscore MD for multiply divide. Select that, hit enter. Let's open up our connection editor and load our multiply divide node into that inputs window. Expand this. So now we're going to select our L-arm FK joint, load that into the outputs of the connection editor. Scroll down to the rotate channels, expand that. We're only concerned with the rotate Y and Z. We're not concerned with the axial or lengthwise rotations, the x-axis on any of these. So we're going to connect our rotate Y to the input 1Y, the multiply divide node. Do the same with the Z. Then we're going to click on our multiply divide node in the channel box and set our input 2Ys to -1. So the Y and Z rotates, which are connected into the input 1 Y and Z, will be negated or inverted by being multiplied by -1. So now we need to create a condition node so that we can switch between the FK, the inverted FK rotations, or the clav follow IK rotations. So we're going to type create node, condition, let's give it a -n flag and name this cave01 L clav follow C and D for condition. Select that and hit enter. So with our condition node selected, what we're going to do is we're going to test to see which mode the arm is in. In this case, we're going to test to see whether it's in FK mode or not. So we're going to connect the weight of the first orient constraint on our J&T arm to see if the FK orient constraint weight is set to 1. And if it is, then we're going to see if that 1 is greater than the second term, which we'll leave at 0. Then we'll output the values of the inverted FK arm joint. Otherwise, we'll output the values of the clav follow IK joints, and both of those will feed into the autoclavicle joint. Let's open up our attribute editor. We'll change our operation on the condition node from equal to greater than. With that node still selected, we're going to load it into the connection editor, to the inputs. Okay, so let's find our first orient constraint, the J&T arm joint. Load that into the outputs and scroll to the bottom. And then connect the FK weight of that orient constraint to the first term. And so if that first term is true, if we're in FK mode, we're going to connect the inverted FK joint rotate value. So we're going to select the multiply divide node and load that into the outputs. Scroll to the top. Then connect the output Y to the color of true G and the output Z to color of true B. Otherwise, if we're in FK mode, then we're going to output the rotate values of the clav follow FK. So let's load that into the outputs. The connection editor. Expand the rotate channels. And connect the rotate Y to the color of false G. And then rotate Z to the color of false B. And lastly, select our condition node in the channel box. Load that into the outputs of the connection editor. Scroll to the top and expand the out color. And let's find our autoclavicle joint and load that into the inputs. Let's find the rotate channel, connect the out color G to the rotate Y and the out color B to rotate Z. Okay, so the last step is just drag selecting over all of our clavicle and scapula joints. Shift selecting the autoclavicle FK, hitting parent to parent them. Okay, so now if I select the orient constraint, we can see we're in FK mode. So if I select the arm IK handle and translate it, the clavicle is following. If I switch the weight of the orient constraint to 1, so that we're in FK mode, and I select the first FK arm joint and rotate this, and the clavicle is following the FK joint. That's how we're going to use the condition node to switch between the two. Let's switch back to IK. Now the last step is to parent all of our arm joints, the J&T, the FK, and the IK. We need to parent these to our scapula pos locator. So select the 3 joints, shift select the scapula pos locator last, and then hit the P key to parent them. So now we have our autoclavicle, which can switch between FK and IK mode. And in the next lesson, we're going to build a switch for it, or an override, so that the animator can dial in a percentage of this autoclavicle rotation or turn it off completely. So now we're almost done with our autoclavicle. One last step is adding in a controller for the animators so they can dial in the influence of the autoclavicle from 0 to 1 or 0 to 100%. We always want to give the animator the option to override these automatic controls that we put in. The way we're going to do this is we're going to use a multiply divide node and then connect it to an attribute, which will be a float value from 0 to 1. Let's start by creating our multiply divide node. Give it a name. Okay, so let's create this node. Let's load it into our connection editor, of course. And then we're going to connect the condition node, the output of the condition node, into the inputs of this multiply divide node. We're going to do this selectively because actually we'll want positive and negative Y rotations, positive or upward Z rotations, but no X rotations on the clavicle. So I'll connect the out color G to input Y and the out color B to input Z. Now we need an attribute added to our first clavicle joint here, which we'll use as the input for the input 2, and this will be the animator control to dial in and out of the autoclavicle. So with that first clavicle joint selected, I'm going to select Channels, Add Attribute. We'll name our attribute in the attribute name field. We'll call this clavicle follow. Once again, the capital letter or camel case defines a second word in the channel box. We'll leave it as a float data type. We'll set our minimum value to 0, the maximum to 1, which will be 100%, and we'll set our default to 0. So with that created, we'll load that into the outputs, scroll to the bottom where we have our new attribute, and we're going to connect this to the input 2Y and input 2Z. So the last step will be taking this multiply divide node, select it, let's load it into our outputs, and then let's select our clav auto joint. Let's load that into our inputs and scroll down to the rotate channels. So we're going to break these connections, which are being connected to the condition node, and then selectively connect them to our multiply divide node. Connect the out Y to the rotate Y and the out Z to the rotate Z. Let's test this. We're going to rotate and nothing's happening. That's because our autoclav is set to 0. So let's dial that up to 0.5. There we have our autoclavicle. Let's take this from 0.5. You can see we can dial it in and out from 0 to 1. Take this back to 0. So now we need to do one thing. We can see that the forward and back rotations are fine. But for the up and down, we want to allow for the autoclavicle to rotate upward, but the clavicle is actually restricted in its downward rotation, which we'll assume that an animator will be aware of, but the autoclavicle is just doing what it's told by being driven by the rotate channels of the autoclav joint. So what we need to do is we can see that the downward rotations, which will be inhibited by a rib cage anatomically, are in the negative Z rotations. So we'll set this to 0. Select our Clav Auto joint and open up our attribute editor. We'll scroll down to the limit information. Now rotate Z with 0 as the current value. We're going to click on the left arrow which loads the current value into the minimum field. And then we'll enable the rotate limit for the minimum. Now we'll reselect our arm FK, rotate up, it's fine. And then it stops when it hits the top of the rib cage. Okay, so with that we're done with our auto clavicle. So let's begin building the scapula for our character. We'll start by drawing a NURBS curve. I want a little guidance here in the placement. So I'm going to turn on point snap. Click the first joint, first CV, then the second. Open up my attribute editor, select component display, and display CVs. I'm going to switch to component mode and select the NCV and reposition it on this surface. I'm going to switch to a side view here. And what I want is more or less just a straight line. It doesn't have to be exact, just approximating at this point. We hide our geometry, create skeleton joint tool, enable point snap once again, and create our scapula joint. I'm going to display the local rotation axes. I'm burning through this part pretty quickly. It's fairly simple. I'm going to orient the last joint to none so that it matches its parent's orientation. Get rid of that curve, select, and rename our joints. Change every instance of joint. And add FK as the suffix. At this point, I'm going to switch back to the side view. Then in component mode and enable the local rotation axes component selection. I'm going to shift select both the local rotation axes of our new scapula joint. Hit the rotate tool. And then rotate to roughly match the orientation of the back. This isn't a joint that the animator is likely to actively manipulate, so this orientation process isn't as important. But it's a good habit to edit these with all joints created. So there we have our scapula. Now quickly I'm going to parent our scapula joint to the end of our clavicle. With our character still templated, I'm going to select the clavicle and rotate our joints. So we can see when we rotate it forward what the scapula would do to the back. It's sort of fighting against what we've done by splitting the clavicle into multiple joints. I mean, the back geometry, that skin to the scapula, which will be most of the upper back, will take a very broad sweep. So we need to deal with that. I'm going to unparent. So the first step we're going to do is What our problem is in the back direction. Let's do this once again. And we rotate back, because he has a fairly limited range of motion, you have to simulate his clavicle hitting up against the rib cage, and also just the physical mass. He can only rotate his arms back so far. Let's say the animator goes back a little further. That's not too bad. The problem arises when he rotates the clavicle forward. So we need to figure out a system where we can more or less leave the scapula as is when it comes to inheriting the rotations, the cumulative rotations of the clavicle, but somehow dampening or limiting that rotation inheritance when the clavicle moves forward. So how I'm going to do that is a method that we're going to use later on. So let's begin building the scapula for our character. We'll start by drawing a NURBS curve. I want a little guidance here in the placement. So I'm going to turn on point snap. Click the first joint, first CV, then the second. Put up my attribute editor, select component display, and display CVs. I'm going to switch to component mode and select the NCV and reposition it on this surface. I'm going to switch to a side view here. And what I want is more or less just a straight line. It doesn't have to be exact, just approximating at this point. We hide our geometry, create skeleton joint tool, enable point snap once again, and create our scapula joint. I'm going to display the local rotation axes. I'm burning through this part pretty quickly. It's fairly simple. I'm going to orient the last joint to none so that it matches its parent's orientation. Get rid of that curve, select, and rename our joints. Change every instance of joint. And add FK as the suffix. At this point, I'm going to switch back to the side view. Then in component mode and enable the local rotation axes component selection. I'm going to shift select both the local rotation axes of our new scapula joint. Hit the rotate tool. And then rotate to roughly match the orientation of the back. This isn't a joint that the animator is likely to actively manipulate, so this orientation process isn't as important. But it's a good habit to edit these with all joints created. So there we have our scapula. Now quickly I'm going to parent our scapula joint to the end of our clavicle. With our character still templated, I'm going to select the clavicle and rotate our joints. So we can see when we rotate it forward what the scapula would do to the back. It's sort of fighting against what we've done by splitting the clavicle into multiple joints. I mean, the back geometry, that skin to the scapula, which will be most of the upper back, will take a very broad sweep. So we need to deal with that. I'm going to unparent. So the first step we're going to do is what our problem is in the back direction. Let's do this once again. And we rotate back, because he has a fairly limited range of motion, you have to simulate his clavicle hitting up against the rib cage, and also just the physical mass. He can only rotate his arms back so far. Let's say the animator goes back a little further. That's not too bad. The problem arises when he rotates the clavicle forward. So we need to figure out a system where we can more or less leave the scapula as is when it comes to inheriting the rotations, the cumulative rotations of the clavicle, but somehow dampening or limiting that rotation inheritance when the clavicle moves forward. So how I'm going to do that is a method that we're going to use later on when we're setting up the auto clavicle, where the clavicle will automatically follow the arm position later on. So this will give you a teaser of that. So with that in mind, let's go ahead and set up this system for automatically controlling the rotation or the inheritance of rotation of the scapula from the clavicle in either direction. Okay, so the first step of setting up this clavicle will involve creating a rigging system that will allow us to control the sweep of the scapula so that it basically mimics the curvature of a rib cage. Let me hide this grid. I'm going to start by mirroring this joint. So we have a right side scapula joint. So really quickly, I'm going to parent this right side joint to have a source of comparison. Then we're going to create a series of locators to control the position and orientation of this scapula joint. So I'm going to start by creating 4 locators. Open up our hypergraph. And the first 2 locators, I'm going to make a child of the first. I'm going to select them all and rename them. So every instance of locator I'm going to change the end number and suffix to give me a more clear indication of what I'm going to use these locators for. So in this instance, I'm going to control the position with the first locator. So I'll change that suffix to pos. This one I'm going to aim. And this third I'll use as an up vector. And lastly, I'll rename this. This is the target. Okay, so I'll quickly create a positional constraint and move the entire hierarchy up to the end of the original clavicle. I'm going to select the up vector locator using the local scale attribute, change its size so that it's easily to distinguish from the others, and translate it up a couple of units. Lastly, the next step, I'm going to point and orient constrain the target locator to the sternum joint. Now the final step in setting this structure up, so I'm going to aim constrain the aim locator at the target. So I'll do that once again by selecting the target, shift selecting the aim locator, opening the constrain aim with the option box. So here, let's see here. Okay, so I'm going to want to use x as my aim vector, so I'll leave that at 1. Y is already pointing up, so I'll use that as my up vector, and these are all the default settings. But we're going to change the world up type so that we'll use this up vector locator, meaning we'll need to change this to object up. Then we input the name of the up vector locator, and then apply. So at this point I'm going to open up my time slider. I'm doing this by right mouse clicking on this sidebar. It will bring up a menu of UI items that I can have access to. So I'll open the time slider. I'm going to set a quick forward and back animation on this clavicle so that I have a test range of motion. Since I know I'm going to do this often, I'll just set it up now so that I can just scrub through the timeline and not have to continually select the joints and rotate them forward and back. Okay, so there we have forward and back. So if I select the aim locator, you can see it's always aiming toward this target on the sternum. Then I'm going to parent our left scapula joint to this. We set a range of motion for this, once again as a point of comparison. Just quickly, -10. It's moving forward 30 degrees. Okay, so now when we compare them, in the back motion, even though the scapula are passing just beyond, or well beyond actually, the center line, you can see that the left scapula, using the aim constraint structure, keeps a little better curvature with, the back, mimicking a rib cage that we'll be following. Also, since these two joints will be controlling a large number of the upper back verts, their orientation is important. So in this case, those verts will be more or less pushed straight in, maintaining a solid form. And ideally an animator will push them to this point, not having the scapula pass beyond one another, which isn't possible, but you never know in feature animation. Whereas with this, it will start angling the vertices inward into the rib cage, which we don't want. But then we see in the forward, this is terrible. It would cause it would result in a huge deformation in the upper back. Whereas this, it will cause a shearing, and I know this just from experience, having already rigged and skinned this character. So once again, as we said, we're more or less content with the back motion, the clavicles angling backwards. But forwards, we need to somehow dampen or limit that. So I'm going to select this joint and unparent it. And now we're going to go about setting up a mechanism to control the forward and back inheritance of rotation of the scapula. So let's begin building the scapula for our character. We'll start by drawing a NURBS curve. I want a little guidance here in the placement. So I'm going to turn on point snap. Click the first joint, first CV, then the second. Open up my attribute editor, select component display, and display CVs. I'm going to switch to component mode and select the NCV and reposition it on this surface. I'm going to switch to a side view here. And what I want is more or less just a straight line. And it doesn't have to be exact, just approximating at this point. We hide our geometry, create skeleton joint tool, enable point snap once again, and create our scapula joint. I'm going to display the local rotation axes. I'm burning through this part pretty quickly. It's fairly simple. I'm going to orient the last joint to none so that it matches its parent's orientation. Get rid of that curve, select, and rename our joints. Change every instance of joint. And add FK as the suffix. At this point, I'm going to switch back to the side view. Then in component mode and enable the local rotation axes component selection. I'm going to shift select both the local rotation axes of our new scapula joint. Hit the rotate tool. And then rotate to roughly match the orientation of the back. This isn't a joint that where the animator is likely to actively manipulate, so this orientation process isn't as important. But it's a good habit to edit these with all joints created. So there we have our scapula. Now quickly I'm going to parent our scapula joint to the end of our clavicle. With our character still templated, I'm going to select the clavicle and rotate our joints. So we can see when we rotate it forward what the scapula would do to the back. It's sort of fighting against what we've done by splitting the clavicle into multiple joints. I mean, the back geometry, that skin to the scapula, which will be most of the upper back, will take a very broad sweep. So we need to deal with that. I'm going to unparent. So the first step we're going to do is what our problem is in the back direction. Let's do this once again. And we rotate back, because he has a fairly limited range of motion, you have to simulate his clavicle hitting up against a rib cage, and also just the physical mass. He can only rotate his arms back so far. Let's say the animator goes back a little further. That's not too bad. The problem arises when he rotates the clavicle forward. So we need to figure out a system where we can more or less leave the scapula as is when it comes to inheriting the rotations, the cumulative rotations of the clavicle, but somehow dampening or limiting that rotation inheritance when the clavicle moves forward. So how I'm going to do that is a method that we're going to use later on when we're setting up the auto clavicle, where the clavicle will automatically follow the arm position later on. So this will give you a teaser of that. So with that in mind, let's go ahead and set up this system for automatically controlling the rotation or the inheritance of rotation of the scapula and the clavicle in either direction. Okay, so the first step of setting up this clavicle will involve creating a rigging system that will allow us to control the sweep of the scapula so that it basically mimics the curvature of a rib cage. Let me hide this grid. I'm going to start by mirroring this joint. So we have a right side scapula joint. So really quickly I'm going to parent this right side joint to have a source of comparison. Then we're going to create a series of locators to control the position and orientation of this scapula joint. So I'm going to start by creating 4 locators. Open up our hypergraph. And the first 2 locators, I'm going to make a child of the first. I'm going to select them all and rename them. So every instance of locator So I'm going to change the end number and suffix to give me a more clear indication of what I'm going to use these locators for. So in this instance, I'm going to control the position with the first locator. So I'll change that suffix to pos. This one I'm going to aim. And this third I'll use as an up vector. And lastly, I'll rename this. This is the target. Okay, so I'll quickly create a positional constraint and move the entire hierarchy up to the end of the original clavicle. I'm going to select the up vector locator using the local scale attribute, change its size so that it's easily to distinguish from the others, and translate it up a couple of units. Lastly, the next step, I'm going to point and orient constrain the target locator to the sternum joint. Now the final step in setting this structure up, so I'm going to aim constrain the aim locator at the target. So I'll do that once again by selecting the target, shift selecting the aim locator, opening the constrain aim with the option box. So here, let's see here, okay, so I'm going to want to use X as my aim vector, so I'll leave that at 1. Y is already pointing up, so I'll use that as my up vector, and these are all the default settings. But we're going to change the world up type so that we'll use this up vector locator, meaning we'll need to change this to object up. Then we input the name of the up vector locator, and then apply. So at this point I'm going to open up my time slider. I'm doing this by right mouse clicking on this sidebar. It will bring up a menu of UI items that I can have access to. So I'll open the time slider. I'm going to set a quick forward and back animation on this clavicle so that I have a test range of motion. Since I know I'm going to do this often, I'll just set it up now so that I can just scrub through the timeline and not have to continually select the joints and rotate them forward and back. Okay, so there we have forward and back. So if I select the aim locator, you can see it's always aiming toward this target on the sternum. Then I'm going to parent our left scapula joint to this. We set a range of motion for this, once again as a point of comparison. Just quickly, -10. It's moving forward 30 degrees. Okay, so now when we compare them, in the back motion, even though the scapula are passing just beyond, or well beyond actually, the center line, you can see that the left scapula, using the aim constraint structure, keeps a little better curvature with, the back, mimicking a rib cage that we'll be following. Also, since these two joints will be controlling a large number of the upper back verts, their orientation is important. So in this case, those verts will be more or less pushed straight in, maintaining a solid form. And ideally an animator will push them to this point, not having the scapula pass beyond one another, which isn't possible, but you never know in feature animation. Whereas with this, it will start angling the vertices inward into the rib cage, which we don't want. But then we see in the forward, this is terrible. It would cause it would result in a huge deformation in the upper back. Whereas this, it will cause a shearing, and I know this just from experience, having already rigged and skinned this character. So once again, as we said, we're more or less content with the back motion, the clavicles angling backwards. But forwards, we need to somehow dampen or limit that. So I'm going to select this joint and unparent it. And now we're going to go about setting up a mechanism to control the forward and back inheritance of rotation of the scapula. So in this lesson, we're going to start building the rigging we need to build our conditional scapula. So the first component we're going to build is a 2-joint scapula IK chain. And since we want to match the local rotation axis of the multi-joint clavicle, we're simply going to duplicate the clavicle by selecting the first joint, selecting Edit, Duplicate. Let's open up our hypergraph. We only need the first and last joint, so we'll middle mouse drag and drop the last joint onto the first, and then select the second joint and delete all the joints in between. So there we have our 2-joint chain here. Quickly rename them. Change this from clav 01JN2 to scap 01_IK. Let's rename the end. Scap IK02 end. Okay, so now that we have that joint built, we're going to build a rotate plane IK handle. So we're going to select the multi-joint clavicle, hide it for a moment. Then to build the IK handle, select Skeleton, IK handle tool, open the option box, make sure that our current solver is set to rotate plane. Click on the first IK joint, and then click on the second IK scapula joint. So we have our new IK handle and an effector. Let's rename both these nodes. So Cave 01 L Scap 01 IKH for IK handle. Then rename the effector Cave 01 L Scap 01 EFF for effector. Let's unhide our multi-joint clavicle. So now we need to create one more component, and that's an up vector locator, or a pole vector constraint for this IK handle. So that way, if we rotate our character off axis by using the root node or the chest or an all node, something we'll get to later when we build the larger hierarchy for this character, we can use a pole vector locator as a constraint parented onto the sternum so that that IK scapula joint won't flip during those rotations. So we'll use a locator, selecting create locator. Let's rename it Cave01 L Scap Pole Vec 01 LOC for pole vector locator. Let's open up our hypergraph. Okay, so we'll just parent it to our first scapula IK joint, and then zero out the rotate and translate channels. And then just to make sure that we're grabbing the proper orientation, we're going to select the scapula IK joint, shift select the locator, and then select constrain orient. So now if we select our IK handle, we can see that it seems to have the same, or it does have the same orientation as the locator that we're going to use for our pole vector constraint. So we can select the locator, translate it away in Y, shift select the scapula IK handle, and then select constrain pole vector. Here we still have clean rotate values on our scapula IK joint. So now we're simply going to parent our scapula IK handle to our clavicle end. So we'll hide our scapula IK to make this easy to select. Select the scapula IK handle, shift select the end of the multi-joint clavicle, and then hit the P key to parent. Let's unhide our IK scapula joint. So when we rotate our arm back and forward, you can see, because we have our IK handle parented to the end of the clavicle, that it follows the multi-joint clavicle along. So no matter what rotations we have cumulative on our multi-joint clavicle, we can be sure that this scapula IK will always aim toward the end, so no matter what combination of rotations we have. Okay, so before we finish off this left side conditional scapula rig, we're going to break for a moment and quickly explain what's going on in the conditional rotation that we'll use to set up this rig. So now we're going to go over a brief explanation of how we're going to set up the condition node for our scapula rigging. So here we have what we'll call a clavicle joint, which rotates back. We'll call this the back direction, and then forward. So here I have a joint which I'm calling the direct joint. What I have is a direct connection from the clavicle joint into this joint. So in both the back and forward direction, it gets 100% of the rotation of the clavicle joint that's connected into it. So this 100% rotation, it works in the backwards direction. We want to get 100% of the clavicle rotation. But in the forward direction, it doesn't quite work. We actually only want a portion of the clavicle rotation. So it's good in one pose, but not in the other. So I have another joint here, which I'm calling the partial joint. With this joint, I'm using a multiply divide node and connecting in the rotate channels of the clavicle joint and multiplying them by 0.5, so we'll get half the rotations of the clavicle. So in the back direction, you can see we're only getting half the rotations of the clavicle joint. It's not quite giving us what we want. We actually want the full rotation of the clavicle. But in the forward direction, it is more or less getting us the partial rotation that we want in the forward sweep of the clavicle. So between the direct joint and the partial joint, we have two halves of one solution. So finally, I have a joint here which I'm calling the condition joint. So you can see we have a multiply divide node, which is set up similar to the partial joint, where we're going to multiply the rotate values of the clavicle by 0.5. We also have a condition node. And what that node is doing, let's open up the attribute editor and select this. Our first term is the rotation of our clavicle, or actually the rotation of the clavicle joint. And what we're going to do is, if that rotation value is in a positive or negative value, we'll compare it against the first term. And so if it's in the back direction, we'll output the values of the full clavicle rotation. Otherwise, we'll connect in the output values of the multiply divide node, and in the forward direction, we'll only get a partial rotate. So here, in the back direction, our condition joint is matching our clavicle. We're getting the full negative rotation. So in that sense, with the multiply divide node, our first term is less than 0. And once again, if we open it, we can see that we have our operator set to greater than. So this first term is not greater than the second term, so we're outputting our color false values, which are the full rotate values of the clavicle. But in the forward direction, you can see our first term is greater than the second term, so we have a truth condition, which are the values from the multiply divide node, which takes the rotate value of the clavicle and cuts them in half by multiplying them by 0.5. So that's basically how our conditional scapula is going to work. It will test a condition, and if it's true or false, it will apply a different set of rotate values, one being the direct rotate values from the clavicle, or the multi-clavicle in the case of the rig, and the other being partial rotate values coming from a multiply divide node. So now let's complete our conditional scapula rig here. So we need one more rig component, which is a two-joint scapula FK. So we're going to simply select our scapula IK joint and select Edit, Duplicate. Let's open up our hypergraph. You can delete the effector node, rename this to Scap Follow FK. This will be Scap Follow 02 FK. Okay, so now that we have that new rig component built, what we need to do is we need to start connecting in the rotate values and the conditional statement to get the rotation result that we want on this. So the first thing we're going to do is we're going to need to create a multiply divide node, and with that we're going to input the rotations of the scapula IK joint and then multiply the rotate Y channel by a percentage so that we'll get a fraction of that rotation. Let's open up our script editor, clear it out. So we're going to type in create node multiply divide minus n argument, and then we'll name this cave01 L scaprot underscore MD for multiply divide. Select this mail command and hit enter. So with our multiply divide node selected, let's open up our attribute editor, confirm that its operation is set to multiply, which is the default. So what we're going to do is we're going to connect the rotate Y of the scapula FK joint, and then change the input to Y to a fraction value. In this case, it will be 0.75. So we'll multiply whatever rotation on the Y channel we get from the scapula IK by 0.75. Let's open up our connection editor, Window, General Editors, Connection Editor, load our multiply divide node into the inputs channel, and open up our input 1. We're going to select our scapula IK joint, load that into the outputs of the connection editor. Let's find our rotates and connect the rotate Y into the input 1Y. Now let's click on our multiply divide node in the channel box and then type 0.075 into the input 2Y channel. So now we're going to create another node, our condition node. So in the script editor, type in create node condition minus name cave01 l scap rot underscore cnd for condition. Select that mail command, hit enter. So you can see we have our condition node created. Let's open up our attribute editor. So in our condition node, what we're going to do is we're going to connect the rotate Y of the FK scapula joint, or the IK scapula joint, into the first term. And we're going to compare that with the second term. Now I already know that the forward rotation of our scapula IK joint will be a positive rotation. So in that case, when the value of the first term is greater than 0, we'll know that that scapula is rotating forward. So we're going to set our operator to greater than. And then we're going to connect the color of true to the output of the multiply divide node, and the color of false will be the full rotate value of the rotate Y of the scapula IK joint. Let's open up our connection editor. Let's load our condition node into the inputs. Let's expand these. Select our multiply divide node. Oh, actually, yeah, first let's select our scapula IK. Load that in. We're going to connect our rotate Y to the first term. And we're also going to connect the rotate Y of the scapula IK joint and to the color if false. So that way we're getting the full rotate values of the scapula IK. And we'll scroll to the top because we had already selected the multiply divide node, expand the output, connect the output Y of our multiply divide node to the color of true G of the condition node. So in the channel box, we're going to click and select our condition node, load that into the outputs of our connection editor, expand our out color. Now select our FK scapula joint, load that into the inputs of the connection editor, scroll down until we find the rotate channel, and connect the out color G to the rotate Y. Reselect our scapula IK joint, load that into the outputs. Now we're going to connect the rotate X and rotate Z of the scapula IK so that they directly drive the same rotate channels on the IK scapula joint. Okay, let's select our scapula FK joint and scroll through the back and forward poses. So here we're getting 100% the rotation of the IK scapula joint, but in the forward pose you can see we're only getting a fraction of the rotation of the IK scapula joint. And these are the values that we get from the multiply divide node. Okay, so we're almost done with this. We need to do one more thing, and what that is I would like to match the length of the FK scapula joint with whatever the length is of the combined rotations on our multi-joint clavicle. So we're going to need one more multiply divide node to do this. So open up our script editor. Before we do that, let's create a distance dimension node, a way of measuring that distance from the base of the multi-joint clavicle to the end. So we're going to create measure tool, distance tool. And just going to click twice in the perspective window. Open our hypergraph. We have two locators and distance dimension node. So we're going to select these and rename them. Modify, search, and replace names. So we're going to replace every instance of locator with cave01 L scap len 0, then add the underscore LOC suffix. And we'll quickly rename our distance dimension node to cave01 L scap len dist. So I'm going to simply point constrain our locators to the beginning and end of our multi-joint clavicle. So select the first clavicle joint, shift select the first locator, select constrain point, select the end clavicle joint, shift select the second scapula length locator, create another point constraint. Okay, so now we have a way of measuring the length of the combined rotations on this multi-joint clavicle. Now we'll open up our script editor and create our multiply divide node. I'm simply going to copy and paste the create node command that we used previously, but we're going to change the name from scaprotmd to scaplen for length underscore multiply divide. Select the mel command, hit enter, open up our connection editor. We're going to load our multiply divide node into the inputs, and then with that node still selected, open up the attribute editor. So here we actually want to change our operation from multiply to divide. We're going to take the dynamic distance, the changing distance of our distance dimension node, and divide that into the original distance, and then use that result to affect the scale x of our scapula FK joint. So we're going to select our distance dimension node and hit the down arrow once so that we have the shape node of the distance dimension selected, and then load that into the outputs of the connection editor. Scroll to the bottom and you'll see a distance channel, so we'll click on that and connect that into the input 1x of the multiply divide node. And then we're going to open up this node here and just type in the value of the distance dimension node into the input 2x. Another thing you could do is you could connect it to the input 2x, and that will record the value, but then when you disconnect it, it goes away. So you'll have to go in and type in that value. So with our multiply divide node still selected, let's load that into the outputs. The connection editor, scroll up to the top, expand the outputs channel, open up our hypergraph and select our scapula FK joint. Load that into the inputs of the connection editor. Scroll down until we find the scale. Connect the output x of the multiply divide node into the scale x of the scapula FK joint. Now when we scroll forward, you can see in the forward pose the length of the FK scapula joint, the scale in this case is at 0.837. So the length matches this distance, the combined distance of the rotations on our multi-joint clavicle, and the same is true in the reverse direction. You can see that our FK scapula joint sits right on top of the end of the multi-joint clavicle. Okay, so we're pretty much done at this point. We have to do one more thing. What we're going to do is replace the point constraint on our scapula pos locator and constrain it to the end of our new scapula follow FK joint. Let's select our scapula pos, find our point constraint node and delete that. Select our scapula follow FK joint, shift select our scapula pos joint, then select constrain point. Next, we're going to parent our scapula J and T to our left scapula aim locator. So now we have our conditional rotation as well as the position and aim constraint from our locators, so that our scapula will try and follow along the back, the rib cage. So we're going to begin this first example of using MEL to build rig components by showing the components that are actually used to build the rig. In this case, the clavicle with the conditional rotation scapula. So the way this works is it uses the position and orientation of a series of locators to build joints matching the position and orientation of those locators. And then the script, the MEL script that we'll use, will tokenize the name of those locators to determine the name of the joints that are built. So let's begin by building 5 locators. We're going to use 5 locators because that's the number of joints that we'll have in this multi-joint clavicle. So we'll select Create, Locator. So we've built our first. With the G key, 4 times, we have a total of 5 locators. Let's open up our hypergraph. Okay, we have 5 locator nodes. Let's select them all and quickly rename them. So modify, searcher and place names. So we're going to change a string locator to L underscore clav 0. Okay, so now we have L underscore clav 0 through L underscore clav 05. So now we're going to just using grid snap spread these out a bit. Okay, so we'll place the first locator here, second, fourth. Let's go to the last one, space it out. Okay, add our grid. Okay, so we have our 5 locators sort of spaced out. Now what we're going to do is we're going to create a series of point constraints. What we're going to do is we're going to constrain the second locator between the first and the third locator between the first and the last, and the fourth locator between the third and the last. And the reason we're going to do this is this will allow us to grab either end and lengthen or shorten this clavicle rig. So let's start with the center first. I'm going to select both end locators, select the middle, then select constrain point. I'm going to select the first and then the third, shift select the second, constrain point, then select the end, the middle, the third, and then shift select the fourth and create our last point constraint. So we want to go in at this point and change the name of all of our point constraints from clav02 and the second token and just slightly rename it. So we'll just remove the A and change it from CLAV to CLV. The reason we're needing to do that is because the script will look for clav in certain instances, so we don't want to confuse it with the point constraint node. So we'll modify search and replace names, replace underscore CLAV underscore CLV. Okay, so we can test this out. We can grab either end, expand or contract it. Okay. Now at this point we're going to create a group node, selecting Edit, Group, and holding down V for point snap. We're going to snap this group node onto the first locator and then rename this clav underscore build underscore grp. This name is important because the script will look for this name and then select all the transform nodes that are children of it, in this case the 5 locators. Let's open up our hypergraph. Let's select all 5 of our locators. Shift select our clav build group node and hit P. So now these 5 clavicle locators are children of the clav build group. And the reason why we point snapped it to the first clavicle locator is this will define the start point of the locator, so this gives us an easy way to rotate the clavicle from its start point as well as translate it. So now, because we need an FK and IK scapula joint as inputs for our conditional scapula rig, we're going to create 2 more locators defining the start and end of both our FK and IK scapula. So let's create 2 more locators. Create locator. So repeat that tool. Select them both. Select modify, search and replace names. So we're going to rename them from locator to L underscore scap 0. So now we have L underscore scap 01 and scap 02. We're going to point snap these, the translate tool, and holding down V. Snap the first scapula locator to the beginning of the clavicle locator and the second to the last clavicle locator. So now I'm going to point constrain this first scapula locator to the first clavicle locator and also orient constrain it. So select the clav 01 locator, shift select the scap 01 locator, then select constrain point and constrain orient. And once again, since we'll be looking for this scap name, we're going to eventually rename these point and orient constraint nodes, but we'll wait till we finish with the second locator. So we'll select the end clavicle locator, shift select the second scapula locator, and then create another point and orient constraint. So now we'll select those four constraint nodes, rename scap to from SCAP to SCP. So modify, search and replace names, underscore SCAP to underscore SCP. Once again, that's just to make sure that we don't have any confusion with the renaming process. So now we can select both of these, and then select Edit Group. We're going to rename this to scap underscore build underscore GRP, just as we did with the clavicle build group, and make that a child of the clavicle group. So, believe it or not, we have all of the components we need to build our multi-joint clavicle rig with the conditional rotation. Let's open up let's close this real quick. Let's open up our script editor. We'll have the script loaded. Scroll down to the portion of the script where we can see, once again, here, when we start to build the clavicle, we're going to select the clav build group. So there's that name. And then here, based on the name of the nodes within that group, we're going to call another procedure which will actually build the joints, position, and orient them based on the locators. So actually we can close that. So that's a very quick example of the components that we're using in most of the build script examples that we have in this tutorial. So once again, it's based on the locator names, their position and orientation, and the group node that they're children of. In this lesson, we're going to go over building the multi-joint clavicle as well as the conditional rotation scapula, but using MEL scripting. So in the previous lessons, we went over building both of those rig components manually. So in that way, we'll fully understand what rig components as well as what nodes and node connections we need to build it using MEL. Let's hide our geometry here and open up our hypergraph and see what components we have to build it. Let's give ourselves a little more screen space. So here, we have 5 locators, one for each clavicle joint, and they're named accordingly. Both the name, the position, and orientation of each of these locators will determine the position, name, and orientation of the multi-joint clavicle. Similarly, we have the beginning and end scapula locators. And once again, those serve the same purpose, as they determine the position and orientation of our IK and FK scapula joint. And these are constrained to the beginning and end of the clavicle so that they will have the exact same orientation and position. So now all we need to do is to move these into place. We'll do that by selecting the build group. And here we can globally move our entire rig and translate it. We have orientation control over each of these locators. But in general, I think for this clavicle, we'll want it all the orientations pointing in the same direction. We can also control the length of our multi-joint clavicle by translating the beginning or end of each of these locators. The center locators are constrained so that they'll average their distance between the two. Let's select our build group node, turn on our point snap, and snap this entire group to a point up toward the center of the chest. Let's turn that off. And we'll just translate that in a bit and then start rotating it into place. Okay, switch to a side view. So I'm going to rotate the Z back and also make sure that that Z axis is basically pointing in the same direction as the palm. Okay, we need to rotate this up in X. Okay, this looks like fairly good positioning here. Okay, I'm going to hide our model once again. Let's look at our MEL script briefly. So here we have a procedure, a proc, which will build joints, position them, orient them, and name them based on each of these locators. And this is called, in other parts of this main procedure, the global procedure, we're actually building the clavicle. And here we see we have a string prefix where we define the prefix of the character. So this could work for cave 01 or giraffe 01, whatever the character prefix is. We pass it there. So here we see a series of switches. I like building my scripts using sort of sub-procedures or discrete blocks of code that I can turn on or off. It helps me to debug the script as well as to organize it, and also you can just turn these on and off and execute portions of the script without having to execute the entire script. So here we can see with these 6 scripts, basically each of them we're building the joints and then arranging them into a hierarchy. Here we're doing it for the multi-joint clavicle as well as the IK and FK scapula. This next switch, we're building the nodes and the connections for the conditional rotation of our FK scapula. And finally, the nodes and connections to control the length of our FK scapula so that the end will always match to the end of the multi-joint clavicle. Once again, this script is available as an HTML document with considerable documentation on the Fahrenheit Digital web page. So with the split screen configuration of Maya, you could have the MEL script with the comments loaded into one screen as a web browser and then follow along interactively in the other. Okay, so now let's execute this script. I have it up as a button on my shelf. There we have it. Let's open up our hypergraph. See what we've built. We built our multi-joint clavicle as well as our IK handle, which is now a child of the end of that clavicle. We have our IK scapula joint as well as our FK scapula. And then finally, we have our locators and our distance measure. So we can test this by selecting our multi-joint clavicle. Rotate it forward. We can see that we're getting the conditional rotation, partial rotation, as well as the end lining up with the end of the multi-joint clavicle. Let's rotate it back. And we're getting 100% of the IK scapula. So here we've built our multi-joint clavicle as well as our conditional scapula rigging using a MEL script. Once again, this MEL script is available on the Fahrenheit Digital website, so you can access it in Maya and then follow along more interactively. And that script has far more commenting with explaining what's going on in all portions of the MEL script. In this lesson, we're going to start building the arm rigging for this character. We're going to start by building the IK arm joint and then use that as the basis for the FK and J and T arm joint. And once we have all three, we'll be able to set up the switching between the FK and IK arms. So we're going to start by building a couple of visual guides for joint placement and orientation. First, we're going to create clusters at the base of the arm and the wrist to define the start and end and basic angle or orientation of the arm joints, and then a 1-degree spline that we'll use to snap our joints to assure that they're in a straight line. We'll see the reason we're doing that later. A couple of things we want to consider is, because this character has such a thick arm, we want to do something a little different with the elbow joint. So rather than having a single elbow joint, we're going to split that into 2 elbow joints. And what we'll get by doing that is we'll be able to distribute the rotations and deformations across multiple joints rather than having them on a single elbow joint. And this will help us quite a bit later on when we move into skinning and deformations. Second thing we want to consider is, because of the design of the character, I've modeled the palm facing downward slightly rather than straight across. And because of that slight angle, we're going to build the arm in such a way that we can be assured that when we create our pole vector constraint, we don't get any slight shifting on the IK arm joint. And that way we can be assured that we have clean rotation values on all of our joints. Okay, so we're going to start by building the cluster, and we're going to use the edge loop tool in Maya, which will allow us to quickly select a ring of edges around the circumference of this basic cylinder of the arm. So we can use that by selecting the geometry and clicking on Edit, select the Edge Loop tool. And then we're going to double click on the first edge, which will define the direction of this loop. So double click there. So we can see we have a ring of edges, or an edge loop, selected. So let's hit Q to exit out of that tool. Now we need to convert this selection of edges to vertices, and then that into a cluster. So to do that, we're going to switch to the modeling module. Let's select Edit Polygons, Selection. Let's tear off this menu. Then in that menu, we're going to convert the selection of edges to vertices. So whatever we have selected, it will convert that to a selection of vertices. So here we have all of our verts selected. Switch back to the animation module. And let's create a cluster from all these vertices. What we've done is, this cluster, its position is the average of all of the position of the vertices. So this more or less puts us in the center of mass at the armpit of the character. Let's switch back to object mode and repeat that process with the wrist. Select the geometry, reactivate our edge loop tool. Let's double click on that edge, hit Q to exit the tool, convert that selection of vertices, and then create our second cluster. Let's go back to object mode. We can close this selection menu. Okay, now we're going to switch to a front view, and I'm just selecting the cluster so that when we switch to a front view, it centers on the selection that we have, in this case these clusters. Now we're going to create a 1-degree spline starting at the base of the arm and then making sure it's a straight line across to the wrist. So we can do that by selecting Create, CV Curve tool in the option box, making sure that our degree is set to linear, and holding down V, which is point snap, we're going to click on the cluster and snap that first CV to the cluster, release the point snap. Then we're going to hold down Shift, and then once we move our cluster, in this case to the right, it will constrain the second cluster in a straight line based on the first CV. So holding down Shift, we'll move our cursor to the right. We can see that no matter how we move our cursor, it's constrained in a straight line based on that first CV. Hit Enter. And display the CVs on that curve. And switch to a top view here. So now we're going to draw our IK arm joints, and using this curve as a guide. So select Skeleton, Joint tool. Once again, holding down V for point snap, we're going to snap it to the first CV, and release the V, and then hold down the C key, which activates curve snap. And what that will do is it will constrain whatever selection we make to the curve. So you want to click, on the curve. You can see, once again, no matter how we move the cursor, it's constrained to that curve. So we'll draw our first elbow joint, still holding down C. Draw our second elbow joint, and then our last. Hit enter. Okay. Now we're going to check the local rotation axes of all these joints and then rename all of them. Let's select them, display, component display, local rotation axis. They all look aligned. We're going to select them all and then rename them. Modify, search and replace names. So we're going to replace joint with our naming convention, in this case Cave01, L, Arm01, IK. Now we're going to do a little manual renaming here. Renaming the third token here. So this will be Arm01. We'll get rid of the one on the end. This will be Arm02 and 03 and so forth. Actually, we need to rename the second one first. Get rid of the 2 on the end. Okay, rename this third joint. Okay, now we can return to the first, rename that. We'll rename this Arm IK 04 end. And we'll just make that distinction because we're going to have multiple arm end joints. We want to make sure that we can distinguish between them. Okay. Okay, so now we can delete a couple of these guides here. The first cluster in the curve we don't need anymore. We want to make sure that we keep the second cluster. We're going to use that in a few minutes to orient our arm. So now we're going to create a couple of more components. The first being a locator for the pole vector constraint. Holding down V, we're going to point snap that up to the base of the arm and translate it back in Z and then rename it. So Cave01, call this arm pole vec and give it the LOC suffix for locator. And next we're going to create a rotate plane IK handle. Now since we built all of our joints in a straight line, if we were to create an IK handle now, it wouldn't know which direction to rotate the joints in order to solve. So what we need to do is we need to define a preferred angle for this IK solver. So we can do that by selecting the arm joints, activating our rotate tool, then defining the bend of the arm, which will set the preferred angle for the IK handle solve. So with all those joints still selected, we'll select skeleton, set preferred angle. And we can reset that to 0. So now we can create our IK handle, skeleton IK handle tool. Let's go to the option box. Make sure that our solver is set to rotate plane. So click on the start of the IK joint and then the end. Okay, so you notice that it has flipped 180 degrees. And that's not something to be concerned with now because we're going to correct that once we set up our pole vector constraint. We can see here we have a 180 degree rotation on X. But for now we're going to select our IK handle and rename it. Cave01 L Arm01 and then IKH for IK handle. Open up our hypergraph and rename our effector. EFF for effector. Get our spelling correct here. Okay, so now we have these 3 components. We're going to create one more object, a locator that will be the parent of the arm joint, the pole vector locator, and the IK handle. We're going to use that locator to position and orient all of those components and keep them all in this perpendicular, this planar relationship. And that way we can be assured that when we create our pole vector constraint, we won't get any subtle shifting as the arm, the pole, tries to adjust to point toward that locator. Let's create another locator. Create locator. Let's point snap it by holding down V up to the base of the arm and parent each of these objects to this new locator. Okay, select the locator last and hit P for parent. Okay, so now we're going to aim this locator, which is the parent of all three of our components now, the joint, the pull vector locator, and the IK handle. We're going to aim it at this wrist locator, or wrist cluster, which is the average of all those vertex positions in the wrist. So we'll do that by selecting the wrist cluster, shift selecting the parent locator, then selecting constrain, aim, so open the option box here. And we basically want to leave it at the defaults. We want the aim vector to be x, so the x points toward this cluster, and the up vector to be y. So we'll click add and delete this aim vector node. And make one more change here. We're going to select this locator, let's display our geometry, and switch to a side view. Then we're going to rotate it on X so that the y-axis points through the palm and elbow, matching that basic angle of the palm. So turn on our rotate tool, and then clicking on the x-axis, we'll rotate it so that we our z-axis is matching the palm angle. Okay, switch to our perspective views, hide our geometry here. Now once again, we have a 180 degree flip on our rotate X of our first IK arm joint. All the other joints are at 0. But if we select our IK handle, we can also see that our pole is facing 180 degrees away from the locator that will be constraining it. So once we create that pole vector constraint, it's going to rotate this pole 180 degrees, returning this joint to a 0 rotate value. So we can do that by selecting the locator, shift selecting the IK handle, and then selecting constrain, pole vector. So we can see our arm flipped 180 degrees. When we select our first arm joint, all of our rotate values are 0. And these negative 0 values are, it's something that Maya has done as long as I can remember, Maya 1, but it effectively is a 0 value in the rotate channels. So with that done, another benefit that we got out of parenting the IK handle to that parent locator is now our IK handle also has the same orientation as the joints. So that way when we move our IK handle, the bend will be on the same axis of the elbow. Okay, so with that done, we're going to create the right side joints. Start by unparenting all these components. Okay, so we're going to leave this locator. We're going to use it a little later. Select our IK handle joint, and then select skeleton, mirror joint tool, so open the option box. So we want to mirror across the YZ plane, which will flip this arm joint from the left to the right side of this character. And then we want to rename these joints, replacing the L with the _R_ to tell us that it's a right side joint. Let's click mirror. So there we have our right side arms. So one thing that we see here is we have a 180 degree rotation here. So if we select our IK handle, translate it in, we get the arm bend, we have our preferred angle, but it's 180 degrees flipped of how we actually want it to bend. So what we're going to do is we're going to create this locator that we have left over, holding down point snap, V for point snap, snap it to the existing pole vector locator, and then we're going to move it over to the opposite side by negating the translate X values. So setting this to a negative 8.232. Let's rename this. So our arm pole vec loc. Get rid of that space there. And then we're going to pole vector constrain the IK handle to this pole vector locator. So with that locator selected, shift select the IK handle, the right side IK handle, and select constrain pole vector. So now when we translate our IK handle in, the elbow is bending in the direction that we need it to. So one last thing is we're going to change the orientation of our IK handle so that it matches the orientation of the arm joints. So we're going to do that by selecting this third IK arm joint, shift selecting the IK handle, and then creating an orient constraint. Now this actually puts us into a cycle. So we want to delete this orient constraint. But now our IK handle now has local axes matching that of the joints. Okay, so now we have our right and left IK arms. Now we're going to create our FK and JNT joints by creating duplicates of these arms. So let's select the IK arm joints on the left and select Edit, Duplicate. Let's open the option box and reset this. So we're going to create 2 copies. So change the number of copies from 1 to 2. We're going to parent it to the world so that it's not parented to anything essentially. Click Duplicate. Okay, so once we duplicated it, it gave us 2 effector nodes, which actually have no effect on these joints, so we'll delete those. And then start renaming. So we'll select this and then change it from IK to FK. So modify, search and replace names. So we're going to replace underscore IK with underscore FK. Hit apply. We'll remove that 1 at the end of the first joint. And then change this arm IK04 to arm FK04. So similarly, we're going to change the underscore IK here to underscore JNT. Hit apply. Let's again remove that last number. And here we can just remove the IK. Okay, so we're going to repeat this process with the right arm. Select Edit, Duplicate. It's going to create 2 copies for us since we haven't changed those values. Delete these effectors and start renaming these. So here we have our JNT joints. And lastly, we're going to rename our FK joints. Okay, change this to FK. Okay, so we're almost there. We need to make one last change. And if we recall in the discussion on joints, when we were speaking of gimbal lock, one area that you want to be aware of potentially getting into a gimbal lock situation are in the shoulders of a character. It's a ball joint, and it's perfectly plausible that we will bypass an X rotation and rotate the arm forward 90 degrees so that the arm is pointing straight forward or further, and then we can find ourselves into a gimbal lock situation fairly easily. So on our non-IK joints, we're going to change our rotation order from XYZ to YZX. Okay, so we'll do that by selecting the first joint, opening the attribute editor, and changing the rotate order to YZX. And we'll repeat that with each of these FK and JNT joints. We don't need to do that with the IK joint. Let's rename this here. We don't need to do that with the IK joint because it's, rotation order is not irrelevant, but you'll never get into a gimbal lock situation. Okay, let's correct this here. Okay, actually let's delete this. Okay, so let's duplicate this FK joint here. Edit, duplicate. Let's change our number of copies to 1. For some reason our second duplicate was off. Okay, select these. Let's modify search and replace names. Change every instance of FK to JNT. Okay, get rid of this naming here. Okay, make sure we have 0 rotations. Okay, let's again check this rotation order, YZX. Because that's a duplicate and we had already changed it, it also has a YZX rotation value. So before we build our stretchy IK rig, I'm going to go over the simple ideas behind how this rig works. So here we have our 2 joints and an IK handle. We'll represent the length of the first joint with A and the second joint with B. The length of the IK handle will represent that with the letter C. So the first formula is fairly simple. If the length of C is equal to or less than the combined length of A and B, then the scale of each of these joints will remain at 1, meaning that as long as this IK handle is less than or equal to the combined length of these 2 joints, their scale will remain unchanged and they'll keep their original length. But if the length of C is greater than the combined length of A and B, the original length of A and B, then the scale of the joints will equal the new length of C divided by the original length of A and B. So for instance, if this new length is 2 and the original length of A and B is 0.5 or 0.5, it will apply a scale of 2 over 1 or 2 to each of these joints, scaling it to twice its length. It's a fairly simple idea. Now let's go ahead and build this new rig. So in this lesson, now that we have our arm joints built, we're going to create a stretchy IK arm. And the way we're going to do this, first we're going to build a way to measure the distance from the shoulder, the base of the arm, to the wrist, the end. And then we're going to set up a condition so that if that distance is shorter than its original length, if the IK handle moves toward the shoulder joint, this IK arm chain will keep its original length and we'll get the typical bend in the elbow. But if we move the IK handle away from the shoulder and we increase that distance, then the IK arm joints will scale or stretch to meet the IK handle at that new extended distance. So the first thing we're going to do is create a way to measure the length of the arm, and we're going to use the distance tool to do that. So to create that, we select Create, Measure Tools, Distance Tool, and click twice anywhere in the window. Hit Enter once we've clicked for the second time. Let's open up our hypergraph and see what we've created. Let's frame this. So we've created 2 locators at the 2 points in the interface that we've clicked, and then a distance dimension node. And what this node does is in world space, it measures and displays the distance between these 2 locators. So now let's rename these locators. Select them and select Modify, Search and Replace Names. So we'll replace locator, the cable 1, L, and call this arm len. Give it a 0 on the end. And give underscore LOC suffix for both of these locators. Let's rename our distance dimension node using our standard naming convention. And DST for distance. Now we're going to attach the position of each of these locators to the start and end of the IK arm joint. So for the first locator, we're going to select the first IK arm joint, shift select the locator, and create a point constraint. And for the second arm joint, rather than constraining to the end joint of the IK arm, we're going to constrain it to the IK handle. So the reason we constrain this second locator to the IK handle rather than the end of the IK arm joint is it helps us to keep ourselves out of a cycle. What I mean by that is if we were to constrain the locator to the last joint of the IK arm, the position of the locator would be dependent on the position of this last IK arm joint. But then if we were to scale the arm joints to match the new length of this arm, then the position of that end joint would also be dependent on the position of this locator and its new scaled position. So they'd both be dependent on each other's position, and that creates a cycle. So by constraining it to the IK handle, we can avoid that. So with this created and the locator is constrained, we're going to create a multiply and divide node. Let's open up our script editor and clear it out, and type in create node, multiply divide, give it a -n or name flag, and our standard naming convention, so Kval1L, and call this armlen01 MDN for multiply divide node. Select that, hit enter. So with that node selected, open the attribute editor and change the operation from multiply to divide. Then we're going to load the multiply divide node into the connection editor. So open the connection editor, load that multiply and divide node in. The first step is we're going to connect the distance attribute of this distance measure, distance dimension node, into the input 1x of the multiply and divide node. So click on that node. And we need to hit the down arrow once to select the shape node of the distance dimension node, and that's what we want to load into the outputs of the connection editor. Let's scroll to the bottom and then connect our distance attribute to input 1x, the multiply divide node. Let's open up that multiply and divide node here. For the input 2x, I'm going to type in the value of our distance dimension node, which is 14.192037. It's just like typing in all 6 digits. So now that we have that, we're going to create our second node, which is a condition node. So type in create node, condition, give it a name flag, then Kval1L, armlen, CND for condition. Let's create this node. And with that condition node selected, open our attribute editor. And here we're going to change our operation from equal to greater than. What we're going to use this condition node for is we're going to compare the first term, the original length of the IK arm joint. Or rather, I'm sorry, we're going to compare the first term, which will be the dynamic length, we'll get that through the distance dimension node, the distance attribute. Compare that to the second term, which will be the original length of the IK arm. And if this first term, the dynamic length, is greater than, if the arm is extended, the original length, then the color of true will be the output of the multiply and divide node, dividing that new length, the extended length, into the original length. Otherwise, we'll leave it at 1, which will keep the scale value at 1 for all these joints. Let's open up our connection editor again, load in our condition node, expand these windows. So select our distance dimension node, hit the down arrow once, and load that into the outputs, and scroll to the bottom. We're going to connect the distance to the first term, and then expanding this condition node, we're going to type in, once again, the original length of the IK arm, which is 14.192037. Now we're going to select the multiply divide node and load that into the outputs of the connection editor. Scroll to the top, expand the outputs. We're going to connect the output X of the multiply divide node into the color if true R of the condition node. Then we're going to leave the color of false R at 1. And so rather than thinking of these as RGB, we'll treat them as XYZ, and here we're only concerned with the scale X of all these IK arm joints. So now with the condition node selected, we're going to load that into the outputs of the connection editor, expand the out color tab, and select each of these IK arm joints one at a time and load them into the inputs of the connection editor. Then connect the out color R to the scale X of each of the IK arm joints. We don't need to connect it to the end arm joint. So let's select our IK handle. Let's translate it inward so we get our arm bend. If we translate it out, we can see our IK arm is stretching to match that new length. So pretty straightforward. That's how we set up our stretchy IK arm. Let's repeat it a little more quickly on the right side, just for reinforcement. So we're going to create our distance tool. Click twice. Let's quickly rename all these nodes. Select the locators, modify search and replace names. Change that L to R and then add the locator suffix to each of these nodes. And rename the distance dimension node. Let's create our multiply divide node. We can use the same line of MEL that we have here, but just change these L's to R's. So we're creating them on the right side. Change our operation to divide. Let's open up our connection editor. Let's load in that multiply divide node. Select our distance measure and step down once to the shape node. Connect the distance attribute to the input 1x. Okay, step back a step and constrain these locators. The first to the first IK arm joint, and then the second locator to the IK handle. Now let's create our condition node. Let's open up our attribute editor, change that operator from equal to greater than. Once again, open our connection editor. Load that condition node into the inputs. Load our distance dimension shape into the outputs. Connect the distance to the first term. Expand the condition node and input the value into the second term. Then select the multiply divide node, load that into the outputs. Then connect the output X to the color of true R. And also for our multiply divide node, type in this original length value. Type that into the input 2x. Okay, select our condition node. Load that into the outputs and connect the output out color R into the scale X of each of the first three IK arm joints. Okay, let's test it quickly. Select the IK handle. Let's translate it in. Get the normal arm bend. Translate it out. You can see our IK arm stretching to meet the new length. So there we've quickly set up the IK arm scaling on both the right and left arms. So in this lesson, we're going to set up the FK-IK arm switching. But in this arm switching, we're not only going to account for the orientation change between the FK and IK joints, we're also going to account for the scale differences, since we're going to allow scale X or length scaling on both the FK and IK joints. The animator will be able to go in and scale X on the FK arm joints, and then we also have the scaling or stretching IK arm, so we're going to have to account for that as well. The first thing we're going to do, let's open up our hypergraph and take a look at what we have here. So we have our J&T arm joints, and these will be driven both orientationally and scale-wise by both the FK arm joints and the IK arm joints. So the first thing we're going to do is to create an orient constraint for the first three J&T arm joints for the corresponding pair of FK and IK arm joints. So I'm going to shift select the arm 01 for the FK and the IK, and then shift select the arm 01 J&T joint last, and then select constrain, orient. I'm going to repeat that for the second and then the third arm joint. So if we look at the orient constraint node, we see that we have a weight of 1 for both the arm 01 FK and IK. So for now we're going to set it to FK mode by setting the weight on the IK channel to 0. That means it's being driven, the J&T joint's being driven 100% by the FK orient constraint. Okay, so another preparatory thing we need to do here is select the pole vector locator and make that a child of the first IK arm joint. So just select that locator, shift select the arm 01 FK, and then hit P to parent it. Okay, so now we're ready to set up some of the scaling connections. So with these orient constraints, we've actually dealt with all the orientation switching for the FK-IK arm joint. And from here on out, we're going to be dealing with scale change. First thing we're going to do is switch to a front view. So first, we're going to need a way to measure the translate X or length of each of the FK arm joints. So we're going to use a series of distance dimension nodes to do that. So we can select Create, Measure Tools, Distance Tool, and just click twice in the front window. Open up our hypergraph once again and start renaming these nodes. We're going to create a pair of locators and one distance dimension node for each pair of FK arm joints. It's one for the forearm, one for the bicep, one for the first elbow joint, and then one for the end elbow joint to the end of the J&T or FK arm. Let's start renaming these nodes. Select the locators and then select Modify, Search and Replace Names. So here we're going to change locator to Cave01L arm FK A0. Let's add an underscore LOC to each of these locators. Let's rename our distance dimension node to Cave01 L arm FK A01 DIST for distance. Now we're going to repeat that. Just click twice. Once again, rename. So we'll change these locator names to L arm FKB 0. Add LOC as a suffix. And rename the distance dimension node. Cave01, L arm FKB01 dist, and create the last distance measure. Rename these L arm FKC0. Once again, add the LOC suffix, and then rename the distance dimension node. Okay, let's quickly group all these just to organize it. Now what we need to do is we're going to parent each of these locators to a corresponding FK arm joint. So the first locator will be point constrained, not parented, point constraint for the first locator. So we select the arm01 FK joint first, and then the first FKA locator, and then select constrain point. Let's repeat that for the second FK arm joint. So now this first pair of locators, which defines the first distance dimension node, this first segment of the arm, the FK arm, they're point constrained now. So let's repeat that for the second pair of locators. Hitting G, and then complete it for the end of the FK arm. Okay, so what this will give us is for each segment of the FK arm, we'll be able to measure the length of that arm. And we'll need that later on when we're adjusting the length of the IK arm joints, when we're switching from FK to IK mode. Okay, so now that we have those set up, we're going to select the second, third, and then the end FK or IK arm joints. With those selected, click on Channels, Add Attribute. We're going to add two attributes to each of these IK arm joints. Once again, this is the second, third, and fourth IK arm joints. The first attribute we're going to call orig length. It will be a float attribute, so we can just hit Add. Then we're going to create a second attribute called FK length, and then hit OK. So you can see that for each of these IK arm joints, we have the two new attributes. This one will go in and set the orig length to equal the translate X at its default state. So this way we can always get back to the original length of the arm if we ever need to reset it. And then for the FK length, we're going to connect each of the distance dimension node distance values into the FK length attribute. Let's open up our connection editor, Window, General Editors, Connection Editor. Okay, let's load in the second IK arm joint. Scroll down to the bottom. Let's find our first distance dimension node. Hit the down arrow once so that we have the shape node selected, and then load that into the outputs. Once again, scroll to the bottom. We're going to connect the distance attribute, the distance dimension node, to the FK length attribute on our IK arm joint. So when we select this second IK arm joint, we can see that the original length and the FK length, at this point they match because they're all duplicates of one another. So let's repeat that process for the third and fourth IK arm joints. Okay, select the shape node, connect the distance to the FK length. Let's do this one more time for the fourth IK arm joint. Okay, so once again we can see our orig length and FK length are all identical. Okay, so now with this connection we have a way of not only resetting to our original value, but also we can dynamically measure whatever the length of each FK arm joint is for the corresponding IK arm joint, even if that FK joint has been scaled an arbitrary value. We can't always know that the FK arm joints will be scaled uniformly. An animator can go in and scale them each individually along their length to translate X. Okay, so now we're going to select, and all these attributes that we're creating now are just housekeeping attributes, I'll call them. They're ways of recording values rather than having to go in and query them on the fly, what you'll need to do. This puts a lot of the information, or all the information that we'll need, in an easy place to find them. So for instance, now we're going to create an attribute on the arm01 IK. We'll select that joint, and then select channels, add attribute. We're going to call this FK length sum. Once again, a float attribute. And what this will be is it will actually be an addition of each of the distance values, the dynamic distance values of each FK arm joint. And we'll do that by connecting the distance attribute of each distance dimension node into a plus minus average node, and then connecting the sum of the plus minus average node, which would be each of these three distances, into the new attribute that we just created on the IK arm joint, the FK length sum attribute. Okay, so let's create a node, create node, plus minus average. Let's give it a name, K01 L arm length sum PMA for plus minus average. Okay, let's load that into our connection editor. Load that plus minus average into the inputs. So with that node selected, let's open up our attribute editor and make sure that the operation is set to sum, which is the default. Okay, so next we're going to select the first distance dimension node, hit the down arrow once so that the shape node is selected, then load that distance shape node into the outputs of the connection editor. Scroll to the bottom till we find the distance attribute, then connect the distance into the input 1D of our plus minus average node. So now we're simply going to, in the script editor, copy and paste the connect adder statement so we can duplicate this twice more. So in this case, we're going to connect each subsequent distance dimension node. So this will be FKB and FKC. Then we need to increment the index of the input 1D field of the plus minus average node. So rather than an index of 0, we'll change this to 1 and this to 2. So what this is doing is connecting the second and third distance dimension node distance attributes into the plus minus average node. So that way it will sum all three distances. Okay, so now let's select our plus minus average node. Let's once again open our connection editor and load the plus minus average node into our outputs. Select our first IK arm joint, load that into the inputs of the connection editor, scroll to the bottom, Then connect the input 1D, which is the sum of all of the uh, distance dimension measures for the FK arm joints, to the FK length sum. So here we have 14.192, which will match the arm length multiply divide node input to x value, which is the sum of the translate x length of each of the IK arm joints. So once again, they're duplicates, so that makes sense. Okay, so one more step here. We're going to set a limit on the first, second, and third IK arm joints so that their minimum scale x value will be 1. Okay, so we'll select the arm01 IK joint, open the attribute editor, scroll down until we find limit information. Let's expand that. Then rather than the rotates, we're going to limit the scale values. So here the current scale is 1. We can just click the left arrow to load the current value into the minimum channel, and then click on the minimum box to enable it, hitting the down arrow to move to arm02 IK, and just repeat that process. Okay, so at this point we have a lot of the information we need to actually create the arm switching. There's one more thing we need to do. We need to create a condition node for each J&T arm joint. So the first, second, and third, we need to create a condition node for each of them. Once again, this is quite a bit here, and I'm going over all the steps involved. This is covered once again in the Animation GUI MEL script, where it takes all the inputs that we're creating here and then creates all the MEL scripting to accurately switch between FK and IK modes using all of the attributes and connections that we're creating here. Okay, let's create a condition node. So create node, condition, give it a name, -n flag, so cave01, L, arm scale 01, C and D. The arm J&T scale. Select that, hit enter to create our condition node. So with that node selected, let's open our attribute editor and change our operation from equal to greater than. What we're going to do is we're going to leave our second term at 0 and then connect the weight of the FK orient constraint on the first J&T arm joint orient constraint into the first term, so that if we're in FK mode, the first term will be 1, which equals the weight of the orient constraint, and that will be greater than 0, the second term, and then we'll output the color of true value, otherwise the color of false. I'm going to copy and paste that line to the bottom of the script editor, because we're going to use this twice more for the second and third J&T arm joints. So as we execute these steps, we'll just copy and paste it so that we can just change the numbering and repeat the process fairly easily. So with the condition node selected, once again open our connection editor, load our condition node into the inputs, select the orient constraint, the first orient constraint for the arm01 J&T joint, load that into the outputs, and then connect the arm01 FK weight into the first term. So next we're going to select the arm01 FK. Before we move on, let's copy and paste that line. Okay. Now we're going to select the ARM01 FK, load it into the outputs of the connection editor, scroll up till we find our scale X. We're going to connect the scale X to the ARM01 FK and to the color if true R. So when we're in FK mode, we want to connect the scale X of the FK joint directly into our JNT ARM joint. Okay, once again, let's copy and paste that output. Okay, so now rather than connecting the scale X of each IK ARM joint, let's clear out the history on the script editor. What we can't do that, and the reason being is when we switch to IK mode, we're actually going to reset our IK ARM scale multiply divide node so that it will, despite its new length, will reset it so that it's at a value of 1. So it thinks its scale is 1. And we will have adjusted the translate X, or the length of each of those IK ARM joints, to match the length of the FK ARM joints. But the scale will be 1, so that way we'll be able to utilize the IK ARM scaling or stretch and squash on that joint. So even if the arm is twice its length and then we switch to IK mode, it thinks its scale is 1. So if we were to connect that in directly into the condition node, we'd have a scale of 1 in our JNT arm joint, when in actuality it's probably a lot greater than that, or could be a lot greater than that. So what we need to do actually is to multiply the scale value of the IK arm joint, once it's been adjusted, to the scale X value of the corresponding FK arm joint. Okay, so what we need to do here is create node, multiply divide. Let's give it a name, Cave01 L ARM FK scale 01 MD. Okay, load this into our inputs of the connection editor. And here we already have our ARM01 FK joint selected, so we can connect the scale X of our ARM01 FK joint into the input 1X of the multiply divide node, and then select the ARM01 IK ARM joint, load that into the outputs of the connection editor, and then connect the scale X attribute of the IK ARM joint into the input 2X of the multiply divide node. Make sure that our multiply divide node is set to multiply. Oh, wrong one. There we go, ARM FK scale 01. Okay, so set the default of multiply. We're going to load our multiply divide node. Let's select that here. There we go. Let's load the multiply divide node into the outputs of the connection editor. Now let's connect that into the condition node. Into the color if false. So connect the output X into the color if false R. Load our condition node into the outputs of the connection editor, and then connect the out color into the ARM01 JNT scale X. Okay, let's find these lines here and copy and paste all of them. Okay, should have done this as I was going along. Okay, a few steps are missing here, so we'll go through the second one manually again as well. Okay, sorry for that pause there. Okay, so now let's set this up again for the second FK arm joint. Actually, we're going to skip the second and set it up for the third. Okay, let's create our condition node. We're going to set this condition node to greater than. Let's go manual again. Let's open up our connection editor, load in our condition node. Okay, once again, we're going to use the weight of the FK channel on the first orient constraint node as the first term. We're going to connect the scale X of the third FK arm joint, scale X. We're going to connect that scale X into the color of true R. Then we're going to create our multiply divide node. Once again, it's set to multiply, which is the default. We're going to connect the ARM03 FK scale X to the input 1x of this new multiply divide node. And then connect the ARM03 IK scale X to the input 2x. Then we're going to connect the output x of this multiply divide node to the color false R of our condition node. And then connect the out color R of the condition node to the scale X of the J&T arm joint. Okay, so let's try this switching real quickly here. So right now, all of our J&T arms are in FK mode. Since the FK weight is set to 1, the IK weight is at 0. So let's select our IK arm joint. Start rotating. Okay, scale the first joint here. Going to select both elbow joints and rotate them together. eventually what we're going to do is actually connect the rotate values of the arm02 so that they are driven by the rotates of the arm03. So that way the animator will only need to select one arm joint. So we're going to select the third arm joint and then scale it on X. Okay. So now to switch to IK mode, I'm going to just manually snap our IK handle to the end of our FK arm joint, and this will all be done with Mel in the animation GUI. So when we look at our IK arm joint, it has stretched to match the length, let's hide this grid here, of the FK arm joint, but it doesn't have any rotation values. It's a straight chain here. So what we're going to do is on the second, third, and fourth joints, we're going to set their translate X to equal the FK length attribute value. So in this case, we'll set it to 7.717. I'm just repeat that down the line. Leave that at 1.236. I didn't scale that. And then set this last one to 21.269. Okay, it's still off. And the reason being is we're still applying a scale factor to each of the first three IK arm joints. So we're going to select the arm length multiply divide node and set the input to X to equal the FK length sum attribute value. So in this way, we're actually resetting the scaling mechanism on the IK arm joint so that this is now its new default length. So we're going to change this to 30.222. And now the scale on each of our first three IK arm joints is 1. And we've applied a translate X to the second, third, and fourth IK arm joints. So now they match the orientation and length of each of the FK arm joints. So now what we need to do is simply set the weights of the orient constraints from 0 on FK to 1 on IK. So there, our J&T arm has the orientation and scale matching the IK arm joint. What we're doing for the scale X, we're actually multiplying the scale X value, which is 1, by the scale X value of each corresponding FK arm joint. Okay, so now that we're in IK mode, let's move the IK handle around a bit. Switch out of point constraint mode. Okay, you can see we still have the scaling, so we'll just scale our IK arm, considerable length here. So now we're going to switch to FK mode. Now the first thing we need to do is we need to record each of the rotate values for the first IK arm joint. Actually, we're going to want to do it for each of the first three. But since the arm is straightened here for this example, we'll just record the first one since the rotate values will be 0 for all the others. And the reason we want to record these values before just simply matching the orientation of the FK arm joints to the IK is when we switch the orientation of the first FK arm joint to match the IK arm joint, it will actually change the rotation values on that first IK arm joint because we'll be changing the position of the pole vector. Let's go in and record these values. So in this case, we have negative 61.458, negative 85.355, and a positive 26.734. And we're going to use Mel scripting in the animation GUI to record these values, but here we'll just do so manually. And to make sure that we're switching this properly, we're going to simply duplicate the FK arm joint and then template it so we can make sure that despite the shifts that we're getting, that our IK arm joint will be aligned perfectly. Okay, so let's reset these rotate values. So this is negative 61.458. The rotate Y is negative 85.355. And the rotate Z is positive 26.734. Then we know that the rotate values on the second and third IK arm joints are 0, so we'll set the FK arm joints to 0. And once again, we can't simply use the scale X of the IK arm joints because we actually reset our scaling connections on the multiply divide node. So what we need to do is we need to multiply the existing scale X value by the uniform scale X value on each of the IK arm joints. So what I mean is we'll multiply each scale X of the second, third, and fourth IK arm joints. We'll multiply each of those by 1.582. Okay. Once again, we'll do this using MEL, but for this example, we'll simply use a calculator program. So 1.582. We'll multiply that by 1.649, which is the current scale X value of the first IK arm joint. So we'll set that to 2.608. I'll just type in all the values here. Okay. Second arm joint, since I didn't apply any scaling to that, we'll just type in the 1.582. Its default is 1, so 1 times 1.582 is 1.582. The last joint is 2.57. Let's open up our calculator once again. So 2.57. Once again, we'll multiply it by 1.582, which is the scale X value on the IK arm joint. We'll set this as 4.06574. So now what we need to do is we need to switch back to FK mode so that we'll be getting the scale values of the FK arm joint at this point. So we can see that our FK arm matches the length of the IK and the FK. There's our original arm length. We can delete that duplicate. So that, it's quite a bit to absorb here, but this is basically how we're going to, or this is how we're going to set up our FK, IK orientation and scale switching. And once you've built your rig, the main thing that we need to do in the rig building is we need to make sure that we have an orient constraint for each of the first 3 J&T arm joints. We need to make sure that we've created a distance dimension node for each pair of FK arm joints for a total of 3. And then we need to add a number of attributes onto our IK arm joints. So for the first IK arm joint, we need an FK length sum, which is the total value of all of the FK arm joint distance dimension nodes. I'm using a plus minus average node to get that. And then for the second, third, and fourth IK arm joints, we need to add two attributes. An orig length, which records the original length of the translate x of that IK arm joint in case we need to reset it. And then an FK length, which is the distance dimension node distance for each corresponding FK arm joint. We just plug that in directly. And then once again, all of the switching is covered once again in the animation GUI with documentation. So once we've set up all of these connections and attributes, the MEL scripting will do all the switching for us later on when we set up our animation GUI. So aside from that, then we also need to remember to create a multiply, divide, and condition node for each of the first three JNT arm joints. So this way we can switch between the scale values for either the IK arm joint or the FK arm joint. And in one case, it will be the IK arm joint scale value, which will have defaulted to 1 once we switch to FK, multiplied by the current FK scale X value. Once again, quite a bit to absorb, but hopefully we can run through this again if it's not clear to you, and it's covered once again when we explain the FK-IK switching in the animation GUI in the final chapter in this lesson. So now we're going to begin building the IK-FK switch, but first we're going to talk about how this is going to work. Many IK-FK arms and legs work by blending between a pair of orient constraints. Both the IK and the FK driving arms will be feeding their orientations into the final driven arm through a pair of orient constraints. And by blending in and out of the weights of each of those, you can blend in the orientation or how the final arm joint is being driven. We're going to build a slightly different arm. Although it will have all the same components, the pair of orient constraints, what will be different with ours is rather than blending the orientation over a series of frames, we're going to switch the orientation on a single frame. And the reason this is from experience, every rig that I've built, the animators have requested that they would like to pose the IK or FK arm and on that frame switch from IK to FK, but have the arm maintain the pose that they've set it at. And then once the switch has taken place, to continue animation in the new mode that they've set, but from the pose that they've placed the arm in. So in this case, it makes sense. It results in less work for the animator and less guesswork. They've posed it in that particular pose for a reason at that frame, and so they'd rather start their animation from that point forward and not have to match positions and rely on the computer to interpolate the blending back and forth. They'd rather have control over that. So the first steps is we're going to actually delete the clusters and the spline that we use to build our arm joints with. Then we're going to unparent all the FK components. We're going to unparent them from the locator that we use to position and orient them. Then we can delete that locator. So once again, the first step will be that for each FK and IK joint, each will have an orient constraint feeding into the rotate channels of the JNT joint. So we can do that by selecting the FK joint first, IK joint next, and then the JNT joint, and then selecting constrain, orient. Now we want to repeat that 2 more times, making sure that we select all the nodes in the same order, and hitting the G key to repeat the last tool. We want to make sure that it's in the same order so that our orient constraint values are consistent. So when we write our MEL script to switch later on, it will be easy to figure out what's going on here. So we can see we have three orient constraints, each with an FK and IK weight of 1, which is 100%. So we can see what's happening by selecting the IK handle and repositioning it. We can see that the J&T arm, since it's getting 100% of the orientation from each of these joints, the FK and the IK, it's basically averaging its orientation between the two. But if we were to go in and one by one set the IK weights of the orient constraint to 0, it will reposition itself to get 100% of its orientation from the FK joint, since from this point on it's not getting any orientation from the IK. So in this sense, you can see how we could, by using an attribute to shift from 0 to 1 with the orient constraints, how we could blend from one arm joint to the other. But once again, that's not the approach we're going to take. We're actually going to switch on a single frame. And it works in a very similar fashion. We need to take a couple of extra steps. Okay, so let's open up our hypergraph and reset all of our IK weights to 0, just as a starting point. And let me pose our FK arm, just so we can see if our switch is actually working. Let me back up. The first step we need to do actually, before we pose the arm, is to parent the pole vector locator to the first joint of the FK arm. And what this will do for us is, no matter how we orient the first joint, it takes the pole vector constraining locator along with it. So this tells the IK arm how it needs to be oriented at its base to match the orientation of the FK joint. So now at this point, we can pose our FK arm and just arbitrarily rotate the base. So just to demonstrate the FK switch, since the base rotation will be gotten through the pole vector locator, let me turn on the handles here. All that we need to do here is to select the IK handle, activate point snap, and reposition the IK handle to the end of the FK arm, and we can see that they match perfectly. All the orientations match perfectly. Okay, so let's back up. Now once again, we're going to actually accomplish both the IK to FK and FK to IK switches using MEL scripts. And the animator will activate these switches through a GUI that we're going to write later on in this tutorial using MEL. But we'll write the scripts now to give you a taste of what these scripts actually do and how they work. So for each of these switches, the first step I'm going to take is to set all of the orient constraint weights to 0. We're going to use the set adder command to set the weight of an attribute, or set the value of an attribute, in this case the weight of the orient constraint. So we need to specify which object we're actually manipulating. In this case, the orient constraint. So what this MEL command is saying is we want to set the attribute value of the first arm J&T joint orient constraint, the FK joint weight. We want to set that value of the orient constraint to 0. Let's select this command and activate it. We can see that our J&T joint now has 0 on both orientation constraint values, so it will return to its original position, which is straight. So I'm going to copy and paste this twice. And change the joint to the second and third. And execute these last two commands to straighten the J&T arm out completely. Now the next step is we want to find out and record the position of the end of the IK joint or FK joint. We're going to record the position, the world space position of that joint, because that's the position that will then later set the IK handle to match. So we're going to do this by creating a float variable, and give it a name, FK_pos for FK position, and then 2 square brackets. What the square brackets tell us in MEL is that not only will we be storing a float attribute, which is a decimal point number, but we're going to be storing an array, the X, Y, and Z float attributes in this case. So more than one float. So here we're going to use the xform command to actually ascertain what the position of that joint is. And I'll explain this command in a moment. So here we're going to, with the xform command, query the world space position of the rotate pivot of the fourth joint of the FK arm, and then store the 3 float values into this variable. So there we can see this is the world space value that has now been stored. So the next step is we're going to set the translate values of the IK handle to each of the float variable values. So we're going to use the command, the setAttr command once again. So here we're saying set the attribute value of the IK handle translate X to the first index of this float array. And the first index will be the X value. Let's copy and paste this twice. We need to change the index, increment it by 1 for the Y and the Z value. And then change it to reflect for which translate value we're affecting. Let's select all 3 of these. We should see our IK handle set to match the position of the end of the FK joint. Okay, it's working fine so far. Now the last step will be to set the weights of our orient constraint so that now the IK handle, the IK arm, will be driving the J&T joint. So we'll change all these from FK to IK, change their weight value from 0 to 1, and that should do it. Oh, I'm sorry, change this to weight 1. Select all 3 of these, hit enter. We saw our J&T arm jump to the FK arm. Now let's test it by repositioning our IK arm. Actually add a little twist in there. Open the attribute editor. So we can see that our J&T arm is now following the FK or the IK arm. So now we're going to go in reverse. So I'm going to actually select the IK arm and duplicate it, and then template this duplicate. See, display, template. This way we can see if our change is actually working, our switch is working in the opposite direction. Now this switch is a little trickier. Not that much trickier, but just a little. Once again, the first steps will be setting all of the orient constraint values to 0. And then what we need to do is we need to record the rotate values of the IK arm. And that's because if we were to take the rotate value, let's say we would start with the rotate X, take that value and put it into the rotate X of the FK arm, it will change the position of the pole vector constraint, which then affects the rotate values in our IK arm. So what we need to do is, before we actually make that change, record all the rotate values in the 3 IK arm joints. And then, with those values recorded, place those values into each of the 3 FK joints. And so that way, whatever changes we get through the a change in position of the pole vector locator won't affect the FK joint. Okay, so let's start this process, give ourselves a little more room since we need a few more mel commands here. Okay, so I'm going to actually delete everything except for the last line. In this case, we're going to be setting these values to 0. Okay, so we can see our J and T arm straighten since it's no longer driven by anything. So now we need to create another float array variable to store the rotate values of each of the IK arm joints. Very similar to what we did in the previous switch. So get adder. We need to tell it which attribute we're getting. So in this case, we're saying that in this float array, we want to get the attribute value of the first IK arm, all the rotate values. So if we select that, you can see we get 3 rotate values, X, Y, and Z. Let's copy and paste this twice. Change these, B for the second IK arm joint, and C for the third. Change these to second and third arm joints. And once we have those values recorded, we need to actually set the rotate values of our FK joint to match the values that we've just recorded. So we're going to use the set adder command once again. So with this command, we're saying set attribute of the FK rotate X to match the first index or the rotate X value of this float array, the rotate X of the IK arm joint. So we're going to have to copy and paste this 2 more times and change this to from X to Y and Z, and change the indexes from 0 to 1 and 2. Let's try this. Let's record these values. and then set their rotate values. Now let's copy and paste this twice and change it from arm 01 to arm 02. Change this from A to B. Change this to C for the third joint, and then specify the third joint. Okay, so now that we've repositioned our FK arm, we're going to switch our orient constraints. I'll just copy these 3 lines here, paste them, change it from IK to FK. Change it from W1 to W0, and set their weight to 1 so that now the FK joints will be driving our J&T arm. Now the last step is I'm going to remove all twist values from our IK handle. We'll set adder. This will zero out the twist attribute on the IK arm. Now let's look and see. So there's our templated arm, which is a duplicate of the original IK arm position. So there we have the 2 mel scripts that we're going to use later on to activate our IK to FK and FK to IK arm switch. And we'll go through these once again, and they're documented in text files so you can follow along with the documentation a little more clearly to get a better understanding of what's going on with these scripts. So in previous lessons, we've set up the FK and IK switching for this arm, as well as the IK stretching or scale. We're going to finish this arm rig by setting up a condition where when we switch between IK and FK, the orientation will also switch between the scale of each of the IK and FK joints. And lastly, we'll change the rotation order of our first arm joints to help us avoid gimbal lock, just as a precaution. So we're going to use a condition node to switch between the scales. In the past, I've tried using multiple scale joints and then switching their weights, but I've gotten unpredictable results, so we'll stick with what I know works and is stable and predictable. Let's open up our script editor and create our condition node by typing in create node, condition, let's give it a name, cave 01, L, arm scale 01, C and D. Select that and hit enter. So with this node selected, let's open up our attribute editor and change the operation from equal to greater than. Now each step I'm going to copy and paste the output into the script editor so that we can reuse this for our second and third arm joints. So now with our condition node still selected, let's open up our connection editor and load it into the inputs. Let's expand these. Then we're going to connect our first orient constraint, the FK weight, into the first term. And we only need to make this one connection since with the IK-FK switching, all 3 orient constraint weights are changed simultaneously. So if one of them is changed and we can check the weight of that, then we know the state of the arm, whether it's in FK or IK mode. So we'll connect the FK weight into the first term. We can see here that the first term is greater than the second, so we have a true condition, in which case we're going to want the color of true R to be the scale X of the FK arm joint, and then the false color will be the scale X of the IK arm joint. Now let's make those connections. Let's copy and paste that output. Now we're going to load the first IK joint, or first FK arm joint, to the connection editor. Connect the scale X into the color of true R, and then connect the scale X of the first IK arm joint to the color of false R. Let's copy and paste those lines of mel in the output to our script editor. Okay, there's the connection to the true value. And we need to make one more connection, and that's connecting the output of the condition nodes. We're going to load that into the outputs of the connection editor to the scale X of the first driven or J&T arm joint. Scroll to the top, expand the out color, connect the out color R to the scale X of our J&T driven arm joint. Let's copy and paste that. So we can see the scale X of the J&T arm joint is being driven. So now we can repeat this by just altering the numbers on these so that we create a second condition node. So change all the scale 01 underscore CNT to scale 02 underscore CND. We're going to leave this, since we're only concerned with checking the weight of the first orient constraint. We're going to change the scale X of the IK and FK from 1 to 2. We'll change this to 2 also. Select that, hit enter. Select our second J&T arm joint and verify that the scale X is connected. And repeat that process for the third arm joint. Select and execute this. Select our third J&T arm joint. Verify that the scale X is connected. So now to test this, we're in FK mode at the moment. I'm going to select our IK handle, translate it out so we can see that it's scaled, but we're still in FK mode. So open up our hypergraph, and we're going to switch the weight of each of these orient constraints so that we're be in IK mode. So here we can see not only we're getting the orientation of the IK, we're also getting the scale. Now let's test it in the opposite direction. So rotate our FK, give it some scaling in X, select the last joint and scale it so that we have a non-uniform scaling. Select our orient constraints and switch them back to FK mode. So there, even in the case where we have non-uniform scale values in X, we've switched back and forth between the orientation and scale of each of these FK and IK arm joints. Okay, so let's reset this. In this lesson, we're going to set up a local global switch for the FK arm. So what I mean by that is when we rotate the chest or the clavicle, for instance, in local mode, this FK arm would maintain its orientation local to its parent, which in this case would be the end of the clavicle. But in global mode, it would behave as it's behaving now, where it would ignore the orientation of the chest or the clavicle and instead seem to be deriving its orientation from a global coordinate system. So we're going to set this up by using a series of locators. One will be the parent of the FK arm. One will derive its orientation from the end of the clavicle, and the other will serve as sort of a root node global orientation. Let's start by creating 3 locators. Create locator. I'll just click on this icon twice. Open up our hypergraph. We have 3 new locators. So I'm going to rename these. Select them. Search and replace. We're going to replace locator, suffix CL. Okay, then I'm going to go in and name them individually. So I'm going to name this Home 01 locator. This will be our local locator. And the last will be our global 01. So for our global, we're going to point constrain it to the pelvis or hip. For our local, we're actually going to parent it to the end of this clavicle. Let's frame that locator and then 0 all of its transforms so we can see it pops to the end of that clavicle joint. Okay, so for our last locator, we're going to position it at the base of the FK arm and 0 out its transforms, then unparent this joint. Now we're going to parent that underneath the joint that we're using to constrain our FK, IK, and JNT arm width, and then parent the FK arm beneath that. I'm going to check one more thing. I'm going to display the local rotation axes of each of these. Display local rotation axes, show the handles. Okay, so this we're going to, that was the wrong one. Select the right locator here. Apologies for that. Okay, so our Y's are pointing more or less upwards. So now we're going to use, let's hide these, a parent constraint between the local and the global locator. We're going to select the local, shift select the global locator, and then select our home locator last. Select constrain, parent, option box. Shrink this down a bit. So we're going to leave our maintain offset enabled. We're not concerned with inheriting or constraining the translate axis. We'll get all of our translation from the positionally constrained locator, which is the parent of the home locator. But we do want all of our rotation channels constrained. So we'll hit Add. Let's open up our hypergraph again. Select our new parent constraint. Set our weight to local. rotate our chest. So our arm remains local to the orientation of the chest. Let's double check the clavicle. So again, we have local orientation for clavicle rotation. Now let's switch to global mode. Let's test our chest joint. Now let's just test our clavicle. So pretty straightforward and simple. And one benefit of this, let's switch back to local mode. Is with the fairly minimal work here. Let's rotate this up. Our J&T joint inherits all the orientation of our FK joint when it's in FK mode, so we don't have to do any work in that regard. We only need to set up this fairly simple parent constraint to allow us to switch between the local and global orientation of our arm joint. And this is something that can be done with any body part, with hips. We'll do it later with the neck when we're into the head rigging. Pretty straightforward, but that's our first example. So here's a simple example of the benefits of having a split knee joint configuration for either the arms or the knees. This example, we have a two-joint system. We can view this as a leg or an arm, where this will be either the knee or the elbow. And here, we have that knee or elbow joint split into two joints. And then we have a polygonal cube which has been smooth bound at default values for either. So I'll quickly bend this at the knee or elbow. So you can see that with both joints selected, it's applying both rotation values. I'll put in a -45 across both joints. So here we have an accumulated rotation of 90 degrees. Whereas if we set this to -90, this is what we get. Turn off the grid so we can see this a little better. And this doesn't look so bad. But what we'll do now is we'll set this to 180, which of course is quite extreme, but this will illustrate the example more clearly. -90. And since we have two values of -90, it adds to -180, basically bending the knee back so that the bottom of the leg or arm points toward the shoulder or hip. And here you can see we reach a point of like a singularity where one joint overlays exactly over the top of its parent joint. Whereas with this, we distribute that rotation over two joints. So you get a slightly better deformation, slightly better control over how that deformation occurs in that area. So even in extreme poses like this, which isn't an impossible pose for either an arm or a leg, we can see how this creates a natural gap or volume preservation, whereas this starts to collapse in on itself. That's a quick example of why we're going to split our knees and elbows for our characters. It's a good idea in general, and hopefully this illustrates that point pretty clearly. So in this lesson, we're going to build a fairly standard rotate plane IK leg. And then we're going to use a locator as a pole vector constraint, and we'll use that constraint to control the forward and back swing of the knee of our IK leg. So we're going to build a split knee IK leg, meaning that rather than having the knee joint running down the center of the knee, I'm going to split that joint into two separate joints, just above and below the center line. So in that way we'll be able to distribute the rotations along the two joints, which helps with the deformations in areas like the knee and the elbow. So I'm going to start by building visual guides for our joints, and I'm going to build some clusters and then snap a 1-degree spline to the clusters and then snap joints to that. Sounds like a fairly tedious process, but it's actually a pretty quick way to build joints. So with the geometry selected, I'm going to start selecting rows or loops of edges by selecting Edit, select Edge Loop tool, click on an edge, then double click, and it selects an entire loop of edges. I'll hit Q to get back into standard selection mode, switch to modeling. I'm going to select Edit Polygons, Selection. I'm going to tear off the menu so we can see it. Now I'm going to convert the selections to vertices, so it will select the edge selections to a series of vertex selections. We also want to make note of the hotkey, which is Control F9. But for now, we'll just select the tool. We can see that the edges we previously had selected have been converted to vertices. So with those selected, I'm going to switch back to the animation menu and then select the form, create cluster. And it creates a cluster that's the average of the position of that loop of vertices we had selected. Switch back to object mode. Let's repeat that process for the edge loop just below the center line of the knee. Activate the edge loop tool, click once, double click, hit Q to get back into standard selection mode. This time we're going to use the hotkeys, which is Control F9. And since Create Cluster was the last tool that we used, I can just hit G and repeat that last tool, which was Create Cluster. Repeat the process for the ankle. So here we can see, because of this 5-edge juncture, the tool doesn't quite know which way to continue the edge loop. So we'll just click the direction that we want to continue it in and double click to create a continuous edge loop. Q, Control F9, and G to create the cluster. Now in this area, we want to create a loop of vertices to build our cluster from, right at this bend where the top of the hip meets with the torso. We're going to do that by actually creating an intersection of vertices and then pruning out the vertices that we don't want. Activate the edge loop tool. So I'm going to select right down here. You can see it selects the edge loop all the way through the character. We can prune that out later. And then our intersecting selection will be through here. Double click, set Q, Control F9, so we can see that we have quite a few vertices selected. We can easily prune those out. So we're still in component mode, so I'm going to click on the Select by Component Types tab here. And then holding down Control, simply drag and deselect the vertices we don't want in this selection. We only want, once again, a loop of vertices around the base of the hip, the juncture into the body. So holding down Control, prune out the vertices we don't want. And hit G to create a cluster and go back into object mode. So now we're going to create a 1-degree spline by point snapping each of the CVs of that spline onto the clusters. We'll do that by selecting Create, CV Curve tool, making sure that it's on 1 degree or linear, reactivating the point snap tool and clicking once on each of the clusters, and then hitting Return when we're done. Let's deactivate that point snap tool. And with the curve still selected, we'll select Display, NURBS Components, and CVs. So now we can delete the CV or the clusters that we've created. Let's open up the outliner, select the 4 clusters, and hit delete. So now let's look at our model here. And I know that I'm going to want to slightly reposition the start of this curve. So I'm going to switch to component mode, select the first CV, hit the translate tool, and switch to a side view. I'm going to move the start of the curve a little higher up on the hip. Switch to a front view and translate it down so that it's closer to the center of the bend as we initially intended. Switch back to a side view, move it forward so it's more toward the center of the mass of the hip. Going to hide our geometry, switch back to object mode, then activate the joint tool and point snap each joint to one of the CVs of this spline. Do that by selecting skeleton joint tool, reactivating the snap to points tool, and then clicking once with the joint tool on each of the CVs and then hitting return once I've drawn my last joint. Just deactivate that point snap tool. Show our hypergraph and display all the local rotation axes of these joints. So we can see that they're all over the place. So in this case, I'm going to manually rotate the local rotation axes of these joints to get them in the alignment that we want. And I'm going to use the locator as a visual aid in that process. In the next chapter, we're going to rebuild this leg, and I'm going to use aim constraints to more accurately alter the local rotation axes of each of the joints. But in this case, I'm going to do it manually just to show you that process. Of course, first step is rename our joints, select them all, change every instance of the string joint to our naming convention. And underscore JNT at each of the joints. I'm going to underscore end for an end. I'm going to reorient the end joint to match the orientation of its parent, selecting the end joint, skeleton tool, orient to joint. You reset it. Then we need to set it to none so it has no orientation change relative to its parent, meaning that it matches its parent's orientation. So now I'm going to create a locator and both point and orient constrain it to the first IK leg joint. Constrain point and constrain orient. Open our hypergraph, delete those constraints on that locator. I'm going to select that locator and also display its local rotation axes. So now that we can see that when I rotate the locator, I created the orient constraint so that its x-axis, the x-axis of the locator, would match the x-axis of the first joint. So I could just rotate along x and change the orientation of the locator and then use that as a visual guide to match the orientation of the first leg joint to. I'll switch to template mode. Just visually rotate this so that it matches the orientation of the major hip mass here. I'm going to go into shaded mode and use the plus key to make the rotate manipulator larger. Once again, I'm eyeballing it, but in the next case, and sometimes this works perfectly well, In the next case, I'll use a slightly different method to get a more accurate orientation if that's required. Okay, so now with the locator oriented, I'm going to switch to component mode and activate the local rotation axes component selection. Select the local rotation axis of the first leg joint and manually rotate it into place so that it matches the orientation of the locator. I'm going to constrain the locator, point and orient constrain it to the second knee joint. Select that joint, select the locator, constrain point, constrain orient. Open our hypergraph and delete those two constraint nodes in the locator. Going to show our geometry again. Once again, manually rotate the locator so that it will give us the alignment that we want to the leg. So I'm going to switch to reference mode or standard mode. What I'm doing here is I want the y-axis to basically pass through the front of the knee. Looks good there. Switch to component mode. Select the local rotation axes of the second leg joint. Activate the rotate tool. Then manually rotate it to match the orientation of the locator. And one visual clue that I use just from experience is when I'm rotating the local rotation axes, and you'll see it more clearly on your machine, on your monitor, is when that axis sort of disappears behind the locator. That's when you know it's closely aligned. You can also switch to the top view and get another good visual view for lining up that axis. So now I'm going to want the third and last joint to match the orientation of the first knee joint. It's going to switch to object mode, point constrain, only point constrain the locator to the second knee joint. And I'm not going to change any orientation on the locator. Switch back to component mode and select both the last and the second to last joint. Switch to top view, activate the rotate manipulator, and rotate the second knee joint so that it aligns with the locator. Switch back to object mode, open up my hypergraph. I can delete both the locator and the guide spline at this point. We have our leg. That's back up here. Didn't quite get my orientation right here. Switch to top view. Let's align the y-axis. There we go. Now we can delete those guides. I just hit the Z key just to back up and correct the mistake I had made. So now we're going to create a rotate plane IK handle. You can simply do that by selecting Skeleton, IK Handle tool, going to the option box, making sure IKRP Solver or Rotate Plane Solver is selected. Click OK. We can see our manipulators change to the IK tool. Select the first joint, the second joint, and hit Enter. Let's rename this IKH. Open up our hypergraph and rename the effector EFF suffix. At this point I'm going to select the leg joint. I could have done this before I created the IK handle. I'm going to mirror that joint to the opposite side. Selecting skeleton, mirror joint tool, making sure that, oh, excuse me, mirror joint tool, making sure that mirror across YZ is selected. YZ is the plane that passes through the center of the character. We want to search for L and replace that with R. So open up our hypergraph and delete the IK handle and effector. I like creating those fresh once I've mirrored. Reactivate our IK handle tool and create a right side IK handle. Rename all these nodes. Rename our effector. So now we have our IK handles for both the legs. So we can see here that as we move it up, we get a twist on the pole. It's nothing drastic, but our next step will be to create locators that we'll use as pole vector constraints. So we can do that by selecting Create Locator. Creates a locator, and let's rename it. Now, one tricky thing about the pole vector constraint is it will aim this arrow, the rotate plane, toward the object that is being constrained to, in this case the pole vector locator. So for instance, if this locator were pointing straight ahead, and we'll do that as an example. Just snap it up there. If we move it straight out, what will happen is the pole will actually shift the leg to point straight forward. Let's do that real quickly. Select the locator first, shift select the IK handle. Let's keep an eye on this leg orientation. Select constrain, pole vector. We can see our leg shifts because our pole arrow has reoriented itself to point at the locator. So it's very important that we actually position and orient this locator in the proper position. So one way that I found of doing that, switch to the hypergraph, selecting the beginning and end of the IK leg joint, shift selecting the locator and creating a point constraint so that the locator is constrained midway between the beginning and end. Then I select the first knee joint or the second joint of the IK leg, shift select the locator, then create an aim constraint along any axis, and I'm only using the scene up. I'm not using an object. Hit add. I can delete these two constraint nodes, select our locator, and then translate it out, in this case, on the x-axis, which is the axis that I use to aim at that knee joint. Translate that locator out. If the locator is selected, shift select the IK handle. Let's keep an eye on the IK leg. Select constrain, pole vector, and we get no shifting in the IK leg. Now with that done, I can select this locator. We can see that the pole will always point toward this target. So that's how we control the swing of the leg. Though we still have access to the twist attribute on the IK handle. Let's repeat that process with the right leg. I'm going to create a locator, rename it. Yeah. Let's capitalize the V here. Select the first joint and last joint of the leg IK. Shift select the locator create a point constraint, select the second IK leg joint or the first knee joint, shift select the locator, create an aim constraint, delete both of those constraint nodes from the locator, select the locator, translate it out in X in this case, the locator selected, shift select the IK handle, then select constrain, pole vector. Once again, no shift in the IK. So now we can hide our local rotation axes. Select all the IK leg joints, display, component display, local rotation axis. Select our right leg locator, move to a side view, and translate it in X so that it's more or less aligned with the left pole vector, just as an act of cleanliness. So now what I'm going to do is create hip joints, and I will repeat this hip joint process in the next tutorial where we'll create a different type, slightly different type of IK leg. But once again, I like you to be able to go to any chapter and it will be complete, not having to refer to other chapters. So I'm going to display our model, go to template mode, and I've mentioned this before, but for mirroring weights, it's advisable to not have joints, left and right joints, running down the center of a character. They should be offset slightly. It's going to create a 1-degree curve, the point snap tool, click on the end of the pelvis, and then the end of the IK leg, or the beginning of the IK leg. Hit enter and deactivate that tool. And with the curve selected, display the CVs. Now I'm going to turn off all objects in the selection masks and then activate only the curves. Go to component mode, switch off local rotation axes. Select the first CV of that new curve that we're going to use as the guide for our hip joint. Switch to a front view and shift it out slightly. That should be fine. I'm going to use this to draw joints to, and just snapping the joints to the CVs of that new spline. Activate the joint tool, activate point constraint, and hit enter when you're done. Deactivate that tool. Display my hypergraph and frame on the selected joints. Select them both. Display their local rotation axes. So I'm going to orient the end joint to match its parent, selecting the end joint, skeleton, orient joint, and I know that it's set to none from the previous orientation that I did on the IK leg. And select both of them, and we're going to rename them. Change joint to hip, and then add the underscore J and T suffix. And delete that spline. Let's turn on all of our selections. I'm going to switch to component mode, reactivate our local rotation axis, and select both the local rotation axes of this hip joint. I'm going to want it to point more or less forward. So with the local rotation axis selected, click on the rotate tool, switch to a top view, and then rotate in Z. That's a quick manual rotation here. I'm basically rotating until the Y forms a straight line. Let's hit the plus arrow. And here you can see a little aliasing or jaggedness in that Y-axis. So you want to get it as straight as possible. Once again, you could use a locator or the aim constraining process that we'll use later to help with that. Okay. Switch back to object mode. We can hide our local rotation axes. Now we can select our left hip joint and mirror it to the right side. Let's test our rotations. So there's scissoring in opposite directions. Now we can parent both of these hip joints to the end of the pelvis. And then parent our IK joint. Let's go to the hypergraph here. To the end of the hip joint. Select the child parent, hit P. Let's do that for the right side. Select the IK joint first, end of the hip, and parent. So now I'm going to select the pelvis. Activate our translate tool. So we can see everything is hooked up as we need it. So the next thing we want to do is I'm going to select this IK handle and translate it up. And so we can see it's starting to flip at this point. Let's move it forward. Let's go to a side view and we can see that what I'm trying to say more clearly. If I translate it up, as the end of the IK handle passes the pole vector, the knee or the IK solve starts to flip. So what you can do is we're going to create controllers and constrain the IK handles to those, and then parent the pole vectors to the leg controllers. So I'm going to use just a NURB circle. Hit apply and create so that we have two of them. Let's rename them. NURB circle. Okay, give it a underscore CTL suffix. Let's give this one a right side designation, change that to 1, and controller suffix. Let's increase their radius by selecting the make node, upping that to a radius of 2. I'm going to select each one successively and then group it to itself. Group, and hit G to group this. If I hit the translate tool, I can see that the orientation as well as the position of the group node matches the controller exactly. So I can use that as a positioning guide, a way to position the controller and still leave the transform values at their default. So I'm going to select the IK handle, shift select the group node, just point constrain it to quickly move it into place, and repeat that for the right side. I can delete those point constraint nodes. Let's rename these. Change it from group. Let's give it an underscore GRP suffix. Change this to right side. 01 underscore GRP. So now we can constrain our IK handles to the leg controllers. Select the controller, shift select the IK handle, and point constrain. and repeat that process for the right side. Now the last step will be to parent the pole vector to the controller. Select the child, shift select the parent, P, child parent P. So now when I select the controller, let's move to the side view. The IK handle, or the pole vector constraint, travels with the leg controller so that the end of the IK solver never moves past the pole vector. So it's only when the end of the solver moves past the origin of the solver that you start getting a flip in the knee. So it helps stabilize the leg, the pole vector constraint, as well as give you additional knee swing. But then of course you still have access to the twist attribute. So I'm going to add an attribute to the controller, a knee twist attribute, so that we'll be able to control the entire leg by making that one selection. So I'll select that, click Channels, Add Attribute, give it a name of knee twist, make sure it's a float value, and set its default to 0. And then click Add. Repeat that for the right side controller. Give it a default value of 0, hit OK. Now I'm going to simply connect the twist value of this attribute to the twist attribute on the IK handle, and they're both set at 0, so they'll correspond precisely. I'll select our left leg controller, open up the connection editor, and load that into the outputs. Scroll down to the bottom where new attributes are created. Select the IK handle, load that into inputs. Shrink this down a bit. And scroll down until we find twist, the twist attribute. So here, I'm going to connect knee twist to twist. So we can see now that there's a connection going into the twist attribute on the IK handle. So when I select the leg controller, it's connecting in and driving the twist attribute on the IK handle. Let's repeat that for the right side. Open up the Add Attributes. Connection editor. We've already done that step. Scroll to the bottom till we find our added attribute. Load our IK handle into the inputs. Find our twist attribute. Simply connect the two. So there we have a pretty standard rotate plane IK leg with a broken knee, or split knee, using a pole vector constraint to help not only stabilize the leg, but give additional control to the swing of the knee. So in the previous lesson, we built an IK leg with a pole vector constraint. One thing we did, although we precisely aligned our pole vector constraining locator, we sort of eyeballed the local rotation axes on those leg joints. We had a locator as a guide, and they were aligned pretty well. What we're going to do in this lesson is we're going to build an IK leg joint and then use an aim constraint to get more precise control over the local rotation axes of this leg joint. And then once we build that, we'll create a rotate plane IK handle, and we're going to create an IK which, even if we rotate this leg 360 degrees about the waist, the IK handle will not flip. And we'll do that in a way where And I've seen this done where when the joints are drawn from an orthogonal view, what I mean by that is if you switch to a side view and draw your joints, your leg joints will be flat on the YZ plane. What we're going to do is we're going to figure out a way to do that on a non-orthogonal leg joint. So here we can see we have our knee out to the side. It's not on a flat plane. So we can't rely on a 90-degree rotation once we adjust our pole vector. And I'm doing this because quite often we'll find ourselves rigging characters that don't have leg joints built on orthogonal planes, not straight along one of the viewports. So in this case, we'll figure out a way to do it in a way that will work on all cases for whatever the orientation of the leg is. Okay, so first here we have a guide spline for the shape of the leg. We're going to create a 4-joint chain. So we'll activate our skeleton joint tool, activate our point snap, and then snap a joint node onto each CV of this guide curve. Hit enter once we've drawn the last joint, and deactivate our point snap. And let's open up our hypergraph, quickly rename these joints, modify search and replace names. So we're going to search for string joint and replace it with cave01 L leg 0, and then add IK to the end of each of these. Okay, so once we have this, then we're going to start aim constraining each of these so that we can align their local rotation axis. So with all these joints renamed, let's select all of them and then display their local rotation axes. Display, component display, local rotation axes. Okay. So now we're going to create a locator. We're going to use this locator as an up vector object for our aim constraint. So select create, locator. We'll simply name this up. And with that locator still selected, activate the translate tool, hold down V for point snap, and then snap it up to the top leg joint. And then just translate it out to the side. So now we're going to unparent the second IK joint from the first. So next we're going to aim the first leg IK joint toward the second. But before we do that, we're going to zero out the joint orient channels. So with that first leg IK joint selected, open the attribute editor. And here we see the joint orient channels. We're going to set all of these to 0. Okay, so you can see our joint has shifted so that it matches the world coordinate system. Once again, there are MEL scripts out there that will automate this process, but the goal here is to explain it to you in detail so that if you're ever asked to write your own MEL script for this or debug a MEL script, you'll understand exactly what's going on. And it's a fairly easy process and is actually a preview for how I orient joints in the build scripts that I show in our lessons. Okay, so with that done, we're going to select the leg 02 IK joint, shift select the leg 01 IK, and then select constrain, aim. So open up our option box. So we're going to leave our aim vector at 1 since we want our x-axis to point toward each joint. So this x-axis will point toward leg 02 IK and so on. Our up vector, I'm going to leave it at y, the default, since I like my y-axis to point out to the side. But once again, you can change these values to what works best in your pipeline. For world up type, we're going to use this up locator. So we're going to change it from vector to object up. And then in the world up object text entry field, simply type the name of the locator, in this case up. hit add. Okay, so now we have our aim constraint. And with our up vector locator, we can translate it back and forth to twist the orientation of this joint along the x-axis. Let's display our model here. Let's twist our joint here. Okay. Let's say this is the orientation that we want for our first leg IK joint. We'll select this aim constraint node and delete it. Select our leg 01 IK and open the attribute editor. So now what we're going to do is we're going to copy each rotate channel value and paste it into the corresponding joint orient channel. So for instance, the rotate X value we'll put into the joint orient X channel, and then once all three of the joint orient channels are set, we'll set the rotate channels to 0. Okay, so let's start typing these in manually. So the first one, 19.404. Once again, all these values will be different based on your character and the orientations that your joints are at. Okay, so now with that done, we have matching values in the joint orient. We're going to set all of our rotate values to 0. So you can see the joint has reset itself to the orientation that we aimed it at. And then we have clean rotate channels. So with that done, now we're going to aim the second leg IK joint to the third. So we're going to select our up vector locator, holding down V, snap it to our second leg IK joint, translate that locator off to the side, unparent the third IK leg joint from the second, select our second, open up the attribute editor, and set all the joint orient values to 0. Now we're going to create another aim constraint. From the third IK joint, I should select the second leg IK joint, constrain orient. You can use the same values. Select our up vector locator, show our geometry here, translate it back until we have the orientation that we want for our knee, first knee joint. Okay, let's open up our hypergraph, delete the same constraint, select the leg 02 IK. Once again, copy the rotate values into their corresponding joint orient channel. So let's do this again manually. So you can see this is a pretty straightforward process, something that's definitely suitable for MEL scripting. Okay, so now we can parent our leg 02 IK to our leg 01. Still have clean rotate channels. So now we're going to unparent our leg 04, and we can simply, rather than aim constraining, since I'm going to want the local rotation axes of this third IK leg joint to match the second, we can just parent the third IK joint to the second, and then use our joint orient tool to set that so that it has no orientation difference from its parent. Select this locator. So we'll select the third joint once it's a child of the second, and then select skeleton, orient joint tool. We'll make sure that that's set to none, and click orient. So then our second joint has oriented itself to its parent. But if we wanted a specific orientation, if we wanted this to point directly toward this last IK joint, we'll go through that same aim constraint process. Show our locator again. There we go. Open up our attribute editor, set all of our joint orient values to 0. Point constrain our up locator to the leg 03 IK joint. Oh, Disable our point constraint here. Translate that locator out to the side, and then create our last aim constraint. Okay, let's get the selection correct here. Aim. Okay. Okay, say that's the orientation we want. Delete this aim constraint. Select the leg 03 IK joint. Copy the rotate values into the corresponding joint orient channel. And zero out our rotate channels. Parent our leg 03 IK to our leg 02 IK. Then for this last joint, we can simply parent it and set its joint orient to none. Okay, we can get rid of that up vector locator. Okay, so there we've used aim constraints to precisely align the local rotation axes of our leg joints. So in this next part, we're going to create a rotate plane IK handle and then set it up so that we have a no flip leg without using a pole vector constraint, but on a non-orthogonal leg joint. So we'll need to figure out a way to precisely, once we've altered the pole vector values, it will flip the leg, and we need to figure out a way to precisely reorient it back to its original position. Okay, so let's start by building our rotate plane IK handle. We'll select skeleton, IK handle tool, option box. Make sure our current solver is set to RP, or rotate plane. Click on the first leg IK joint. Click on the last. Rename our new IK handle. It's K01 L leg 01 underscore IKH. Then rename the effector K01 L leg 01 underscore EFF, or effector. Delete that spline. So now we're going to create a pole vector constraint. We're going to use that to realign this leg after we've altered its position, once we've changed the pole vector values for this. So we're going to create a locator, and then point constrain the locator to the first and last leg IK joints. So select the first and last joints, shift select the locator, and then select constrain point. And now we're going to aim constrain this locator to the third IK leg joint. Select that, shift select the locator, constrain, aim. We don't have a world up object, so we'll just use vector and then add. It doesn't really matter which axis we're constraining here. Delete these constraint nodes. Now let's select both the IK handle and the locator. Switch to a top view. So you can see that they are aligned to one another. There's the angle of the pole vector, which matches the angle of this locator. Okay, switch back to perspective. Now we can select that locator and translate it out on, in this case, X, the axis that we aimed with. So now, just as a visual guide to verify that our reorientation has worked, I'm going to select the leg 01 IK joint and duplicate it. Edit, duplicate. I'm going to collapse this and template it. So display, object display, template. Once again, this is the duplicate. that we're turning into a template. We're just going to use that to verify that our leg has been properly realigned. So now I'm going to create one more locator, create locator. I'm going to point and orient constraint this locator to the leg 01 IK joint. Let's just select the locator, constrain point, constrain orient. So now I'm going to select the IK handle, and we can see our pole vector is pointing at this angle presently. In order to get this no flip leg to work, what we're going to do is we're going to choose sort of an axis that will apply the no flip to. So in this case, it will be the side view of the character. So what we're going to say is, no matter how we rotate along this perpendicular plane, basically pointing out to the side from the hip, this leg will not flip. And the reason it won't flip is because rather than having the IK handle pass its pole vector, the pole vector will be pointing out to the side of the character, so the IK handle will be perpendicular to it. It will never pass it, so it won't ever flip. You can sort of think of it as this IK leg forming sort of like a wheel, and the pole vector will point straight out, sort of like a spoke on this wheel, or the like the hub that it's attached to, the drive shaft sort of. So it won't ever pass it because one will be perpendicular to the other. And that's what causes an IK flip when the end of the IK handle passes its pole, or the origin of the IK handle. So in order to get this to work, we need to select the IK handle and select the pole vector X, once again based on the scene coordinate system, the world coordinate system. We're going to set the X to 1, the pole vector Y to 0, and the pole vector Z to 0. So there we can see our IK leg has been twisted off of its normal axis. So now what we need to do is we need to select the locator that we have point and orient constrained to the top of the joint and record the rotate X value. So I'll just open the script editor and just type in negative 88.231 just so that we can remember it. So now we're going to use the orient constraint to reorient the leg back to its original position. So select that locator, shift select the IK handle, then select constrain pole vector constraint. Sorry, I may have said orient constraint earlier. I actually meant pole vector constraint. So now let's select the locator that we point and orient constrain to the top of the IK leg joint, and then make another note of its rotate X value, which is negative 18.281. Let's open up our script editor, type that in. So what we need to do now is we're going to delete the pole vector constraint. Okay, select the pole vector constraint node and delete it. Select our IK handle and reset the pole vectors back to 1 on X and 0 on both Y and Z for the pole vector. Now we're going to select the IK with the IK still selected. Select channels, add attribute. We're going to create an attribute called knee twist. We'll leave it as a float data type and simply set its default value to 0, not specifying a minimum or maximum. Then hit OK. So we have this new knee twist attribute. So now what we need to do is subtract the second rotate X value after we pole vector constraint, the IK leg, we need to subtract that from the original rotate X. I have a calculator program here, so we're going to type in 88.231 minus 18.281. That gives us 69.95. So we're going to set our twist to this new value, 69.95. You can see our IK leg has realigned itself. It's laying directly on top of the templated leg. So now what we need to do is we want to give animators access to this the twist. What we're going to do is we're going to set up a node connection so that we'll be able to use this zeroed knee twist attribute to actually affect the IK handle twist attribute. So we're going to use a plus minus average node to do that. What we're going to do with that node is we're going to feed in the knee twist value and then subtract this value, the 69.95, from that value, and then connect that into the twist attribute. Let's open up our script editor. Type in create node plus minus average minus name flag. Call this cave01 L leg IK underscore PMA for plus minus average. Select this mel, hit enter. With the plus minus average node selected, open up the attribute editor. We're going to set the operation from sum to subtract. Okay, so now let's open up our connection editor, window, general editors, connection editor. Load our plus minus average node into the inputs, select our IK handle, and load that into the outputs of the connection editor. And scroll down to the bottom until we see our knee twist attribute. Let's open up our script editor here. Let's edit, clear out the history. We're going to connect the knee twist to the input 1D. What these inputs mean on the plus minus average, you can sort of think of them as dimension. A one-dimensional array, two-dimensional, and three-dimensional. Since our knee twist attribute is a single float value, we only need to input it into the 1D input because we only have one float value. So select the knee twist. You can see the other two have grayed themselves out. It knows that you cannot connect this to the 2D and 3D inputs. And so we'll connect the knee twist into the input 1D. So we're going to select this line, this mel output, and copy and paste that into the script editor. Let's expand this window a bit. So now we're going to edit this line of mel, which is output from that connection. We're going to change it to set attribute, get rid of the minus F, cave01. So we're going to set to set attribute cave01 L leg IK underscore PMA, and change it from an index of 0 on the input 1D to an index of 1, and then type in the value we're going to set it to, which is negative of the twist attribute value, in this case negative 69.95. So select that, hit enter. So you can see that we've set the attribute to negative 69.95. Let's select our plus minus average node in the channel box, load that into the outputs of the connection editor, scroll up to the top. With our IK handle still selected, load the IK handle into the inputs of the connection editor. So we're going to connect the output 1D to the twist of the IK handle. So we select the IK handle. So now when we select the knee twist attribute, which is set to 0, an animator will have access to the knee twist and still have a zeroed out animation attribute. So now let's test this no twist here. Select our IK handle. There you can see, because our pole vector is pointing 1 on X, we can rotate this leg completely around the hip and we won't get a flip on the IK. So once again, that's creating this no flip IK leg on a non-planar leg, which is something that's quite common. You will often get characters that don't have their legs drawn in a straight line, and this is a way of creating this type of rig on any type of orientation for a leg. And we also covered using aim constraints to precisely affect the local rotation axes of your joints. Once again, there are scripts to do that, but this is just showing what's going on in detail so that you can understand these scripts and write them yourselves and be able to troubleshoot such situations. Okay, so now let's start building our stretchy IK leg here. The first thing we need to do is a way to measure the distance from the beginning of the IK leg to the end. So we're going to do that by creating a distance dimension node, or distance measure. I'm going to switch to a front view, zoom in, and then select Create, Measure Tools, and Distance Tool. Select the tool and click twice in the viewport, and then hit Enter once you've clicked your second time. Switch back to the perspective view. Let's open our hypergraph to see what we've created. We've created 2 locators and a distance dimension node. Now, the distance dimension node measures and displays in the viewport the world space distance between these 2 locators. So now let's go about renaming all of these. Give it a dist suffix for distance. Select our 2 locators. Modify search and replace names. Change every instance of locator our standard naming convention, and then give each of them an underscore LLC suffix. Okay, so with that done, now we need to point constrain each of these locators to the beginning and end of our IK leg. So we'll select our Lego 1 IK joint, the first joint, shift select the first locator, select constrain point to create a point constraint. Now the initial thought would be to point constrain the second locator to the last joint of the IK leg. But unfortunately this would create a cycle, and that's because the scale of the IK leg joints depends on the position of the second locator. But if we constrain that to the end of the IK leg, the position of the second locator will then be dependent on the scale of the IK leg joints. So we're creating a cycle where they're each dependent on each other. So in that case, we can use either the IK handle as a constraining object, or my choice will be using the actual leg controller, but either will work perfectly fine. So I'll shift select the second locator and create another point constraint. So now it's a little hard to see here on my monitor, but if I select the foot controller, and as I move the foot controller, the locators will change their relative distance between each other, the world space distance between each other. So you'll see the distance measure value update in the viewport. So that's how we'll measure the distance of the leg. So now with that in place, we can open our script editor and begin creating nodes.
The first is what will be a multiply divide node. Let's give it a name, matching our standard naming convention. Create the node. So we'll go Window, General Editors, open our connection editor, and load our multiply divide node into the inputs and expand our input 1. Now we're going to connect the distance into the input 1x. To do that, we can open our hypergraph, select our distance dimension node. But actually, this node doesn't give us access to the actual distance attribute. What you need to do is we need to select the distance dimension node and hit the down arrow once to select the shape node. And we load that, the distance shape, into the outputs, scroll to the bottom, and we see a distance attribute. So that we want to connect into the input 1x of our multiply divide node. So now we can see that 10.658, which is a rounding off of this value, but it actually has the full float value connected into that input 1x. Now we're going to divide that into the total length of all the IK leg joints. And we can get that by looking at the translate x, which gives us the distance from its parent. So here we have 7.09, the second is 0.656, and the last is 4.741, which I know offhand to actually it equals 12.487. So you can use the simple calculator program to determine this value by adding up those three translate x values. So now we're going to create a second node here, a condition node. Let's spell it right. Spelling dyslexia today. CND for condition. Okay, with that node selected, you can open up our connection editor once again. And also, while this node is still selected, I'm going to open the attribute editor and make sure that our operators change from equal to greater than. Let's load that condition node into the inputs. Let's open up all of our tabs here. So what we want to do, our first term gets compared to our second term to determine the truth or falsity of this condition. Our first term will be the distance measure. The second term will be the total length of all the IK leg joints. So we already know that the second term is going to equal 12.487. Then we're going to select our distance node, hit the down arrow once so that the shape node is selected, and load that into the outputs of the connection editor. Scroll to the bottom, connect the distance into the first term of the condition node. So now we need to make the connections into the color if true or false. We're only going to use the R value since we're only concerned with we're only going to output an X value for the scale X. So first I'm going to load the multiply divide node into the outputs. In the output X, if the length of our distance measure is greater than the total length of all the IK leg joints, that means that our leg has been extended to its full extent, and then it starts moving beyond the length of the combined length of the leg joints. So if that is true, if this is greater than the initial total length, we want the output of the distance, which will then be greater than the length of the leg joints, divided by that initial leg distance. We want that output of the multiply divide node, the output x, connected into the color if true r. Otherwise, select the condition node again. We want that to be 1, since this will be the scale value. So I can see here by looking at this, our color if true, we have a pretty large value here. So I'm guessing our multiply divide node is still set to multiply. Let's select that node, open up the attribute editor, click on the multiply divide tab, and change it, the operator, from its default of multiply to divide. Click back to our condition node, and there we can see we have a value just below 1. So now with our condition node selected and that problem fixed, we're going to load our condition node into the outputs, expand our out color, and one by one select each of these joints and load them into the connection editor, and then scroll to their scale X value. And then connect the out color of the condition node, the out color R, to the scale X. Let's do that for each of the IK leg joints. It isn't necessary for the last joint. So here we can see that because the distance is not greater than the total length of all these joints, we're using the false color value, which is 1. Let's test this quickly. Still have a scale of 1. But if we move it beyond its original length so that this value is greater than the 12.487, then we get larger scale values in the IK leg joints. Set this back to 0. So there we've created our first stretchy leg. Now this can be pretty easily scripted. We'll repeat it once again on the right side so we can go over it once again a little more quickly the second time and get the gist of what we're doing, and hopefully it'll be a little more solidified with the second attempt. Okay, so now let's quickly build the stretchy IK on the right leg. We've been through the process once before, so I'm going to go a little more quickly here. Switch to the front view. Reactivate our distance tool. Click twice and hit enter. Go back to our perspective view. Select these two locators and rename them. Open up our hypergraph and frame it. Leave the same information in there and just change it from L to R. And give it both of these an underscore LOC suffix. I'll rename the distance dimension node itself. Now for the point constraining, first joint and the first locator, create a point constraint. The foot controller, second locator, I'm going to hit G to activate the last used tool, which is point constraint. So I'm going to create our multiply divide node, and I've already have these values exist in my script editor, so I'll just change the L to R. Up our attribute editor and change that to divide, something we almost forgot to do last time. Open the connection editor, load that multiply divide node in. Connect the distance attribute. Connect that into the input 1x. Then set the input 2x to the total length of the IK joints. This is 12.487. I'm going to create condition node. Once again, just changing the L to R. Load the condition node into the connection editor. Open the attribute editor and set that node to greater than. Taking the distance, connecting it then to the first term, and putting 12.487 into the second term. Select our multiply divide node and connect that output X to the color of true R. Select our condition node, load it into the output, then connect the the scale X, of each of these joints. Connect the output of the condition node R to the scale of each of these IK joints. Let's test what we have here. Okay, so we have both of our legs set up to allow for stretchy IK. So in this lesson, we're going to go over one more example for using MEL to build rig components. In this case, we're going to build a stretchy IK leg. I want to point out that we're using the same type of input components to build this leg. There are several different ways to do this, and over time we hope to post some of these new methods on the Fahrenheit Digital website. But for now, we're going to remain consistent and use the same locator-based rig building. Let's switch to template mode. Let's quickly position this leg rig. How this works is there is a top node that's used for global translation and rotation. We're not using any scale on any of these build rigs. Let's move it into place. Switch to a side view. Now let's rotate it. Switch to a perspective view. Rotate it out. In this case, we're trying to get the ankle more or less aligned to where that's going to be. Then we're going to swing the knee out. Next, we're going to deal with the knee by selecting a selection handle for the knee position, moving to the translation, switch to a side view here. And we'll position that knee node. Then here I have an attribute called knee offset, which allows us to change the position of our broken knee. I'm going to straighten those out a bit. And the last component is the ankle position. Move that down to the ankle. Switch to perspective view. Double check all this. Let's swing the knee out just a little bit more. Let's open up our hypergraph, see what we have in the scene, and then let's take a quick look at the script. So once again, we're using the same procedure to create and name the joints based on a suffix and the position orientation of the input locators. And here are the switches we have for this global procedure. We're first building the joints and then arranging them into a hierarchy. Then I'm building the IK and then setting up the stretchy IK connections. Once again, this will be available for you on the DVD and for download on the Fahrenheit Digital webpage with quite a bit of documentation explaining every step in detail. Let's close this. I have a button up here. Here we have our leg built. Let's hide our build components. Let's turn off our geometry. Select our IK handle. And as with the manual stretchy IK,
It retains its normal scale when compressed, but when expanded, once it reaches a point of hyperextension, then it will stretch. We also have a pole vector constraint built. Let's unhide our build rig, and we can see that we have a pole vector locator as well. So we have another example of building a rig component using MEL, in this case, the stretchy IK leg. In this lesson, we're going to build the fingers manually for this character. We're going to actually use a series of 1-degree splines as guides to snap our joints to, but we're actually going to go one step prior to that and create a series of clusters at each knuckle, and then use those to snap the CVs of the spline to. Let's start by using the edge loop tool to create the clusters on the knuckles. So we're going to start with the index finger here. Select the geometry, then select Edit. Select the edge loop tool. You double click on the edge, which selects a ring or a loop of edges. Then we're going to hit Q, exit out of that tool, switch to the modeling module, and select Edit Polygons. Selection, just tear that menu off. We're going to convert this selection of edges to vertices. So with that done, switch back to animation, then create a cluster by selecting Deform, Create Cluster. Okay, so there we have a cluster that's centered on that selection of vertices. Let's repeat that. Let's hit Y to reactivate the edge loop tool. Let's find this knuckle, double click, have our edge loop selected, hit Q to exit that tool, convert selection of vertices. I'm going to tear off my recent commands menu, something that you can do on the Mac OS X Maya, and create a cluster. Just repeat that process. Okay, now for the last cluster here, we're just going to select a couple of these vertices here, and then just create a cluster. Okay, so we're going to actually extend this joint back into the carpals, or back into the wrist. So I'm just going to select this vertex and create a cluster, and we'll reposition that later. Okay, let's do this once again for the middle finger. So here we're going to have to create a couple of edge loops, one for the bottom and one for the top of that first knuckle. Let's do that again. Okay, create our cluster. Let's repeat this for the next knuckle. Okay, and then the fingertip here. Select a couple of vertices. Okay, so there we have our clusters. Okay, so I'm going to cheat here a little rather than go through this whole process. Switch back to object mode. I've actually created the splines for the other fingers here. So actually going to, oh, we need to create one more cluster, I'm sorry. We'll follow that edge back. Okay, create that last cluster. Okay, so now we're going to draw a couple of splines here. We're going to select Create, CV Curve tool in the option box. I'm going to make sure that the degree is set to linear. Then activating Point Snap, we're going to start at the tip and then go back to that first cluster, open the attribute editor, And in component display, display the CVs of that curve. Let's repeat that with the middle finger. Okay, we can deactivate the point snap. Select all the clusters here and delete them. I'm going to display our high-res hand here. Switch to component mode. We're selecting CV or vertex components. We're going to reposition these first CVs so that they're positioned in the center of the mass of the carpal or palm of the hand of this character. Okay. Okay, so with that done, let's hide our geometry here. Then we're going to switch to drawing joints. So we're going to select skeleton, joint tool, reactivate our point snap, and simply start clicking joints. Okay, hit enter. Open up our hypergraph. Let's quickly rename this. Actually, let's do one thing here. We'll select all the joints and display their local rotation axes. Reorient the last joint so that it matches its parent. Hit skeleton, orient joint. Make sure the orientation is set to none. And we're going to unparent the second joint from the first, and then duplicate the first joint. Now this duplicate has the same position and orientation as the first joint. So we're going to select the first joint, shift select the second joint, select the duplicate joint last, and create a point constraint. The reason we're doing that is that's a quick way of creating a second carpal joint or palm joint to get a little bit of extra flexibility in the palm area since he has such a large hand. And it will average its position between those and still retain the orientation of its parent. Okay, so with that done, now we can select all of them and rename them. Modify, search and replace names. So we're going to search for joint and replace with our standard naming convention, in this case Cave01, L index, I'll just put 0. Okay, so we're going to add underscore JNT to each of these. The second one, we need to renumber it as well. Oops, accidentally hit a caps lock here. Let's go in and correct this. Okay, and just go through this chain, renumbering and renaming all of these joints. Just can't quite spell JNT. Let's get this right. Okay, and we'll just name this 06 end. Okay, let's repeat that process, or before we do actually, sorry. Let's switch to turn off our point snap, switch to component mode, and activate our question mark icon, which is local rotation axes. Let's go in and just shift, select each of these. Display our hand there, and activate our rotate manipulator. We're going to rotate so that Y points out to the side of the finger. So we're going to be rotating on Y. What I like to do is get close to a front view here and then rotate so that my Y-axis is sort of parallel to one of the edges. Okay, so now let's repeat that with the middle joint. Reactivate our joint tool here, point snap. Okay, display all of our local rotation axes. Let's duplicate this first joint. Point constrain it to the first and the second to average its position. And reparent all this. Let's orient that last joint. Once again, that's just a precaution. It's not something that needs to be done since we're not going to be skinning to it. It's just a habit I have of doing. Okay, quickly go in and rename, modify, search and replace names. I'm going to change this to middle. Let's go in and rename them. So here at underscore JNT. And change the numbering and name on all the subsequent middle finger joints. So once again, as with the toes, this appears to be a fairly tedious process, but I'm talking through this, and if you were to concentrate, and have the anatomy of your character well in mind, it's a process that can go fairly quickly. Once again, not only am I trying to go through this and explain all the steps, but also talking through it slows it down a bit also. Let me select these local rotation axes. Activate our rotate tool. Make sure our point snap isn't on. And then rotate so that the Y sort of lines up with one of these edges. Okay. Okay, back to our joint tool and our point snap. Create our ring finger. Okay, unparent the second from the first. Select and duplicate the first joint. We're going to point constrain this duplicate joint to the first and second to average its position. Delete that point constraint node and reparent it all together. Select them all, display their local rotation axes. I'll just reorient this last joint and go in and quickly rename them. So this is our ring finger. Set our JNT suffix and correct the numbering. Okay, let's go in and correct these local rotation axes. Okay, just shift select each of them. Let's display our model here and show our rotate channels, rotate manipulator. And rotate this so that Y is, more or less parallel to one of the edges on the model. Reactivate our joint tool, activate our point snap. Let's draw the pinky joints. Okay, once again, I'm going to unparent the second from the first, duplicate the first. I'm hitting Command D. We're going to select the first and second, shift select the third, create a point constraint to average the position. Delete that point constraint and parent it all together. Okay. Local rotation axes. Orient the last joint. Skeleton orient joint tool. Now let's rename. So this is our pinky. Go in and add the suffix. think we may not have averaged this position here. So let's create our point constraint again. Let's delete that. Okay, now we have our averaged carpal joint. So now we can go in and edit these local rotation axes. Once again, this is rough editing the local rotation axes. We're going to go in, once all these joints are built, and finesse them, particularly in the carpal area. Let's reactivate our joint tool. Holding down V this time to activate point snap. Okay, there we have our thumb joints. So here, although we're going to duplicate the first joint, we're not going to average its position for the carpals. We're going to use it to create a joint that more or less points toward the index finger, and we can use that to pivot the base of the thumb in so that the tip will sort of move toward like a cupping position where you can swing the thumb over so that it touches the pinky. Let's unparent this. Duplicate that first thumb joint. Okay, let's reorient the last. Let's quickly go on and rename these. These are our thumb joints. Rename that. Quickly add that JNT suffix. Okay, so I'm going to unparent all these and hide them real quickly. And select the first thumb joint and open the attribute editor. I'm going to zero out all the joint orient channels. So we have clean values, because what I'm going to do is actually aim constrain this joint toward the pinky joint, and then take all those rotate values and transplant them into the joint orients, and then zero out the rotates. So we'll create a locator here. We'll call it up. We're going to parent the, or actually just point constrain the locator to that first thumb joint. Okay. We'll move the thumb up in Y. We're going to select the first index finger joint, shift select the thumb 01 joint, and then create an aim constraint. Constrain, aim. Let's open the option box. So we're going to aim the X vector toward the index finger joint. We're going to leave the up vector at Y. Our world up type is object, and our world up object is the locator named up. Let's add. So now we can use this locator here to reposition the y-axis. So we're going to swing on X and have our Y pointing upwards. Show our model here. Switch to templated mode. Okay, so the important axis here is actually the x-axis. So we can delete this aim constraint, delete the locator. So now we're going to select that joint and open the attribute editor. So all of these rotate values, we're going to need to transplant them into the joint corresponding joint orient and then zero out the rotation channels. Okay, now zero these out. Okay, so we have zero rotate values. We still have the orientation change that we just put in there. Open up our outliner and find these hidden joints. Okay, so let's unhide them. Let's rebuild our graph editor. So now we'll just parent them. Actually, before we do that, we're going to reorient these joints, switch to our component mode, select all these local rotation axes. Display our model, activate our rotate tool, okay, swing this rotate all the way around so that Z is pointing downward as it is on all the other fingers. Okay, so now we can untemplate this joint and parent everything together. So now I'm going to select all of the joints except for the first two carpal joints, which are the first two joints in each of the fingers, and turn off their local rotation axes display. So that way we can focus just on these carpal joints, as I like to call them. Okay, so we're in template mode. I missed a couple of these. Okay, so we're just going to go in and finesse these where we need to. Okay, we'll start with the index here. Okay, so angle that to, basically what we want to do is we want to create sort of a arc with the local rotation axes of all these carpal joints, which are the first two joints of the fingers. That way when we rotate them in, the goal is to sort of have them all sort of converge inward. Okay, this actually looks pretty good. So we can quickly test this by just drag selecting over these joints. You don't need the last joints. Doing a quick rotate. So you can see we probably want to go in and adjust the pinky local rotation axes. Okay, let's do this again. Okay, a little more adjustment on the pinky, this first joint in particular. A little bit on the second. So the goal is to basically just have all the finger joints in a very gross manner when they're all multi-selected. Just sort of curl in and more or less just work together. Okay, so there we have our finger joints. Now what we're going to do is we're going to select the end FK joint of the left arm. We're going to do that by typing in select cave 01 L arm 04 underscore END JNT, and then selecting edit duplicate. So we're going to rename this from a duplicate of 04 arm joint to wrist 01 underscore JNT. Actually going to select that 04 wrist joint and rename that to END. So we don't want to skin to that actually. Repeat that for the right arm just to make sure. Okay. So now what we're going to do is parent each of these joints to this new wrist joint. So select the thumb first, shift select all the other fingers, just the first joint, and select the wrist joint last, the parent of all of them, and hit P. Okay, so now we have this new wrist joint with all of the finger joints. So now I'm simply going to select the wrist joint and mirror it over to the right side. Do that by selecting Skeleton, Mirror Joint Tool. Let's open the option box. And we're going to mirror across the YZ plane, which cuts through the front of the character. We're going to mirror the behavior of these joints and switch from the left to the right side. Okay, so there we have our right side finger joints. Okay, so although somewhat tedious, we went through just using a series of guide splines and just snapping joints to manually build our FK finger rigs. So in this lesson, we're going to go over using a Mel script to build the fingers for this character's hand. So here I'm working in Maya in a split screen panel configuration here. And I have an HTML document loaded into a browser panel with the Mel script loaded. Once again, this is a document that's available to you with all of the Mel build scripts that you can work this way, where you have the script loaded into one panel and just follow along and read through all the documentation to see what's going on in that script. Okay, so let's look through this briefly. It works pretty much the same as the clavicle build script, but let's look through it once again. You can see there's quite a bit of documentation. But basically, up here we have a procedure where we build and add a prefix to the joints based on the locator names, and then a prefix string that we pass into this procedure. So here, basically the way this works is we grab the position and orientation of the locators, record those values, and then use them to position and orient joints so that they match whatever the locator values are. And then once again, based on the locator names as well as a prefix string that we pass in as an argument, we rename all those joints as we create them. So here is the global procedure, FD hand build, which is the meat of the script. What we have here, we can see that we pass it a string prefix. So this is a string variable which will define the prefix of the character. Below that, I have a number of integer variables, finger build, fing hierarchy, and driven keys. And what these are, once again, these are switches. These are sort of subcomponents of this entire script, and by setting them to 0, which is off, or 1, which is on, I can execute portions of this larger global procedure at any given time. And once again, this helps with troubleshooting as well as giving you the flexibility of executing only certain portions of a build script at any given time. So here we can see in the finger build switch, this block of code, what we do is we select all of the transforms within our build group, record their names, and then for each of them we run them through a tokenize command so that we can extract out a portion of their name, and that's how we get the name of the a part of the name of the components from the locator. Then once we have that, we run the make joints procedure, where for each of the nodes or the locators that we've gotten from the build group, we add the prefix JNT. Okay. In this next switch, Fing hierarchy, we cycle through each of the digits and then parent them into a given hierarchy. Once again, this is explicit based on the number of joints that I'm using to build this hand. If you're building a finger with more or fewer joints, you want to go in and edit this for loop to change the number of digits of joints that it's looking for in each digit. And here we actually call the global procedure and then pass it the cave01 character string. But before that, there's one more switch here. Let me find that here. Oh, here we go. Driven keys. If this is enabled, what it does basically is it creates a duplicate for each of the JNT joints for each digit. Changes the uses the build procedure, the make joints procedure, but passes it SDK for set driven key as the suffix, and then builds a whole new series of joints and parents them so that they're the parent of each corresponding JNT joint. Okay, let's maximize this window, and I have the script, Mel script, loaded into the script editor. Exact same script. Just going to execute it. Makes these joints a little smaller so we can see what's going on here more clearly. Let's open up our hypergraph. Okay, so here's our index. We can see that for each joint we have not only an SDK, which is a set driven key joint, but also in the same location with the same orientation, a JNT joint. The reason this is you can add a number of poses to each of these SDK joints. For instance, if you wanted Fing curl, you could select each of those SDK joints, define a curl pose, and then the animator, let's say this is a curl set-driven key pose, the animator will still have each of the JNT joints where they can go in and layer animation on top of the poses that you will have built for them. Okay, so once again, pretty straightforward, and the script is there for you to use and modify and look through. So what we do at this point with the arm of the character in this scene, we would actually duplicate the last JNT arm joint, larm04 end, and then rename that to larm wrst01 underscore JNT and create a wrist joint. And that will have, because it's a duplicate, the same position and orientation as the end of the FK arm. And then we just simply parent each of these new finger joints to that new wrist joint. And then once you've done that, select it, mirror it over, and then you've created your right hand as well. So let's quickly run through that in a mock way. I'm going to switch to a front view. I'm just going to create a joint, and this will represent our wrist joint. Okay, so let's rename this Cave01L WRST01 JNT. Once again, it would be a duplicate of the end of the FK arm joint. So I'm going to select each of these and then use them to quickly repo this as a point constraint. Okay, delete that. Just reposition this just roughly where it would be. Okay, so there's our wrist joint, which in the final scene would actually be a duplicate of the last JNT arm joint. And the JNT arm, once again, is the arm that's driven by both the FK and IK arm joints. So what we do is we go in, do this in the hypergraph, and we select the top node of each of our new finger joints, shift select the wrist joint last, and then hit P or edit parent to parent them into a single hierarchy. So that will be our left hand. To mirror over to the right, we'd simply select our wrist joint and then select skeleton, mirror joint,
Let's reset this. So we want to mirror across the YZ plane, which mirrors from left to right. We want to mirror the behavior and search for every underscore L underscore and replace that with underscore R underscore, switching from left to right. Click the mirror key, and there we have our right hand. So in a subsequent chapter, what we're going to do is we're going to skip ahead a little and create a controller for the IK arm, and rather than using a NURBS object, a NURBS cube made of NURBS curves, we're going to use a different type of object, just another option for you to use. And then we're going to set up a local global switch for the orientation of this new wrist joint. So there is an example of using MEL scripts to build a finger with the SDK joints or set driven key joints so that you can layer not only finger poses but also allow the animator to layer animation on top of whatever poses you've defined for them. In this lesson, we're going to use a MEL script to build the finger joints for this hand rig. So here in the browser window within Maya, we have that MEL script loaded in as an HTML document. So you can see here we have quite a bit of commenting here explaining just about every line of MEL code within this script. And this again is a file that's available to you with this product. Let's quickly run through it. It's similar to the other build scripts that we're using. I'm trying to use the same inputs and the same standards for building rigs. So here we have a procedure which creates joints based on a prefix and suffix naming, as well as the position and orientation of a series of locators. Here we have the global procedure, which executes the bulk of the MEL script, and here's the string prefix that we pass to it, which is the prefix of the character, in this case cave01 for this particular character. We have 3 switches. When enabled, they will build the fingers, parent them into a hierarchy, and then create a series of duplicate set-driven key joints. And once again, I like breaking my scripts up into these switches to help me organize them into distinct blocks of MEL code, as well as to help me troubleshoot. If something's going wrong and it's a very long script, if I've broken it into the switches, into logical sections, then I can turn certain sections on or off, which will help me narrow down where a problem might be occurring. So here's the entire script, once again with quite a bit of commenting, explaining everything that's going on within the script. Let's expand our perspective view. And open up our hypergraph to show the inputs that are used to actually build this hand. So here we have the inputs for the index finger. And what we have are 6 locators, one for each joint in that finger, and these are for the carpals or the palm. You'll notice that they each have the same local rotation axes, with X pointing forward and then Y, in this case, pointing out. So what the script does is it takes the prefix string that we pass in the very beginning into the global procedure, and we'll add that to the beginning of each of these nodes. And it will use the position and orientation as well as the name of this node to build and name the joints. And then in the make joints procedure at the very beginning of the MEL script, we add a suffix to the end of the joint. So in the end, we'll have cave01, which is the string prefix, L index 01, and then JNT. So once again, we have that for each of the 6 fingers, including the last joint. Let's open up the script editor, and here I have the MEL script loaded into the script editor without the commenting, just a straight script. Let's enable all the switches here. Let's scroll to the bottom. And here, once all of this MEL is loaded,
At the very end, we call the global procedure handBuild and then pass it a string, which is the character prefix, in this case cave01. So we'll place our cursor at the very end and hit the Enter key. So here we can see we've quickly built a series of finger joints. There's index 5 JNT, index 4 JNT, and index 3. But if we hit the up arrow once, where we step one node up in the hierarchy, you can notice that we have an index 03 SDK, which is the set-driven key joint. And each of our JNT joints has a duplicate SDK joint. And what we can use these for is we can layer set-driven key poses onto these joints, and an animator will still have the JNT joints to add on top of whatever poses we may give to the animator. So here we can see all of the joint hierarchies built. For each SDK joint, there is a corresponding JNT joint. So to finish this off, we just need to select the end arm joint. So in this case, I'm going to select -R cave01 L arm 04 underscore end. Let's change this to underscore JNT. There we go. Then I'm going to duplicate this. So edit, duplicate. Let's go to the option box. We'll parent it to world. Make sure we're only making one copy with no transforms on it. Duplicate. We're going to rename this node from arm04 JNT1 to cave01 L wrist 01 underscore JNT. Hit enter. Let's open up our hypergraph. Let's frame that joint. And now we can select each of our new finger hierarchies and parent them to our wrist joint. So there, we've quickly built our hand. Eventually, we're going to parent this wrist joint to the L arm 04 end joint for the JNT arm. But for now, we'll leave this as is, and in subsequent lesson, we'll go over mirroring the hand over it and then adding one extra control for IK wrist. So in this lesson, we're going to create a controller for our left arm IK handle, as well as a local global switch for our left hand. Now you see we have the entire hierarchy here, so we've actually skipped forward a bit because we need a node that will only add once we've created our hierarchy. And what that node is, it's a locator which I have point and orient constrained to our all node, so that basically we get the base level orientation of our character. And we can use this for a local constraint for other items that we put into the hierarchy here. So once again, we had to skip forward a little bit in the hierarchy, but this will be added into the animation GUI. I just wanted to show how this works. Okay, so let's open up our hypergraph. And the first thing we're going to start with is we're going to create a controller for our left arm IK handle. In the past, I've used splines as controllers, either circles. Here's a NURB circle. I've used 1-degree splines to create a cube, but in this case I'm going to show another option for creating controllers for a character. And what these are is these are nodes which are called implicits. For this hand, I'm going to use an implicit sphere, but you also have the option of using an implicit box and an implicit cone. And what these are, once again, these are nodes which have transforms on them, so you can move them in a scene and set keyframes on their rotate, translate, and scale, but they don't ever render. They're drawn through OpenGL, so you'll never have to worry about these objects rendering, and you'll always be able to see your shaded character through these wireframe objects. So to create our implicit sphere, we open the script editor and type in create node, implicit sphere. Hit enter. Let's frame that. And there is our implicit sphere. So what we're going to do while we have that is, first of all, rename it. Call this cave01 L hand01 underscore CTL. Let's call this hand IK01 CTL. Then we're going to group it to itself. Select the implicit sphere node and then choose edit, group. Let's rename that. Once again, what I'm going to use this group node for is to position and orient the hand controller without adding transform values onto the controller itself. Okay. So what we're going to do to quickly move it and to orient it is select the left arm IK handle and use that as a constraining object, both positionally and orientationally. So with our arm IK selected, I'm going to select the hand group node and then select point, which moves it into place, and then constrain orient, which orients it to the IK handle. Once we've done that, we can select the constraint nodes, both point and orient, and delete them. We only needed them to temporarily move our object into place. So once again, we still have clean translate, rotate, and scale values on our IK hand controller. Let's display our high-res model, and we can see that our implicit sphere is sort of hidden within the wrist of our character. So we need to make that larger. So once again, we want default scale values, although we're never going to use scale values on our IK handle, but just in case you were going to use this for another object that you could scale, we're going to open the attribute editor with the implicit sphere selected, click on the shape node tab, and then we have an attribute, implicit sphere attributes radius, and it's set to 1, so we'll set it to 3. So we saw our implicit sphere grow to a radius of 3. Let's shade our model. Once again, we can see our implicit sphere, but it's something that's an OpenGL wireframe type display, so it will never obscure our model. Okay, with that done, I'm simply going to parent our IK handle to the implicit sphere. And we are done with that. So I'm going to parent this to the all node. So when I select this, it will move our entire character around, including the IK handle. Okay, so with that done, we're going to move on to the local global switching for the orientation of the wrist joint. In order to do that, we're going to need to create a couple more locators. One will be the parent of the wrist joint, which will be point constrained to the end of the JNT arm, and then derive its orientation, its rotation, from a parent constraint. One node going into that parent constraint will be this global locator, and another will be a locator which will match the orientation of the forearm joint. So let's create our two locators. Select create locator, hit G to create another. Now let's rename these. This first one I'm going to rename to cave01 L hand01 LOC. This will be the parent of this wrist joint. The next locator we're going to rename to cave01 L hand local 01 LOC, and this will be the one of the parent constraining objects, which will get the forearm orientation. Okay, so let's first select the arm 03 JNT joint, and then shift select this new hand local locator, and we're going to create a point and orient constraint. So with those two selected, constrain point and constrain orient. We're only really interested in the orientation of this when it comes to creating the parent constraint, but I also like positioning it so that we'll sort of know where to find it
easily in space. But once again, it could stay at the origin as long as it's getting the orientation of the ARM03 JNT joint or the forearm. Okay, so now what we need to do is we need to create a parent constraint where we're using both the hand local locator as well as the global locator. So select them in that order, the local locator first, shift select the global locator, and then shift select our hand 01 locator last, and then create constraint parent. Let's open the option box. And we're only interested in the rotation of both of those locators. So we're going to make sure that the translate is disabled. We want to leave maintain offset on, and we'll hit add. So here we can see we have a parent constraint with the hand local as well as the cave global locators both set at a weight of 1. Right now we're going to set the global to 0 so that it's in local mode. So with that done, we're going to point constrain our hand 01 locator to the end of the JNT arm. So we're going to select LARM04 end, which is the last joint on the JNT arm. Shift select our hand 01 locator and create a point constraint. Okay, so now we've positioned it. Okay, now we're going to parent our wrist 01 joint to the hand 01 locator. Now let's test this out. So our arm is in IK mode right now. So we'll select our new controller and move it around. So our hand is in local mode, so it will always match the orientation of the forearm joint. Let's reset this. Now let's change our parent constraint. There we go. To a weight of 0 on local and 1 for global. Now let's move our IK controller, and we'll see that our hand maintains its original orientation, which so happens to be the orientation matching this global locator. Okay, so when I switched there was no popping in the hand, and that's because we're at the default. So there's a 0 rotation on our hand controller. But if I were to, let's say, position this IK controller and then switch our parent constraint, we'll see our wrist joint will actually change orientations. So we'll set our global weight to 0 and then our local to 1. And then we saw a shift in our wrist joint. Let's back up and show how we're going to do this eventually. And this will be all MEL scripted in the animation GUI. There'll be a button which will switch this for us and then do the very simple change that we need to make in order to make sure that the wrist joint never pops. So open up our script editor. So what we're going to need to do when we're switching from local to global or vice versa is before we do that, we simply need to unparent our wrist joint. So what our GUI will do when we click our local global wrist button is it will first execute the command parent -w, which is world, cave 01 L wrist 01 JNT. So this will unparent our wrist joint and parent it to the world or the scene. Then our script will set our weights, changing modes from global to local, and then reparent our wrist joint to our hand locator. So after we've switched modes, we'll parent cave 01 L wrist 01 JNT to cave 01 L hand 01 underscore LOC. So once again, we've already switched modes. We'll reparent our wrist. And there we are. We're in local mode without a pop in our wrist joint. So once again, we're going to set this up in the GUI, but I just want to show you how we're going to set up the local global switching for all of our local global modes. Once you've changed the default position, you're going to have to unparent the children of whatever they're parented to so that there's no shift or pop when you're switching from local to global or vice versa. And unfortunately, we had to skip ahead to the final hierarchy where we've added in the simple global locator. Once again, this locator, let's open up our hypergraph. It's sitting under the no transform group node, which we'll get to in lesson 16. And it is simply position and orient constrained to our all node. It's our Cave01 all node. And you can use this locator, the global locator, for any local global switching. We're using the all node, or basically the base of the character for our global. So now that we have our left hand built using the MEL script, we're going to create an extra wrist joint which we'll use to drive the wrist when it's in IK mode, and then we'll mirror that rig over to the right side and then hook it up there as well. Okay, so let's open up our hypergraph and see what we have here. So we have this wrist joint. What we're going to do is we'll eventually parent this to the end of the J&T arm. And here we'll have full rotation control over the hand. But we're going to duplicate this wrist joint and connect the rotation channels of a control box, which will control the IK arm, so that we can have full control of the wrist both in FK and in IK mode. So here I've imported a control box made of 1-degree splines. I'm going to go in and rename this. So Cave01 and arm IK control. This control box, once again, is something that I use over and over again, so I've saved it out into my directory and simply imported it into scenes and rigs that I'm going to use it on. This is also something that I make available to you from the Fahrenheit Digital website, so you can download this and use it on your rigs as well. So now that I have this renamed, I'm going to group it to itself, edit group, and that way I can position and orient the group node and still have clean transformation channels on the control itself. Let's rename this group node Cave01R arm IK01 underscore GRP. I'm sorry, L. So I'm going to select this, duplicate it, and now rename all this to replace the L with R. I was getting a little bit ahead of myself with that renaming a little earlier. So replace the L's with R. So to quickly move them into place, we're going to position and orient constrain them to the IK handle. So select the IK handle, shift select the group node, and then select constrain point. That moves it into place. And constrain orient orients it to the IK handle, which is also oriented to the arm. Then we can select the two constraint nodes, the point orient constraint, and delete them. Then we'll repeat this process with the right arm. Select the IK handle, shift select the group node, and then select constrain point and constrain orient. Select the constraint nodes and delete them. Now we can simply parent the IK handles to these control boxes. So select the left arm IK, shift select the left arm IK controller, and then hit P to parent it. Let's repeat this on the right side. Select the right arm IK handle, shift select the right arm IK control box, and hit P. So now our controller once again has clean translate, rotate, and scale values. We can use it to control the IK arm. Now what we're going to do is select the wrist joint and duplicate it, delete all the other joints beneath it, and we'll use that duplicate joint, which will be the parent of this wrist JNT joint, and we'll rename that wrist 01 underscore IK and connect the rotations of the arm IK control box into the rotations of the wrist joint. So we'll select that, edit, duplicate, let's frame that. You can delete all the extra fingers and change the suffix from JNT to IK. Okay, let's shift select our wrist joint, shift select the wrist IK, hit parent. And you can see that the wrist joint has the same orientation as the IK controller. And that's because when we built this arm, we positioned and oriented the arm, the pole vector constraint, and the IK handles all at one time, so all of their orientations match. So I'm going to select the arm IK controller for the left arm, open the connection editor, Window, General Editors, Connection Editor, and load that into the outputs. Scroll down to Rotate, shift select the wrist IK joint, load that into the inputs of the connection editor. Let's find our rotate channels and connect the rotates of the arm controller to the rotate of the wrist IK. So that gives us is, once again, we have full rotational control in FK mode, but one node up. By rotating the control box of the IK arm, we also get rotational control of the wrist when in IK mode. So with that done, we can parent the wrist IK joint to the end of the JNT arm. But before we do that, we're going to select the wrist IK and then select skeleton, mirror joint. Make sure we have our right suffix search and replace. Then mirror that over to the right side. Okay, reselect our wrist IK joint, shift select our arm end for the JNT, and then hit parent. Now we're going to connect the rotate channels of the right wrist IK joint will be driven by the right arm IK controller. So once again, Window, General Editors, Connection Editor. Let's load in our right arm IK controller. Select our wrist IK joint. Load that into the inputs of the Connection Editor. Then let's connect the rotate the IK controller to the rotate of the IK joint. Okay, there's the FK control, and then the IK control through the control box. Select the R wrist IK, shift select the end of the JNT arm, and parent. So there we have our controls mirrored, and we have wrist controls for both the FK and IK wrist joints. So in this final lesson on the Mel scripted hand, we have both of our hands built with the controller boxes. Now we're going to build one more control. One of the switches in our Mel script creates a series of SDK joints which are parented one up from the corresponding JNT finger joint.
And what these joints are, SDK, is we can use them to add set-driven keys so that we can have key poses available to the animator, but they'll still have full FK control to go in and finesse these poses. Let's look at this hierarchy a little more closely. Here's our index. You'll notice that here's our J and T joint, and one node up is an identical joint, which is in essence a duplicate of the J and T index 01, which we call index 01 SDK. So the way this works, let's go in and select all of the index SDK joints. And if we had a pose which was index curl, the set-driven key would do something like this, let's say. But the animator would still be able to go in, select the J and T finger joints, and finesse whatever set-driven key poses we might have on top of that. So in order to use that, the first thing we're going to do is to create a series of curl attributes for the fingers of our left hand here. We're going to put those attributes on the wrist joint. So selecting the wrist joint, let's clear out some of these unneeded attributes, so visibility and radius. Let's go ahead and hide that. Scale and translate. We're going to go ahead and hide and lock those. So now we just have our rotation, and we're going to add a curl attribute for each of the fingers. So with the J and T joint selected, we can select channels, add attribute. This opens up our add attribute dialog box. So in the attribute name, we're going to type in the name of each of the finger curl attributes. So for instance, we'll start with thumb curl. We'll leave it as a float attribute, and we're going to set the minimum -10, the maximum to 10, and the default 0. We can hit add, so now you see we have this new attribute. But as of now, it's not connected to anything. We'll go ahead and do that later. So with the add attribute dialog box still open, we'll add the remaining curl attributes. So index curl, -10, 10, 0. Let's do that for each of them. Okay, one more. Our pinky curl. Okay, so we have 5 curl attributes. Okay, let's start with the index. It's pretty simple to illustrate how this works. So we're going to select our wrist joint, make sure we're in the animation module, and then select animate, set driven key, set, and the option box. This brings up our set driven key dialog. We're going to load this into driven so that what happens, driver. So what happens is these attributes will drive the attributes loaded into the driven section at the bottom of the set driven key dialog. Let's open up our hypergraph. We're going to select our set driven key joints. And for this curl, we're actually only going to curl the actual finger and leave the carpals open in this example. So we'll select these 3 set-driven key joints, load them into the driven portion of the dialog box, select all of them. We're going to curl on our Y rotation axis, so we'll select rotate Y. So eventually what we're doing here is the index curl attribute will drive the rotate Y of the 3rd, 4th, and 5th set-driven key index joint. So at the default position, we're going to hit the key, and we've set a key on rotate Y. We're going to click our wrist joint and set our index curl to 10, the maximum. Drag select all three of these set driven key finger joints and curl them in. Let's say minus 60. Hit key, and we can return our index to 0. You can see when we set it to 10, it curls our finger. But if we go negative 10, it sets it back to default. So we're going to set this to negative 10 so that we can define the behavior at that value on the curl attribute. So here we're going to curl it back slightly. Let's say 30. And key that. So here we've set our curl, and then the animator can go in and finesse this however they like. Reselect that, and the two layer one on top of the other. Okay, let's quickly set this up for the other four fingers. Let's open up our hypergraph. Let's collapse this, select our middle. Oops. Start at the third SDK joint. Rotate Y and change this to middle. At the default position, we'll key that. We'll set middle to 10. Set this to negative 60. Key. Then set our attribute to negative 10. Set this to 30. Key once again. We're going to do the ring finger. Okay, open up our hypergraph. Expand all on our ring finger. What I'm doing there is I am right mouse clicking on the node, and it brings up this drop down menu, and I'm selecting expand all to expand that entire hierarchy. Select the three SDK joints, load them into the set driven key menu, set the first key at the default, set our ring curl attribute to 10, set this rotate Y to negative 60, key that, set this attribute to negative 10, set this channel to 30. Key it again, and so one more for the pinky. Let's collapse that. Let's expand all on our pinky. Shift select the three SDK joints, load them into the driven part of the set driven key dialog box. Set the first key on default. Select our wrist joint. Set the pinky curl attribute to 10. Set the rotate Y on the SDK joints to negative 60. Key it. And set the pinky curl attribute to negative 10. And set the rotate Y to 30 on each of the pinky SDK joints. Okay, so let's test this out. So we can select each of these, curl the fingers back, curl them in some. And once again, the animator can go in, select each of these J and T joints individually, finesse the pose, go in, and they're additive, one on top of the other. So that way you can quickly add set-driven key poses that the animator can use to help rough out poses and still allow them the latitude to go in and set their own finesse animation on top of those poses. So that way you can layer animation. In this lesson, we're going to go through a process similar to what we did earlier with the manual fingers. We're going to build a few of the toes manually for this character. Once again, in a very similar process, we're going to use the edge loop tool to create some clusters, snap 1-degree splines to those clusters, and then use those as a visual guide to draw our joints. Okay, so let's select our geometry to activate our edge loop tool. Select Edit. Select the edge loop tool. Going to create the first edge loop on this bend. Okay, hit Q to exit that tool. Once again, we're going to switch to the modeling module and then edit polygons, selection, tear off this menu. We're going to select this, convert this selection of edges to vertices. With the vertices selected, switch back to the animation module and then select the form, create cluster. Let's repeat that process. Hit Y to reactivate the edge loop tool. Let's find our next toe knuckle. Select that edge loop, hit Q to exit the tool. Convert that selection of vertices. Create another cluster. Now I'm just going to select the vertices on the end of this toe, then hit G to create that last cluster. And we're going to select the vertex back here, then hit G once again. Okay, so let's repeat that with this next toe. Create our edge loop tool. So here, once again, we're going to have to select the top and the bottom. Okay, exit that tool. Convert selection of vertices. Let's create another cluster. Okay, create an edge loop on that knuckle. Convert the selection of vertices. Create a cluster. And we'll just select the vertex on the end. Actually, we'll just average between these two here. Hit G to create a cluster. Okay, let's create one more cluster back here. Okay. So now we're going to draw 1-degree splines through all these clusters. Let's hide the model here, and then select Create, CV Curve tool. Make sure it's set to 1-degree linear. Activating Point Snap. We'll just click through each of these clusters. Hit G. Open up our attribute editor, and then select Component Display CVs. Now let's draw our next spline. Display the CVs of that spline. We can toggle off our point snap tool, and then let's delete all these clusters by turning off all the selection masks, turning on only the deformer selection mask, and selecting all these clusters and deleting them. Let's turn on our geometry here. Let's activate our spline selection mask, switch to component mode. Select the CVs and just quickly position them into place. Okay. And I'm going to display the splines that we created a little earlier, that I created a little earlier. Okay, so now let's hide this geometry and start creating these toe joints. So again, we're going to activate our point snap tool, select skeleton, joint tool, start clicking on each CV to draw these toe joints. Okay, so there's our first. Let's open up our hypergraph. Zoom in. Going to display all their local rotation axes. Display, component display. local rotation axes. Of course, we're going to orient the last joint here. Skeleton joint orient. The orientation is still set to none. Let's quickly rename this. Modify, search and replace names. Let's reset this. So we're going to search for every instance of the string joint and rename it to cave01 L index toe 0. I'll go in and manually add the JNT suffix. We'll just add end to the end joint. Okay, let's repeat this process for the next toe joint. Display all these local rotation axes. Let's orient that last joint. Actually, before we proceed, I'm actually going to rename this first from index toe to thumb toe. So once again, modify, search and replace names. I'm going to search for underscore index toe and replace that with underscore thumb toe. Okay, now let's rename this group of joints here. We're going to search for joint and replace it with cave01 L, and this is index toe. Add our JNT suffix. If we were to go in and write a mel build script for this, it would basically be something quite similar to what we've done with the toe or the finger build script. Pretty much the same type of thinking or logic involved here. Just that you can still have the set-driven key joints, very similar to the fingers. Okay, display these local rotation axes. Let's orient the last. Let's rename these. So these will be the middle toe. Okay, reorient the last joint. These are the ring toe joints. Some serious renaming to do on that last chain. Let's first complete renaming this one. I'll get the naming right on that middle toe joint chain. Okay, so here we can see I've completely misnamed this. So I'm going to search and replace names, search for middle index. We're going to change that to okay. Okay, so that corrects the naming there. Activate our joint tool and draw our pinky toe joint. Okay, our last renaming. Okay, and this is going to be called pinky toe. Okay, the last set of suffixes. Okay, I'm going to switch to component mode, activate our question mark, the local rotation axis component. I'm going to go through and select each of the local rotation axes. I'm going to flip them so that their y-axis is pointing out to the side. In this case, that should be -90 on x. So let's go here. Let's type in rotate -r, -90 on x, 0 on y, and 0 on z. Okay. Show our model here so we can see that our y-axis is pointing out to the side on each of our toes. So we can switch back to object mode and duplicate each of these joints. Select the thumb toe joint and select skeleton, mirror joint tool. We want to mirror across the YZ plane once again. With the mirror function being behavior, we're going to search for the left joints and mirror them over to the right side. Okay. Let's repeat that for each of them, just selecting and hitting G. Okay, so there we've quickly manually built a set of toe joints and mirrored them over to the right side. A bit repetitive, but not too difficult to do. If you were to concentrate on it 100%, it's something that you could do, in a pretty short amount of time. Once again, something that could be readily mel scripted, but once again, just wanted to go through the manual process. So in this lesson, we're going to build the standard heel, ball, toe reverse foot for this character. And we're also going to build a truncated reverse foot, which will only incorporate the heel and the ball. And that way we can take advantage of the lengthened metatarsals, the toe joints which extend further back in the feet. So we're actually going to start by building the shortened reverse foot. Let's select the joint just for framing. Move to our side view. We're going to create a 1-degree spline just as a visual guide. Draw our first spline. CV, holding down point snap. We'll snap it on our center joint. And then snap the last CV. Right, so, okay, let's open up our attribute editor, display our CVs, then switch to component mode. We're going to select the CV, and move it over here, and then using the middle toe, we're going to snap it to that center line point on the foot. Right there, okay? Switch back to the perspective view. Let's hide our foot, switch back to object mode. Now let's draw our joints. Skeleton joint tool. Holding down point snap, just create our joints. Display their local rotation axes. I'm going to switch to component mode and toggle on the local rotation axis toggle, and then rotate. First let's align our last joint. Just orient that. Now let's select all of our local rotation axes and rotate them -90 degrees in X. Okay, switch up back to object mode. So why did I rotate them -90 degrees in X? I want this upward motion to be positive in rotate values. Just having done this before, I know that that's a positive rotation. Okay, so now let's rename these joints. Modify, search and replace names. So change joint to foot. Okay, let's rename these. Let's change that to 2. Get rid of the 1 on the end. Change this to end. I'm going to take this foot controller and its group node and then parent it to the end of our new foot joint. That way when we select our reverse foot, take our IK along with it, I'm going to create a locator Okay, let me capitalize this G here, and we're going to use this for the local global switch. Zero out the translates after we've parented to the second foot joint. Let's remove that. So first we're going to point constrain this locator to the second foot joint, which is the ball. Constrain point. Then we're going to create a parent constraint between the ball joint and the heel joint. Actually, let's rename these just to make it more evident what we're doing here. I'll leave that as is. We're going to select the ball joint first, the local, and the heel joint second, the global. Shift select our local global locator, and then create a parent constraint. We're going to go to the option box and make sure that only the rotation is selected. Hit add. Select that new parent constraint, and we'll start out by setting to 0. So now we're going to select all of our toe joints and then make them a child of the local global toe locator. So now what we have, if we select our heel joint, go to the translation, you can rotate the heel up. There we have our global. Switch it to local. It's our heel rotation. And then our local toe rotation. One last step will be creating a controller, a zeroed out controller for this foot joint so that we have zeros on all of our transforms, including our rotates. So I'll just quickly create a NURBS curve. I'll group it to itself. I'm going to select our heel controller, shift select our group node, create a point orient constraint. I can delete those two constraint nodes once I've positioned and oriented it. So here we can see that our foot controller has zeros in all the transforms. So let's rename this. controls, rename the group node. Make this heel joint child of the foot controller. We have clean transform values. So that's our truncated or shortened just heel ball reverse foot. Now let's back up a second and build a heel ball toe reverse foot. Okay, so we'll unparent this, select all this and delete it. And we'll unparent our toes in the locator. Select our spline, and we're going to rebuild this spline and add and go from heel, toe, back to the ball and up. Once again, we'll create a 1-degree spline with point snap. Start at the heel, go to the toe, back to the ball, then up to the ankle. Display our CVs. We can select the old spline and delete it. Now we can see that we're not, with this configuration, we can't take advantage of the metatarsals that we have extending back further into the foot. So I'm going to unparent the toe joints and delete the old metatarsals, or the toe 01 joints. Okay. I'm going to, with point snap still selected, create joints starting at the heel, going to the toe, back to the ball, then up to the ankle. Now we can turn off our point snap. Let's display our local rotation axes. And let's orient our last joint. Skeleton orient joint tool. That's done. Go ahead and change all of our local rotation axes, once again by rotating them all -90 on X. Switch back to object mode, and then we'll rename our joints. Okay, so this time we're going to start out by naming them in a more descriptive manner. So that's our heel. This will be our toes. We'll just capitalize that. This will be our ball joint. This will be our foot end. So now we're going to point constrain our local global locator to our toe joint. Select our toe joint, shift select our local global locator, constrain point. Then we're going to use our toe joint and our heel joint as the parent constraint for the local global locator. Select the toe joint, shift select the heel joint, and then the locator last. Then we'll parent constraint, once again confirming that just the rotate values are checked. We'll just set that to 0. We'll set that to local. Select our 5 toe joints and parent them to our local global locator. and turn off our local rotation axes. And once again, parent the group node of this foot controller to the end of our foot joint here. Select our foot joint. There's our heel roll. Our toe roll. And then our ball. We'll switch it to a different mode here. With our heel roll. Leaving our toes on the ground. Then the ball roll. We'll quickly go on and create the controller. Create NURB circle. We'll set its normal axis to Y, since the dominant rotation of the heel is Y. Click Control Group to group it to itself. Then we'll parent that to the heel joint. Then we'll zero out the rotations and translations of that. So constrain orient, there we go. We're going to parent our heel controller to our NURB circle and then rename all these components. Okay, so here's our more standard reverse foot. I think we've all seen reverse feet built in the past where the leg actually extends from the ankle in a continuous joint down to the forward, to the ball, and then to the toe, and then we'll have multiple IK handles, and then parent those IK handles to the reverse joints. But from experience, I've seen that that isn't really necessary. We can get the same effect and the same deformations by skinning to these joints here and then using only one IK handle. Just makes it a little more simple and we still get the same effect. So those are two examples of the standard reverse foot. One a truncated version, and then here we have our standard reverse foot with the heel ball toe. In this lesson, I'm going to build a slightly different type of foot rig, which I call the toe flop. What this does is it pays a little less attention to the typical heel, ball, toe configuration of a foot rig and lends more weight to allowing flexibility in the front part of the foot. I'm going to build this for this particular character. It's not always useful, but in case a case like this where we have a character that will spend perhaps less time walking on the ground and more time swinging through branches and grasping things with his feet, we'll want that extra flexibility in the front of the foot. Let's switch to template mode and begin building this rig. It's fairly simple and straightforward. So we're going to start by building a guide spline through the middle of the foot. Create CV curve tool, make sure it's set to linear. Switch to a side view and zoom in. So holding down point snap, draw 3 points. Switch back to perspective mode and open up the attribute editor and display the CVs. I'm going to switch back to the side view. Reactivate our spline tool, and holding down point snap once again, I'm going to snap a CV to the beginning of the first curve and then to the end of the leg, matching the position of the IK. Okay, so at this point I'm going to go ahead and detach the toe joints. At this point, we're actually going to replace the flexibility in the front part of the toes with the new joint chain that we're building toward the front here. So I'll select Edit, Unparent, and then delete the remaining joints, the toes. I'm just going to simply go in and with our skeleton tool, activating point snap, snap joints to each of these CVs. Display their local rotation axes. Of course, reorient the last joint. I'm going to activate the local rotation axes component selection and rotate all of these local rotation axes by 90 degrees. And do a quick rename. Changing every instance of the word joint to our standard prefix and give it front foot and add the JNT suffix. I'll reactivate our joint tool, holding down point snap. Draw a chain in the reverse direction, leading from the beginning of the spline to the end of the leg. Display our local rotation axes. Reorient that last joint. And then I'm going to go ahead and rotate the local rotation axes by -90. Okay, we can hide those local rotation axes and switch back to object mode. Rename these joints. I'm going to rename them B foot. Give them the JNT suffix. And correct this, give this an end suffix. Okay, we're actually most of the way there. At this point I'm going to switch to the side view. Reactivate our joint tool and holding down point snap, actually go back to perspective. Holding down our joint tool and point snap, I'm going to draw a single joint node right at the juncture of the front and back foot. Rename this. Just call it foot. So I can parent the front and the back foot to this new foot joint. And now I'm going to parent the IK handle to the end of the back foot joint. So what we have now is with the main foot control, we have translation and rotation control. over the entire foot as well as the IK handle. Once again, this pays less attention to the heel ball toe configuration, although I'll show in a moment that you can add a ball roll to this, or heel roll, I'm sorry. We have the ball rotation, fairly straightforward. Then we also have the ability to flop the toes so they can curl around and grasp a branch or a log, which is something that I foresee doing with this character. So this is a viable foot rig for this type of character. And to finish this off, we're going to attach the toes to the end of the front foot joint. And do that by first creating a locator, renaming it. All toes are one loc. I'm going to point constrain this locator to the end of the front foot joint. And show our locators, so we can see our new locator there. And then I'm going to parent constrain the locator to both the second front foot joint and then the main foot joint. So I'll select the front foot joint first, the foot joint second, and then the locator last. Select parent constraint, option box, and I only want the rotate channels. I'm already driving the translates with the point constraint. So I'll hit add. At this point I'm going to set the parent constraint values so that it defaults to, well, let's start out with the end of the front foot. Select our toe joints and parent them to our locator. Let's collapse that. Let's curl our toes and see what we get. Then select our main foot joint. So here the parent constraint is deriving its orientation from the front foot joints. So I'm going to select the parent constraint and reverse these values. So it's 100% on the main foot joint. So we'll select the main foot joint. We're getting our orientation from that joint. Now select our toe flop joints. And here we have a local global switch. Okay, let's set it back to what I will call its default value. And so then we have a very simple version of a foot for this character that's going to be grasping objects with his feet as if it's a hand quite often. Once again, less attention is paid to the heel ball toe roll. But at this point I'm going to go in and add a heel rotation. Switch to a side view and zoom in. Select our joint tool and create a single joint node where we want our heel. Switch to perspective. I'm actually just going to point snap this into place. What I'm using as a guide is the poly edge running from the center of the middle toe all the way back through the heel. So I'm going to rename this joint quickly. Heel of one joint, and make that a parent of the main foot joint. So this gives us a quick
heel rotation as well. It's not as robust for, once again, heel, ball, toe walks, but for this character, I'm going to want a more prehensile foot. This is a very quick and fairly simple foot rig, which can give you some heel control, but once again, that's not necessary. And in actuality, in the final rig, I'm going to leave that out since I know I'm not going to be doing that many walks. And you could counter animate, do some animation with that, but you could leave that in once again to get the heel rotation. So in this lesson, we're going to build a ribbon neck rig as well as a simple head joint for this character. That will just about finish off the rigging for the character, and then we'll move into building the hierarchy. So this ribbon is pretty much identical to the spine ribbon. The only difference will be the number of joints that we're going to attach to it. Okay, so let's turn off our geometry here, and let's start by building the actual ribbon, which once again will be a NURBS plane. So we'll select Create, NURBS Primitives, Plane. Just reset this tool. So we want our axis, or the flat portion of the plane, to point up in Y. So we'll leave our axis at Y. And once again, we're going to set our length as well as our V patches to equal the number of joints that we're going to eventually attach to this ribbon. In this case, that will be 3. So we'll set the length to 3, the V patches to 3. Then we're going to leave the surface degree to cubic, or a third degree surface. Let's create that ribbon. Let's frame in on that and quickly rename it. So cave01 underscore C underscore neck ribbon underscore GEO for geometry. Okay, so let's select this and display the control vertices, or CVs, on this NURBS plane. So display NURBS components, CVs. So we can see that we have a third degree surface in both U and V. Let's open up our attribute editor to verify this. So though we have 1 span in U and 3 in V, we have a degree of 3 in both the UV direction. What we want to do is we want to rebuild the surface so that we retain the number of spans, but we'll rebuild the U degree to 1. So to do that, let's switch to the modeling module, select Edit NURBS, Rebuild Surfaces in the option box. So we're going to leave the rebuild type to uniform. The parameter range will also leave at 0 to number of spans. So the first major change will be the direction. Rather than rebuilding both U and V, we're only going to rebuild U. So let's enable that. After that, the number of spans in U, we want to change that to 1, which equals the current number of spans. We don't want to change that. We just want to change the degree. So here, the degree will change from cubic to linear. And since we're only rebuilding in the U direction, we could ignore all of the information, the number of spans in V as well as the degree in V. That won't be rebuilt. Let's hit the rebuild key. So you can see that now we have a 1 degree surface in U, and we still have a third degree surface in V. Let's open our attribute editor. So we can see degree 1 in U, degree 3 in V. So now let's delete history to remove the input nodes that we've created, the rebuild surface. So with the surface selected, edit, delete by type, history. So you can see all the input nodes have been deleted. So now with that done, we need to create 3 follicles using the hair system, and we'll use those follicles to eventually attach joint nodes onto a UV position of this neck ribbon. So we'll select the plane, switch to the Dynamics module, then select Hair, Create Hair, and open the option box. Let's reset this. So I like changing my output to NURBS curves.
And here we're going to set our U count to 1 and our V count to 3. Leave everything else as it is in the default. Create hairs to open up our hypergraph. So you can see here we've created a hair system, 3 follicles, and a group of output curves. The output curves in the hair system, we can select and delete those, but the follicles we want to keep. So let's quickly rename them. Let's give each of them a number. So this will be Cave01C neck ribbon 01 underscore FOL, which is the suffix I use for follicle. This will be neck ribbon 02 underscore FOL, and then 03 FOL. Now let's rename this group node. Cave01 neck follicles underscore GRP. Okay, I'll switch to a side view, and we're going to create 3 separate joint nodes that will attach to the NURB surface by making them children of the follicles. Let's switch back to the animation module and activate the joint tool by selecting skeleton joint tool. Click anywhere in the interface and hit enter, and then repeat that twice more until we have 3 separate joint nodes. Open our hypergraph. You can see we have these 3 joints. So let's quickly rename them. Modify, search and replace names. Let's reset that. So we're going to search for joint and replace with Cave 01 C neck 0. Since we're going to use these to actually skin the models, we're going to give them each an underscore JNT suffix, which is the suffix we're using for all joints that will eventually bind to. Now with that done, we're going to parent each joint to a corresponding follicle. I'm going to middle mouse drag and drop the joint node onto the follicle. I could also select the joint node. The child should select the parent, the follicle, and hit P. A couple of different ways to do that. So once each joint has been parented to a follicle, I'm going to select each of the joints, drag over all the translate channels for the joints, and then type in 0, which will zero out their translation relative to their parent, which effectively pops them directly onto their parent. Okay, so let's switch to component mode. Select a few CVs. I'll move them around, and we can see that the joints are locked to a UV position as well as the normal information of this deforming NURBS plane, which we're calling the ribbon. Okay, so with that done, we're going to build a series of controls which will control the expansion and contraction as well as the center of this ribbon. I'm going to just select these joint nodes and change their radius to 0.25 so I can easily distinguish them from the joints we're about to create. So switch to a side view. I'm going to activate the grid. So we're going to draw a 2-joint chain from the top of the ribbon pointing back, another 2-joint chain from the bottom pointing forward, and then a single joint node in the center. Reactivate our joint tool, and holding down X for grid snap, I'll just click twice, so pointing in the one direction from the top to the bottom. Let's rename these. So we're going to search for joint and change it to Cave01C neck top and give them an FK suffix. Okay, so reactivate our joint tool and holding down X once again, create 2 more joints pointing in the opposite direction. Select and rename them. These will be neck bottom, BTTM. Give them the FK suffix. Then a single joint node, we can just click anywhere. Don't need to hold down grid snap for this one. And we'll rename this to neck mid. And give it the underscore FK suffix. Okay, so I'm going to select the ends of the top and bottom neck joints, change their translate to 0.5, just as a visual thing to shorten these joints. So now we're going to create a stack of locators, one to control the position of each of these joints, another the orientation by aiming it toward another object, and then a third which will be an up vector object for the aim constraint. So we'll select create locator. Let's open our hypergraph, frame it on our locator, then hit the G key twice to reapply the last use tool. So now we have 3 locators. We're going to select the second and third, shift select the first, and hit P to make them children of the first. Let's hide this grid at this point. Okay, let's select them and quickly rename them. So we're going to search for locator and change to Cave 01C neck top 01. Okay, so let's remove the last digit, give it an underscore pause for position for the first locator. Second locator will be underscore aim, since we're going to aim constrain it toward an object. And the third will be underscore up, since we're going to use that as an up vector object. So once we've renamed them, let's select the up locator and translate it, let's say 2 units up in Y. I'm going to change the local scale to 0.5 so we can clearly distinguish the up vector locator. So now let's select the neck top pause locator and duplicate it twice. Edit, duplicate. Let's hit G once again. Okay, so let's rename these. Let's change this from neck top to neck bottom. Let's search for top, change to bottom, BTTM. And let's rename these from top to mid. Okay, then we remove the numbers at the end of the pause locators. For the neck mid locators, we actually need a fourth, which we'll use to offset the joint position in the center. So we'll select the neck mid aim locator, duplicate it, edit, duplicate. With the duplicate selected, we'll shift select the aim locator in parent. Let's quickly rebuild this. Now we're going to change the suffix from aim to OFF for offset. Okay. Now I'm just going to select each of these the neck top pause locator, activate the translate tool, holding down V for point snap. Just snap it to that top joint. Repeat this with the neck bottom pause locator. Okay. Now we're going to select each of these joints and make them a child of the corresponding aim locator. So the neck top FK joint will be a child of the neck top aim, and the neck bottom will be a child of the neck bottom aim. Okay, so now we're going to parent this neck mid FK to the neck mid offset locator, and then drag over the translate channels and set them to 0 so that it pops to its parent. Okay, so with that done, we're going to start creating some constraints. The first being, we're going to constrain the neck mid position locator to both the neck top and neck bottom position locators, so that way it will average its position between them. So we're going to select both the neck bottom and neck top pause locator, shift select the neck mid pause locator, and then select constrain point. So now if we select either the top or bottom pos locator and translate it around, you can see the middle will average its position between them. Now we need to orient all these locators so that they each will aim toward one another. Okay, so open our hypergraph. So first, we're going to aim the neck bottom aim toward the neck top pos. So we'll select the neck top pos, shift select the neck bottom aim, and then activate our aim constraint, aim. So open the option box. Okay, so we can see we want the aim vector to be z. So we're going to change it from 1, set that to a weight of 0, and give the z-axis a weight of 1. And we want to leave our up vector at y, which is what it is currently. We're going to change the world up vector to object up since we want to specify this up locator. So once we do that, let's type in the name cave01 underscore c neck bttm01 underscore up. Hit apply. Okay, so you can see we have this aim constraint. So next, let's aim the neck top aim to the neck bottom pos locator. So select the bottom pos locator, shift select the top aim locator. So rather than aiming it on z with a weight of 1, which would flip this locator 180 degrees, which we could do, instead we're going to set this aim vector weight to -1. So that way it will still aim back toward the neck bottom locator, but its local axes will remain unchanged. And that's by setting it to a -1. And we just need to change the name of the up vector locator, so to neck top 01 up. Hit apply. And lastly, we're going to aim our neck mid toward our neck top pos locator. So we'll select the top pos locator first, shift select the neck mid aim locator. Let's reset our aim vector to positive z, and then change the name of our up vector world up object to neck mid 01 up, and hit add. So now let's select any of our top or bottom pos locators, translate it around. You can see not only do we have the expansion and contraction, but we also have orientation information. Okay, so one last step. We're going to point constrain our neck mid up vector locator between the top and bottom up locators. And this will give us our twist, since if we rotate either end, it will also average the position of the neck mid up vector locator. So we'll select the top and bottom up vector locators first, shift select the neck mid up vector locator last, then select constrain point. So if we select, for instance, our neck bottom pos locator and rotate it, you can see that it also twists the neck mid aim locator. Okay, so switch to a side view. Let's activate our grid once again. So now let's position these pos locators up on the grid. It's holding down X. Let's just snap it up there. Do the same with the neck bottom. Okay, so we know that this ribbon is 3 units in length, and we have -1 for the and z for the position of the bottom pos locator, and +1 for the neck top pos locator. So those equal 2. Those add to a length of 2. So we need to set these to 1.5 for the top pos locator and -1.5 for the neck bottom pos locator, so that they're aligned exactly on the end of the ribbon. Let's hide our grid real quick. So one last step, we're going to select our ribbon geometry, and then shift select all 3 of our neck FK joints, and then we're going to smooth bind it. So skin, bind skin, smooth bind. We'll bind to selected joints. Our bind method will be closest distance. Our number of max influences we're going to leave at 2. You want to make sure that after bind, maintain influences is disabled, it's not enabled. And we can leave everything else at the default. Hit bind. So now what we need to do, let's switch to a side view. We'll just quickly edit the profile, the influences of these joints, so that we can edit the profile of our ribbon. So selecting the neck mid FK joint, let's just translate it down. And switching to component mode, we're going to edit the smooth skin weights of these CVs so that we can get the arc that we want, or the profile that we want in our ribbon. Let's select this set of CVs and open up our component editor. Window, General Editors, Component Editor. A little difficult to see. Let's actually hide our locators. Yeah, that should be fine. So you want to make sure you're on the Smooth Skin tab. So here, we're going to set the weight. We're going to increase the weight on the neck mid joint to 25% or 0.25. I'm going to use the down arrow key to select the last set of CVs and make sure that the weight is 100% on the neck bottom FK. You can use the up arrow to step through so we can see that this set of CVs is 50% on each of the joints. We'll leave that. And then we'll set this set of CVs to 0.25 on the neck mid, just as we did on the other end. Step up one more and make sure that 100% of the weight is on the neck top FK joint. There we've quickly edited the profile of our ribbon. Switch back to object mode. Set this mid FK joint back to 0. Okay, let's show our locators. Let's show our model. Now let's quickly move our ribbon into place. So I've selected the top and bottom pause locators. Okay, let's quickly place them into place here. Let's hide our geometry once again. So we're going to select the neck bottom pause locator and holding down point snap, just snap it to the end of the chest joint. So with that pause locator selected, I'm going to shift select the end of the chest and then parent the neck bottom pause locator to the chest end joint. So now if I select the chest joint and rotate it, you can see that it leaves the head behind. So that way we'll get a sort of FK, or IK, I'm sorry, on our neck so that we can position our head, leave it in place, and then adjust the body and know that it won't adjust the position of the head. Okay, so let's switch back to a side view. I'm going to select the offset locator for the neck mid, activate our translate tool. Well, first let's select our neck top pause and position that sort of at the base of the ear here. Now I'm going to select the offset locator for the neck mid and give it a little arc. I mean, not much in this case. Okay, so we're almost there. So now what we're going to do is create a 2-joint chain for the head. We're going to add significantly to it in our last lesson or last tutorial on facial rigging, but for now we'll just use this joint to add all the weights once we move into the skinning and deformations into part 2 of this tutorial. So select skeleton, joint tool, holding down V, we'll point snap to the neck top joint, show our geometry once again. Holding down Shift, just drag out a straight line till it reaches the orbit of the eye, then hit enter. Back to a perspective view. Okay, let's actually snap this on that joint. Let's open our hypergraph and frame that. Of course, we're going to quickly rename it. Rename them. So we're going to search for a joint and rename to Cave 01 C Head 0 and give it a JNT suffix. Underscore JNT. Underscore JNT. I'll select them both, display their local rotation axes. Display, component display, local rotation axes. Select the end joint and reorient it so that it matches its parent by selecting Skeleton, Orient Joint tool, making sure that the orientation is set to none, so that it has no orientation change relative to its parent. Okay, so now we know that all of our chest joints are oriented so that they're Y's pointing out to the left side of the character. So we're going to make that same change to the head joint. Switching to component mode, we want to activate our question mark icon, which activates local rotation axes. We'll select each of these local rotation axes and then rotate them 90 degrees on the x-axis. So we'll type rotate -R 90 0 0. Okay, so we can select these two joints and hide their local rotation axes. The last step, we're going to parent the neck top pause locator to the head joint. So select the top pause locator first, the head 01 joint, and hit P. So at this point, we're pretty much completely done with the hierarchy, with all the rig components. So there we can position our chest and know that we're not upsetting the position we've specified for the head joint, as well as select the head and position it any way we want. We get squash and stretch on the neck, and it acts as sort of like an FK where it doesn't disturb the position of the chest. Okay, so there we have our ribbon neck. So in this lesson, we're going to build a ribbon neck rig as well as a simple head joint for this character. That will just about finish off the rigging for the character, and then we'll move into building the hierarchy. So this ribbon is pretty much identical to the spine ribbon. The only difference will be the number of joints that we're going to attach to it. Okay, so let's turn off our geometry here, and let's start by building the actual ribbon, which once again will be a NURBS plane. So we'll select Create, NURBS Primitives, Plane. Just reset this tool. So we want our axis, or the flat portion of the plane, to point up in Y. So we'll leave our axis at Y. And once again, we're going to set our length as well as our V patches to equal the number of joints that we're going to eventually attach to this ribbon. In this case, that will be 3. So we'll set the length to 3, the V patches to 3. Then we're going to leave the surface degree to cubic, or a third degree surface. Let's create that ribbon. Let's frame in on that and quickly rename it. So Cave 01 underscore C underscore neck ribbon underscore GEO for geometry. Okay, so let's select this and display the control vertices, or CVs, on this NURBS plane. So display NURBS components, CVs. So we can see that we have a third degree surface in both U and V. Let's open up our attribute editor to verify this. So though we have 1 span in U and 3 in V, we have a degree of 3 in both the UV direction. What we want to do is we want to rebuild the surface so that we retain the number of spans, but we'll rebuild the U degree to 1. So to do that, let's switch to the modeling module. Select Edit NURBS. rebuild surfaces in the option box. So we're going to leave the rebuild type to uniform. The parameter range will also leave at 0 to number of spans. So the first major change will be the direction. Rather than rebuilding both U and V, we're only going to rebuild U. So let's enable that. After that, the number of spans in U, we want to change that to 1, which equals the current number of spans. We don't want to change that. We just want to change the degree. So here, the degree will change from cubic to linear. And since we're only rebuilding in the U direction, we could ignore all of the information, the number of spans in V as well as the degree in V. That won't be rebuilt. Let's hit the rebuild key. So you can see that now we have a 1 degree surface in U, and we still have a 3rd degree surface in V. Let's open our attribute editor. So we can see degree 1 in U, degree 3 in V. So now let's delete history to remove the input nodes that we've created, the rebuild surface. So with the surface selected, edit, delete by type, history. So you can see all the input nodes have been deleted. So now with that done, we need to create 3 follicles using the hair system, and we'll use those follicles to eventually attach joint nodes onto a UV position of this neck ribbon. So we'll select the plane, switch to the Dynamics module, and select Hair, Create Hair, and open the option box. Let's reset this. So I like changing my output to NURBS curves, and here we're going to set our U count to 1 and our V count to 3. Leave everything else as it is in the default. Hit Create Hairs to open up our hypergraph. So you can see here we've created a hair system, 3 follicles, and a group of output curves. The output curves in the hair system, we can select and delete those, but the follicles we want to keep. So let's quickly rename them. Let's give each of them a number. So this will be Cave01C neck ribbon 01 underscore FOL, which is the suffix I use for follicle. This will be neck ribbon 02 underscore FOL, and then 03 FOL. Now let's rename this group node. Cave01 neck follicles underscore GRP. Okay. I'll switch to a side view, and we're going to create 3 separate joint nodes that will attach to the NURB surface by making them children of the follicles. Let's switch back to the animation module and activate the joint tool by selecting skeleton joint tool. Click anywhere in the interface and hit enter, and then repeat that twice more until we have 3 separate joint nodes. Let's open our hypergraph. You can see we have these 3 joints. So let's quickly rename them. Modify, search and replace names. Let's reset that. So we're going to search for joint and replace with Cave 01 C neck 0. Since we're going to use these to actually skin the models, we're going to give them each an underscore JNT suffix, which is the suffix we're using for all joints that will eventually bind to. Now with that done, we're going to parent each joint to a corresponding follicle. I'm going to middle mouse drag and drop the joint node onto the follicle. I could also select the joint node. The child should select the parent, the follicle, and hit P. A couple of different ways to do that. So once each joint has been parented to a follicle, I'm going to select each of the joints, drag over all the translate channels for the joints, and then type in 0, which will zero out their translation relative to their parent, which effectively pops them directly onto their parent. Okay, so let's switch to component mode Select a few CVs. I'll move them around and we can see that the joints are locked to a UV position as well as the normal information of this deforming NURBS plane, which we're calling the ribbon. Okay, so with that done, we're going to build a series of controls which will control the expansion and contraction as well as the center of this ribbon. I'm going to just select these joint nodes and change their radius to 0.25 so I can easily distinguish them from the joints we're about to create. So switch to a side view. I'm going to activate the grid. So we're going to draw a two joint chain from the top of the ribbon pointing back, another two joint chain from the bottom pointing forward, and then a single joint node in the center. Reactivate our joint tool, and holding down X for grid snap, I'll just click twice. So pointing in the one direction from the top to the bottom. Let's rename these. So we're going to search for joint and change it to Cave01C neck top and give them an FK suffix. Okay, so reactivate our joint tool and holding down X once again, create two more joints pointing in the opposite direction. Select and rename them. These will be neck bottom, BTTM. Give them the FK suffix. Then a single joint node, we can just click anywhere. Don't need to hold down grid snap for this one. And we'll rename this to neck mid. And give it the underscore FK suffix. Okay, so I'm going to select the ends of the top and bottom neck joints, change their translate to 0.5, just as a visual thing to shorten these joints. So now we're going to create a stack of locators, one to control the position of each of these joints, another the orientation by aiming it toward another object, and then a third which will be an up vector object for the aim constraint. So we'll select create locator. Let's open our hypergraph, frame it on our locator, then hit the G key twice to reapply the last used tool. So now we have three locators. We're going to select the second and third, shift select the first, and hit P to make them children of the first. Let's hide this grid at this point. Okay, let's select them and quickly rename them. So we're going to search for locator and change to Cave01C neck top 01. Okay, so let's remove the last digit, give it an underscore pause for position for the first locator. Second locator will be underscore aim, since we're going to aim constrain it toward an object. And the third will be underscore up, since we're going to use that as an up vector object. So once we've renamed them, let's select the up locator and translate it, let's say 2 units up in Y. I'm going to change the local scale to 0.5 so we can clearly distinguish the up vector locator. So now let's select the neck top pause locator and duplicate it twice. Edit, duplicate. Let's hit G once again. Okay, so let's rename these. Let's change this from neck top to neck bottom. Let's search for top, change to bottom, BTTM. And let's rename these from top to mid. Okay, then we remove the numbers at the end of the pause locators. For the neck mid locators, we actually need a fourth, which we'll use to offset the joint position in the center. So we'll select the neck mid aim locator, duplicate it, edit duplicate. With the duplicate selected, we'll shift select the aim locator in parent. Let's quickly rebuild this. Now we're going to change the suffix from aim to OFF for offset. Okay. Now I'm just going to select each of these the neck top pause locator, activate the translate tool, holding down V for point snap. Just snap it to that top joint. Repeat this with the neck bottom pause locator. Okay. Now we're going to select each of these joints and make them a child of the corresponding aim locator. So the neck top FK joint will be a child of the neck top aim, and the neck bottom will be a child of the neck bottom aim. Okay, so now we're going to parent this neck mid FK to the neck mid offset locator, and then drag over the translate channels and set them to 0 so that it pops to its parent. Okay. So that done, we're going to start creating some constraints. The first being, we're going to constrain the neck mid position locator to both the neck top and neck bottom position locators. So that way it will average its position between them. So we're going to select both the neck bottom and neck top pause locator, shift select the neck mid pause locator, and then select constrain point. Now if we select either the top or bottom pause locator and translate it around, you can see the middle will average its position between them. Now we need to orient all these locators so that they each will aim toward one another. Okay, so open our hypergraph. So first we're going to aim the neck bottom aim toward the neck top pause. So we'll select the neck top pause, shift select the neck bottom aim, then activate our aim constraint, aim. So open the option box. Okay, so we can see we want the aim vector to be Z. So we're going to change it from 1, set that to a weight of 0, and give the Z-axis a weight of 1. And we want to leave our up vector at Y, which is what it is currently. We're going to change the world up vector to object up since we want to specify this up locator. So once we do that, let's type in the name cave01 underscore C neck BTTM 01 underscore up. Hit apply. Okay, so you can see we have this aim constraint. So next, let's aim the neck top aim to the neck bottom pause locator. So select the bottom pause locator, shift select the top aim locator. So rather than aiming it on Z with a weight of 1, which would flip this locator 180 degrees, which we could do, instead we're going to set this aim vector weight to -1. So that way it will still aim back toward the neck bottom locator, but its local axes will remain unchanged. And that's by setting it to a -1. And we just need to change the name of the up vector locator, so to neck top 01 up. Hit apply. And lastly, we're going to aim our neck mid toward our neck top pause locator. So we'll select the top pause locator first, shift select the neck mid aim locator. Let's reset our aim vector to positive Z, and then change the name of our up vector world up object to neck mid 01 up, and hit add. So now let's select any of our top or bottom pause locators, translate it around. You can see not only do we have the expansion and contraction, but we also have orientation information. Okay, so one last step. We're going to point constrain our neck mid up vector locator between the top and bottom up locators. And this will give us our twist, since if we rotate either end, it will also average the position of the neck mid up vector locator. So we'll select the top and bottom up vector locators first, shift select the neck mid up vector locator last, then select constrain point. So if we select, for instance, our neck bottom pause locator and rotate it, you can see that it also twists the neck mid aim locator. Okay, so switch to a side view. Let's activate our grid once again. So now let's position these pause locators up on the grid. It's holding down X. Let's just snap it up there. Do the same with the neck bottom. Okay, so we know that this ribbon is 3 units in length. And we have -1 for the and Z for the position of the bottom pause locator and +1 for the neck top pause locator. So those equal 2. Those add to a length of 2. So we need to set these to 1.5 for the top pause locator and -1.5 for the neck bottom pause locator, so that they're aligned exactly on the end of the ribbon. Let's hide our grid real quick. So one last step, we're going to select our ribbon geometry and then shift select all 3 of our neck FK joints, and then we're going to smooth bind it. So skin, bind skin, smooth bind. We'll bind to selected joints. Our bind method will be closest distance. Our number of max influences we're going to leave at 2. You want to make sure that after bind, maintain influences is disabled, it's not enabled. And we can leave everything else at the default. Hit bind. So now what we need to do, let's switch to a side view. We'll just quickly edit the profile, the influences of these joints, so that we can edit the profile of our ribbon. So selecting the neck mid FK joint, let's just translate it down. And switching to component mode, we're going to edit the smooth skin weights of these CVs so that we can get the arc that we want, or the profile that we want in our ribbon. Let's select this set of CVs and open up our component editor, window, general editors, component editor. A little difficult to see. Let's actually hide our locators. Yeah, that should be fine. So you want to make sure you're on the smooth skin tab. So here we're going to set the weight. We're going to increase the weight on the neck mid joint to 25% or 0.25. I'm going to use the down arrow key to select the last set of CVs and make sure that the weight is 100% on the neck bottom FK. You can use the up arrow to step through, so we can see that this set of CVs is 50% on each of the joints. We'll leave that. And then we'll set this set of CVs to 0.25 on the neck mid, just as we did on the other end. Step up one more and make sure that 100% of the weight is on the neck top FK joint. There we've quickly edited the profile of our ribbon. Switch back to object mode. Set this mid FK joint back to 0. Okay, let's show our locators. Let's show our model. Now let's quickly move our ribbon into place. So I've selected the top and bottom pause locators. Okay, let's quickly place them into place here. Let's hide our geometry once again. So we're going to select the neck bottom pause locator and holding down point snap, just snap it to the end of the chest joint. So with that pause locator selected, I'm going to shift select the end of the chest and then parent the neck bottom pause locator to the chest end joint. So now if I select the chest joint and rotate it, you can see that it leaves the head behind. So that way we'll get a sort of FK or IK, I'm sorry, on our neck so that we can position our head, leave it in place, and then adjust the body and know that it won't adjust the position of the head. Okay, so let's switch back to a side view. I'm going to select the offset locator for the neck mid, activate our translate tool. Well, first let's select our neck top pause and position that sort of at the base of the ear here. Now I'm going to select the offset locator for the neck mid and give it a little arc. I mean, not much in this case. Okay, so we're almost there. So now what we're going to do is create a two joint chain for the head. We're going to add significantly to it in our last lesson or last tutorial on facial rigging, but for now we'll just use this joint to add all the weights once we move into the skinning and deformations into part 2 of this tutorial. So select skeleton, joint tool, holding down V, we'll point snap to the neck top joint, show our geometry once again, and holding down shift, just drag out a straight line till it reaches the orbit of the eye, then hit enter. Back to a perspective view. Okay, let's actually snap this on that joint. Let's open our hypergraph and frame that. Of course, we're going to quickly rename it. Rename them. So we're going to search for joint and rename to cave 01 C head 0 and give it a JNT suffix underscore JNT underscore JNT. I'll select them both, display their local rotation axes. Display, component display, local rotation axes. Select the end joint and reorient it so that it matches its parent by selecting skeleton, orient joint tool, making sure that the orientation is set to none so that it has no orientation change relative to its parent. Okay. So now we know that all of our chest joints are oriented so that their Y is pointing out to the left side of the character. So we're going to make that same change to the head joint. Switching to component mode, we want to activate our question mark icon, which activates local rotation axes. We'll select each of these local rotation axes and then rotate them 90 degrees on the x-axis. So we'll type rotate minus R 90 0 0. Okay, so we can select these two joints and hide their local rotation axes. The last step, we're going to parent the neck top pause locator to the head joint. So select the top pause locator first, the head 01 joint, and hit P. So at this point, we're pretty much completely done with the hierarchy, with all the rig components. So there we can position our chest and know that we're not upsetting the position we've specified for the head joint, as well as select the head and position it any way we want. We get squash and stretch on the neck, and it acts as sort of like an FK where it doesn't disturb the position of the chest. Okay, so there we have our ribbon neck.
So in this lesson, what we're going to do is we're going to go through the process of creating on-screen animation selections for this character. We're going to use NURBS curves, but rather than constraining the joint, for instance, so that the rotations of the NURBS curve selection will drive the rotations of the arm FK joint in this case, what we're going to do is we're going to parent the shape node of that curve to the joint. In essence, we're basically tricking Maya. And how we'll do it is, an example is selecting this NURBS cube, and if you open the attribute, you can see that actually the shape node is the tab that's selected. So what Maya does when you select an object, a transform, it selects the shape node and then sort of steps up one node to the transform node. So knowing that, we're actually going to parent the shape node of the NURBS circle to the joints that we actually want it to control. So when we select that circle, it will actually step one up to select the joint. So that way you can have on-screen controls for the animator to select, and it will still leave all the transforms on that joint open. Okay, so we're going to start by creating a NURBS circle. Create NURBS primitives circle. Let's open the option box. Since X is the axis running down the length of the joint, and we want our NURBS circle to basically be perpendicular to that so that its normal points down the joint, we're going to leave the normal axis at X. And the other options we can leave at default. We want the sweep angle to be 360 degrees so that we have a complete circle. The radius we can adjust as needed based on the shape of the model. I'm going to leave the degree at cubic, third degree, and the number of sections I'll leave at 8. Once again, these are all options that you can change to suit your own needs for this character. So we'll hit create. Let's quickly rename this NURBS circle. Cave01 L arm01 underscore CRV. Okay, so now let's open our hypergraph. So once again, we're going to use this NURBS curve to control the arm01 FK joint. So with that curve selected, we're going to shift select the arm01 FK joint and then hit P to parent it. So now we're going to zero out the translate and rotate channels of the NURBS curve so that it positions and orients itself on the joint. Let's display our geometry quickly. Let's click on the Make NURBS Circle node in the channel box, and then you can change the radius to suit your character's size and shape. So here we'll just set that to 5 so that you can clearly see that in the scene. So now, while this NURBS curve is still a child of the arm01 FK joint, we're going to freeze the transformations on the curve. So with the curve selected, we'll select Modify, Freeze Transforms in the option box. Pretty much want it left at defaults, just making sure that the Translate, Rotate, and Scale channels are all enabled. Click on Freeze Transform. Then we can unparent this arm curve. And now we're going to use a Mel command to parent the shape node to the arm01 FK joint. Okay, so we're going to use the parent command. So type in parent minus R, which is relative, minus S, which is shape node. So we'll be parenting a shape node. And then the name of the control curve with its shape node actually specified. So what I mean is we'll type in cave01 underscore L underscore arm01 CRV shape, capital S. That specifies the shape node of that arm control. So if we select it here, you can see under the shapes in the control in the channel box, it has shape with the capital S at the end of that, specifying the shape node. Okay, so then this is what we'll be parenting, and the We'll need to specify what we're parenting it to. In this case, it's cave01 L arm01 underscore FK and semicolon. Select that and hit enter. So if we select our nerves circle, you can see that it actually selects our arm01FK. Let's open up our outliner so we can see a little more clearly what's happening here. I'm going to display the shape nodes in the outliner and right mouse click and reveal selected. And we can see, we expand this, we can see the cave01, the arm01 curve shape node is now a child of arm01FK. So once again, this is a way of creating an on-screen selection for the animator while still not locking up any of the transform channels on the actual joint itself. So an animator, in that way, through a Mel GUI, you could select the arm01FK, and if an animator wants to select their controls on screen, they'll still have that nerves curve to select from also. Once again, this selection object, it can be any transform. As long as it has a shape node, then you can use the same process to parent the shape node up to the joint that it's going to be controlling. So let's do this one more time for the, or two more times for the second and third arm FK joints. We'll start by creating nerves primitives circle. Let's hit G to repeat that. Open up the hypergraph. We'll frame those two. Quickly rename them. So modify search and replace names. We're going to replace nerves circle with cave01 L arm 0. We're going to add the underscore FK on the end. Actually change the numbering on these to 3 and 2. So select this. See, we have quite a few nodes in our hierarchy here. Okay, shift select the arm02FK. Hit P to parent. Zero out the translate and rotate channels. Show our model so we can adjust the radius of that nerve circle. Okay, so set that to 3.5. So with the arm02, let's change this to CRV. The arm02 CRV selected and still a child of the arm02FK joint, we're going to freeze the transformations on that nerves curve. Modify, freeze transformations. So we can now unparent that. And parent once again. Parent minus relative minus shape, cave01 L arm02 CRV shape. We're going to parent that to cave01 L arm02 underscore FK. Once again, we can select that curve. You can see that it's actually selecting the arm02FK. Let's quickly repeat this for the last arm-FK joint on the left-hand side. Select the curve, which we'll quickly rename to CRV. Shift select the arm03FK, parent. Zero out the translate and rotate channels on the nerves curve. Select the make nerve circle node and adjust the radius. Once again, we'll set this to 3.5. So with that nerves curve still a child of the arm03FK, modify, freeze transformations, unparent that nerves curve, repeat our parent command. Parent minus R minus S, cave01
L arm03 underscore curve shape. We're going to parent that to cave01 L arm03 underscore FK. Select that, hit enter. So there we've created 3 on-screen selections, which still leave the transforms of the joint open for animation. So rather than using constraints, by parenting the shape node, you still get the same effect where the animator still has an easy item to select on screen without locking up any of the channels of the joint that it's actually going to control. Okay, so in this lesson, we've built all of our rig components. So now it's time to assemble them all into a final hierarchy. So we're going to arrange this in basically 3 levels of transformation. The first being a root level node, which will transform all of the joints except for the arm and leg IK handles. Above that, we'll have an all level transform, which will include all of the arm and leg IK handles, as well as have the root level transform group node as a child. So with that all node, we'll be able to move the entire character in the scene. Above that, we'll have a group node under which we'll parent nodes that don't need to inherit any transformation value, because they'll be getting all of that information through constraints, whether they be a point constraint, parent, aim, or orient constraint. Okay, so let's open up our hypergraph. Scroll all the way to the end here. Let's create our basic hierarchy stack here. Okay, so first we're going to select Edit, Group, rename this. This is going to be cave01 underscore root. This will eventually move up to the top of the pelvis joint. We're going to want to give the animator clean rotate, translate, and scale values. So we're going to group this node to itself by hitting Control G or Command G. Rename this cave01 root underscore group. So we'll actually reposition this root node using the group. So holding down point snap, just snap it up to the top of the pelvis. So we're going to reselect the group node and then edit group twice. Now these 2 new group nodes are at the world origin, and we're going to leave them there. The top group node we're going to rename simply cave01, and this will never be transformed in the scene. The one below that will be our all node, so cave01 underscore all. So one more group node, edit group, we'll parent that to the cave01 node, and this we'll rename cave01 no transform group. So here we have the 3 basic components of our hierarchy. We have the root level transform, which is at the hip level, the all level transform, which is at the world origin, and then a no transform group. Okay, we can actually close the hypergraph. I'm going to close this for a second, give ourselves a little more screen real estate, and then open the outliner. So here at the bottom, we can split this panel in 2. So we'll do that. In the bottom panel, we'll scroll down to our hierarchy stack, expand that. So that way we can select from the top panel, just start at the top and work our way down, and then we have quick access to the hierarchy stack in the bottom window of the panel. Okay, so let's start. So at the very top is a group node containing all of our geometry, the models.
the low res and the high res. These will eventually inherit their transformations or get their transformations through smooth skinning and other deformers. So we can select that, shift select the node transform group, and hit P to parent. So next we have the chest joint and the pelvis joint. You'll notice that when we select each of them, the nearest IK handle, in this case the arms, and for the pelvis the leg, is not highlighted. So these are our root level transforms. So we'll select that, shift select the root, and hit parent. We can quickly test this by selecting the root node, activating translate for instance. It seems to be moving just about everything in the scene except for the head and the IK handles. So next we have the spine ribbon geometry, which is smooth skinned, so it will inherit its transformation through the smooth skinning parameters. We have a group node with the follicles on the spine ribbon, which are locked to a U and V position on that geometry. And then a ribbon pause locator, which is both point and aim constrained. So we can select these three nodes, select edit group to organize them. We're going to rename this to cave01 spine underscore grp. And parent this to the node transform group. So next we have a series of locators and distance dimension nodes, which are all constrained to arm rigging. So we can group these, rename it arm len underscore grp. And because they're getting their position, which is all that really matters with these nodes, from point constraints, we're going to parent it to the node transform group. So next we have the spine target locator, which has both a position and orient constraint to the second chest joint. We have the scapula position locator, which is point constrained to the end of the clavicle. And then there's also an aim constrained locator beneath that as a child. The scapula IK handle is point constrained as well as pole vector constrained. And we have the scapula length locators with the distance dimension node. So we can select all of these. Let's group them together. Name this to cave01 scap len underscore group. Once again, parent to the node transform group. So we have our clavicle IK follow, which have both point and pole vector constraints. And actually on the scapula pole vector, they don't have a pole vector constraint on the IK handles. That's not necessary on that. But for these, we do have a pole vector constraint. So they're point and pole vector constrained, so we can group these, rename it, cave01 clav follow underscore grp, parented to the node transform group node. So now we have our foot group nodes. These will control the IK handles for the legs. So we actually want to parent these under the all node. So with those two foot group nodes selected, we'll select the all node and hit P for parent. Here we have a set of locators and distance dimension nodes relating to the legs for their length. We can group these together, rename the group node, cave01 leg len underscore grp. Parent that group node to the node transform group. So you can see we're actually gotten pretty far through this whole hierarchy process. So here we have our all toes locator, which is point and parent constrained, so it's deriving both its position and orientation through those constraints. Quickly group them together, rename the group, cave01
all toes underscore grp, parent that to no transforms. Here we have our leg IK handles. They have point constraints on them, and so our IK handles, because they have the point constraints on them, they're getting their position through those constraints, so we will parent them to the no transform group node. Now in doing so, I've just introduced a problem into our hierarchy. It's not readily apparent at the moment, but later on when we do another test, just to test the entire hierarchy out completely, we'll see that problem at that point. And I'm doing that intentionally just to show how problems can crop up. It looks like we're doing something right here. And then once we see the problem, go back, figure out what it is, and then correct it. Okay, so next we have our ARM IK group. These we want to parent to our all node. And lastly, we have the ribbon, the follicle groups, and the middle position locator, which also has an aim constraint as a child for the neck ribbon. And just as with the spine, we'll group them together, rename the group K01 neck underscore grp, parented to the no transforms group node. And lastly, we have our head joint, which is a root level node. We'll parent that, as with the chest and pelvis, under the root. Okay. So last step, we're going to select all these distance dimension nodes and hide them, Control H. So now let's open up our hypergraph. Okay, so our hierarchy is a lot cleaner at this point. We have our root node, our all node, and then the no transforms group node. Do some quick tests here. That moves everything except for the IK handles. The all node is moving everything. And our no transform node is never meant to be moved. So now, with the hierarchy built, a quick test I like to do on hierarchy is to select the all node and to apply a transform value larger than 90 to all of the rotate and translate channels. So I'll drag select all of those channels. In this case, just type in 100. Frame our rig. So everything looks okay except for our legs. Our knees are not pointing forward as you would want or expect. So that's the problem that I spoke of earlier. So let's set our character back to the default position and track down this problem. Let's open up our hypergraph. So what's happening here is our IK handles are point constrained, so they're getting their positional information from the foot controllers. But we set these legs up with the no twist control system for the IK inside this grid. So what that means is while we're getting positional information, we're not getting any orientation control through a pole vector constraint. So we can fix that by simply parenting them to the foot controller. So that will, they'll inherit their position and orientation from their parent, the feet, which will be oriented properly to the body. So we'll select and delete both of those point constraints. Right mouse click and expand all on the foot controllers. And parent each of these IK handles to the end node on the foot. So select the right leg IK handle. Just select the end foot node, which is also in the same position at the ankle of the IK handle. Parent. Okay, let's quickly test this. Select our all node once again. Drag select over our rotate and translate channels. Type in 100. Let's frame our character. There we can see nothing's flipping, our knees are oriented properly, because now they're deriving their orientation information from their parents, the foot controllers. Okay, select our all node, reset it to 0. One last step, I'm going to select the Cave01 node and then lock all of the transform attributes. We'll leave the visibility available so we can hide and unhide the entire character, but the translate, rotate, and scale, let's lock selected. And at this point, we have our complete character hierarchy. So now our rig is completely built. So at this point, we're going to go over a very brief demo of the animation GUI, which is available for you to look at in more detail as files that come with this tutorial. Let's start by looking at the actual Mel script that I used to build this GUI. Okay, so it's pretty straightforward. I'm building a window, and once again, all this is available to you with quite a bit more commenting than what we see here, just to explain everything that's going on here, although there is good commenting in this. And so what I'm doing is I'm using a form layout, and that way I can define explicitly the position of buttons in the GUI. So here, let's scoot this over a bit. I'll just run through this pretty quickly. Here I'm defining different region buttons, the head and neck, the upper chest buttons, the right arm buttons, which include the clavicle, the FK arm, the IK controller, pole vector, and so forth. So what I do here with these string variables is I create a button, give it a label if necessary, define a width and a height, and then if a command is attached to this, I'll execute the command. In this case, I'm using select toggle, the character prefix, which is one of the variables passed into the global procedure, and then I choose the selection object. So pretty straightforward. And in this section, I actually define the position within the form layout of each of the buttons. Quite a bit here, but once you get into a rhythm, it goes pretty quickly. And this can serve as a template that you can edit and refine and define your own GUI. But this is the section that I want to talk about here. Here's an actual procedure that we have which will allow us to switch between the FK and IK modes in our arms. So we'll quickly go over how this works. So once again, we have the global string, which is the character prefix, which we'll predefine here. And then what I do is I look to see if the button name, I use the gmatch command, which actually looks to see if the button name matches this string. And what this means to FK, that button setting will be the text on the button if we're already in IK mode and need to switch to FK. So if that's the case, if this is true, then we'll execute the following commands. The first, I unparent all the clavicle rigging from the auto clavicle joint. Because the FK and IK arms rotate at slightly different values, meaning that the auto clavicle for the IK has a different amount of rotation to reach the end of the IK handle as does the auto clavicle for the FK joint. In order to avoid a pop, I just simply unparent all the clavicle rigging, and then I'll reparent it again at the end once the switch is made. So I start by unparenting the clavicle from the auto clavicle, then I disable the IK weights of the orient constraints. Since we're already in IK mode and going to switch to FK, the FK orients are already set at 0. So I'll set everything at 0. And then, as I say here, I record and store the rotate values of the IK joints. So the first and second. And then I set the FK rotate values to match those of the IK. In this section, what I do is I record both the IK scale X values as well as the FK scale X values. And the reason being is, in order to match the scale of the IK arms, I'll need to multiply those two values. And then here, I'm setting the scale X of each of the FK joints to equal this float attribute, which is a multiplication of the scale X of each IK and FK joint. And the reason being is because we are allowed to scale both the FK and IK. Later on we'll see that I reset the IK multiply and divide node so that it resets itself to 1 basically. And if I were to plug in that scale value into the FK joints, although the IK arm will in actuality be scaled to 2 or 2.5, whatever the value is, it thinks its default scale value is 1. So if we were to set the FK value to equal that of the IK, it would think it's at 1 also, which is actually incorrect. So we need to multiply the FK scale X value by whatever the new IK scale X value is. Once again, a bit to absorb at this point, but in the final MEL script that will be available for you to look at, this is documented quite well. So at this point, once we switch the orientations as well as adjusted the scale of the FK arm joint, then we switch on the orient constraints so that we're now in FK mode. We set those orient constraint values to 1. In these final sections, I enable the visibility of the FK arm controls and then disable the visibility of the IK arm control. Then I do some button switching here so that I hide visibility false. I hide the IK arm button and then display the FK arm buttons. And then lastly, I reparent all the clavicle rigging to the auto clavicle, and then I'll select the first FK arm joint. So in the opposite direction, if I'm switching from FK to IK mode, once again I start by unparenting the clavicle rigging, switching the weight of the FK orient constraints to 0, so everything's at 0 at this point. Then I'll just quickly create a point constraint, which will allow me to reposition the IK handle to the end of the FK arm. Then I'll delete that point constraint. It's only needed just to reposition it. So at this point, I'll record all the translate X of the FK joints and then set the arm joints to match those. So that will do is, I don't want to rely on scaling to affect the length of my IK arm. And the reason being is I still want to be able to stretch my IK arm, but from this new position, which will match the scaled position of the FK arm. So rather than relying on scaling, I will reposition the IK controller, which will stretch and straighten the arm, and then adjust the translate X values of our IK joints, and then set the scaling to 1. So that way we match the length and the bend of the elongated FK arm, but then our scale value is still at 1, and our multiply divide node, which is used to squash and stretch the IK arm,
is reset to think that it's at 1. We set a new default value for the input 2x, which is done here. I set the multiply and divide node to equal the combined translate x length of all the FK joints. So that's the new basis from which the IK arm scaling is calculated from. Then in this section, I turn on the IK orient constraints. I set their values to 1. I'll reset the IK pole vector to 0, or rather the twist attribute on the IK handle. I'll set that to 0. I'll toggle the visibility of the joints so that now the IK joints are turned invisible, or IK joints are turned visible, the FK joints are turned invisible, and then the IK controller is visible. Then lastly, I switch the visibility of the buttons in the GUI. All the FK buttons, their visibility is turned to false, whereas the IK arm and the controller, their visibility is set to true. And then, once again, I reparent all the clavicle rigging to the auto clavicle, and then select the IK arm controller. So quite a bit there, but let's do a quick demo and see how this works actually. It's a very simple GUI, very simple in appearance, but we'll add on to it as we move on to the next sections with the skinning as well as the facial rigging. We'll add new tabs to this GUI, as well as a few other buttons. So I've activated my GUI here. You can see we just have basic buttons to select some of the controls here. I'm using the select toggle mode here. So for instance, if I were to select the chest joint, I would reselect it, which unselects it. Otherwise, I could select chest 1 and just click and select chest 2, and then click on each of them to deselect them. So pretty much every control is in here, all the fingers, the carpals, there's the wrist, the neck and head. Okay, so now what we need to do is just demonstrate how this arm works. So right now, we're in IK mode. So I'm just going to move this IK arm around, give it a little twist in the elbow, then I'm going to switch to FK. There was no shift in the arm, and it's now displayed our FKI controllers, our FK arm controllers, selected the first FK joint, and now our IK controller button is no longer visible. So that's selected. I'll just go in and arbitrarily rotate this and scale it a little bit. Select our next arm joint, scale it, rotate it a bit, give the wrist a little rotation, just arbitrarily, doesn't really matter. Now I'm going to switch from FK to IK. Once again, no jump. You can see our IK controller is visible and selected. Our FK buttons are no longer visible. So I'm going to go ahead at this point and stretch out our arm. Then I'm going to switch back to FK. So there we go. At this point, I'm going to turn on the auto clavicle. Let's turn it to 2, not a very extreme value. Okay, so let's go in and start rotating some of these. Okay, set their scale values. Add some bend back into this. Scale it down a bit. Okay. Let's rotate this some more. Switch back to IK. Once again, no shift. We're still in auto clavicle mode. So there we have simple GUI, which updates based on whether or not we're in IK or FK mode. And this is done by monitoring the label
on this button here, rather than using a script job. One of the upsides is that you don't have a script job that you need to monitor. One of the downsides is you need to update the timeline in order to see that change in the button. But that's also true with the script job as well. You'll need to somehow update that timeline. So there's a quick demo of the GUI. So once again, this is a part of the documentation that's available with these lessons, and just a quick demo there. So once we go through the Mel script in detail in the text format, all this will be a lot more clear, and is building on the auto clavicle rigging that we built earlier on, as well as the FKIK orientation and scale switching, which we also built. This is simply a way of controlling it and then having an animation GUI that reflects what state of FK or IK the arms are in. Otherwise, the GUI is fairly straightforward. Eventually, we'll add a few other controls, offset controls for the arms and legs once we get into the skinning section, which will go on this page, and then we'll add a head tab onto this, and then create a couple of tabs, and then a few other buttons for select all, selecting groups. But this is the basic GUI at this point.